ਨਾਨਕ ਨਾਮ ਦਾ ਤਾਜ ਇਲਾਹੀ ਸੀਸ ਸਜਾਵਣ ਵਾਲਾ, ਜਿਸ ਦੀ ਹੋਂਦ ਚ ਸ਼ਬਦ ਗੁਰੂ ਦਾ ਜਗੇ ਪੁਨੀਤ ਉਜਾਲਾ। ਸਦਾ ਸਦਾ ਪੁਰ ਨੂਰ ਰਹੇ, ਸਦਾ ਸਦਾ ਪੁਰ ਨੂਰ ਰਹੇ। ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ, ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ। ਸਦਾ ਸਦਾ ਪੁਰ ਨੂਰ ਰਹੇ, ਪੁਰ ਨੂਰ ਰਹੇ, ਪੁਰ ਨੂਰ ਰਹੇ। ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ। ਅਨਹਤ ਨਾਦ ਬਜੇ, आहत जलन बुझे, अमृत शब्द वरे, तन मन तीन हरे। सदा सदा पुर नूर रहे, पुर नूर रहे, पुर नूर रहे। गुरु नानक देव विश्व विद्याला। धरती अंबर पवन समुंदर सूरज चंद सितारे, एक दी तुन विच गावन वावन राग इलाही सारे। सत सुहान सदा मन चाओ, सत सुहान सदा मन चाओ। एह गुरवाक उजाला, सदा रहे परगास रूप। गुरु नानक देव विश्व विद्याला, गुरु नानक देव विश्व विद्याला। चिंतक सिरजक रसक विनोदी, सहज निमर विसमादी। निर्मल निरभव सच दा खोजी, विगसे आद जुगादी। रोशन हो वंडे रुशनाई, रोशन हो वंडे रुशनाई। दिखया पावन वाला, गुरु नानक देव विश्व विद्याला, गुरु नानक देव विश्व विद्याला। जिथे मिलदी ओट ने ओटिया, पौंदे मान ने माणे। ओह दर उसदा ओह कर उसदा, एह गुरवाक वखाणे। जिथे मिलदी ओट ने ओटिया, पौंदे मान ने माणे। ओह दर उसदा ओह कर उसदा, एह गुरवाक वखाणे। ओथे नदर मेहर दी होवे, ओथे नदर मेहर दी होवे। जिथे नीच समाला, गुरु नानक देव विश्व विद्याला, गुरु नानक देव विश्व विद्याला, गुरु नानक देव विश्व विद्याला, गुरु नानक देव विश्व विद्याला।
Hi, good morning. Hi, good morning, Professor Vishwanathan.
Oh, good morning, Bindya. How are you?
Dr. Mahajan.
Good Dr. Mahajan.
Yes.
Good morning, sir.
Good morning, Dr.
Good
Pandey.
morning.
Yes. Okay, Jasmine, I think we can start. Your voice, you're not audible.
I'm not audible?
Yes, everybody else is audible. The host for the today is not audible.
Oh, I see. Okay. I was wondering if that you meant me.
No. Jasmine. Yeah, Jasmine, can you check what is the problem with your audios?
Maybe the mic is.
Hello, Professor Ramanathan.
Hi, how are you?
We met, I think, during my PhD days when I was in ISC Bangalore.
Oh, yeah. That's
You
true.
might not remember me. I was
Yeah, no, after you tell me, I can recall, but not otherwise. Yeah.
Deepika was my batchmate, not batchmate, but I was a regular
contemporary.
Yeah.
So, Priyal, I think.
Good morning, ma'am.
Yeah, good morning. Maybe you can start then. Jasmine has some problems with the,
Jasmine, will you start or should I? You can check it once. No, you are still not on. I'll start, you can check it later on. Okay. Wishing you all a very good morning. This is Priyal Sharma, a final year chemistry undergraduate, GNDU, and a member of organizing committee for NCSOS. I hereby extend a very hearty welcome to all our dear audience on the behalf of our organizing committee members of NSCoS 2020. Yesterday has been very fruitful in terms of all the scientific insights via our eminent speakers and lab demonstrations. On this note, let's hope for more brainstorming sessions as we here begin our second day of National Students Conference on Spectroscopy 2020. Now over to Jasmine, a final year chemistry undergraduate GNDU and a core committee member of CYROX. And over to you, Jasmine, if you can continue. I think I need to continue. Okay, so the day today is divided into two sessions. So without any further delay, I would like to invite Dr. Aman Mahajan, Assistant Professor at Department of Physics, GNDU. He has done his specialization in condensed matter physics in controlled growth of molecular and metal oxide nanostructured materials, light emitting and gas sensing applications. He will be chairing our first session of the day, which includes 3 scientific talks and 2 live poster sessions. So here I would request Dr. Aman Mahajan to start the session. Over to you.
Good morning to all of you. First, I am thankful to the organizers, especially Dr. Bindia, for taking initiative to conduct this type of the conference for students covering spectroscopy from the atomic to molecular level as well as the nuclear level. As discussed earlier in today's session, there are 3 invited talks by Professor K.S. Vishwanathan, Dr. Pandey, and Professor Sudipta, along with the 2 live poster sessions in which the participants shall show their poster based on their research topics. And in this session, each talk will be of the 50 to 55 minutes, and I request all the speakers to kindly complete their presentation within a time for a smooth conduct of this session. So with this, I'm going to introduce the first speaker of today's morning session, Professor K.S. Vishwanathan, who is retired from the Department of Chemical Sciences, IISER Mohali. At present, he is the adjunct faculty at Department of Chemistry, IIT Madras, as well as visiting professor, Department of Science, Korea University. He obtained his PhD in the physical chemistry from the Vanderbilt University, USA. He has done the post-graduation and the graduation in chemistry at the Vivekananda College, Madras. His research interests involve matrix isolation, IS spectroscopy for study of conformation, non-covalent interaction, reaction of the high temperature species, fluorescence spectroscopy of lanthanides and actinides, laser-induced breakdown spectroscopy, and as well as he is much more interested in the science education at school and university levels. And he is a recipient of the Indian Spectrophysics Association Award in 2010 for contribution in matrix isolation and fluorescence spectroscopy. Also, he obtained the Kalpakam Science and Technology Award for the best basic research work during the 1999 and 2001. So with this brief introduction, I now invite the Professor Vishwanathan. Sir, please.
Thank you. Yeah, thank you for the margin. And
thank you, sir.
I hope I think I am audible. So let me get started with my talk. I will share my screen. I hope the screen is visible. I'll put it onto full screen mode. Yeah. Yeah, but at the outset, I would like to thank the organizers for giving me this opportunity to talk to the students and the faculty on a topic that I have been working on for quite some time, infrared spectroscopy. In fact, all of my career has been in using infrared spectroscopy to study hydrogen bonding interactions and molecular structures, the molecular conformations in ultra low temperature matrices like 10 Kelvin matrices. And of course, the reason why we go to 10 Kelvin is to basically isolate the molecule, freeze them out, and then be in a position to study unambiguously the infrared spectroscopy of these systems. Of course, I will not talk to you about my research today because this was supposed to be more aimed at undergraduate and postgraduate students. Therefore, I will talk to you about the basics of infrared spectroscopy. And if you're interested in what we have, what I have done, maybe you can just write to me and I will send you relevant material on the areas of research that I have been doing over the last many years. Now, infrared spectroscopy is one powerful tool that is used in the study elucidating molecular structures, molecular bonding information, and so on. You already have listened to many speakers yesterday. Some of them spoke on fluorescence spectroscopy. You had a talk on EPR. You had a talk on a couple of talks on NMR, and so on. And the point to be made here is that spectroscopy is the sum total of many branches, many tools, and you need very often more than one or more than two to be able to unambiguously tell what the system is that you're studying, to be able to unravel the mysteries of the system you're studying. So there is no such thing as one tool being better than the other. You need all of them to complement each other and provide you the necessary information so as to understand the system that you are looking at. Infrared spectroscopy is one such tool. It's a very powerful tool, all right, but it is one such tool. And very often you'll have to couple infrared spectroscopy with mass spectroscopy and UV visible and fluorescence and so on, so that you completely understand the system, or at least understand the system in as much detail as possible. So we will look at the importance first of molecular structure. Then I will give you the introductions on the basics of the infrared spectroscopy. And then we will look at some applications in structural characterization, how to understand bonding in molecules, and maybe some applications in analytical chemistry using infrared spectroscopy. And that's the reason why I have titled this talk as Infrared Spectroscopy, a window to molecular structure. The reason being, through the use of infrared spectroscopy, very often you can get good structural information, and that's the reason why I titled this talk as Window to Molecular Structure. You'll see that today's science doesn't go in isolation. You know, there is a lot of give and take between various branches of science. Chemistry has to borrow and give a lot to physics. Physics has to give a lot and borrow from materials, and mathematics and biology and medicine. All of them are interrelated. And therefore, it is very essential to understand this interrelationship when you start your research career. You know, when you're studying undergraduate, sometimes we say, oh, I don't like inorganic chemistry, or I don't like organic chemistry, so I will sort of skip it. I will not concentrate on that, and so on. But you will see, once you get to start doing research, you don't have that liberty. You have to be able to appreciate and understand other branches of science in order to do your own branch of science. For example, I have done basically physical chemistry. I use spectroscopy, but I rely a lot on organic chemistry to make my molecules. I rely on organic chemists to help me make the molecules. And therefore, there's a lot of give and take between various subjects. And this is essential to understand when you start your research career. Why are we looking at molecular structures in the first place? Chemistry is essentially the art and science of understanding molecular structure. If you ask me in one sentence, can you tell me what chemistry is? My definition of chemistry would be that it is the methodology or the art and science where you understand molecular structure. Chemistry is not 2 KMnO4 plus 16 HCl giving me 2 KCl plus 2 MnCl2 plus 8 H2O plus 5 Cl2. That's not chemistry. That's only a way of bookkeeping chemistry. Chemistry essentially is to study molecular structures, and from the molecular structure to see whether I can understand the properties And from the properties to see whether I can make molecules that can have functions. And if I want to alter the functions, then I know how to alter the structure. And therefore, this trigonal relationship is very, very important. So the structure imparts properties, properties provide functions, and to alter those functions, I need to change the structure all over again. And therefore, this cyclical nature, the cyclical relationship is very, very important to understand. And the foundation for all sciences basically is in trying to understand molecular structure. And that is where chemistry provides a lot of important information to, in fact, to all of sciences. You have studied from high school, you know, that if it is asked of you, why is diamond hard and graphite soft, immediately you start giving the answer that diamond has got a network structure of tetrahedral carbons, graphite has got a planar sheet structure, which can slide over each other, and therefore it is soft. But the essence is, you are already being introduced to the concept of a structure property relationship at this point. So when we try to give an explanation as to why diamond is hard, what you're really trying to do is to correlate a property of diamond to its structure. And that is what chemistry is all about. Likewise, you know, if you have para-dichlorobenzene and ortho-dichlorobenzene, the para-dichlorobenzene has a higher melting point, the ortho-dichlorobenzene has a lower melting point. And if you ask the question why, it is the symmetry of the para-dichlorobenzene that allows it to fit into a crystal quite snugly, quite efficiently, and therefore has a higher melting point. Again, you will see that the physical property here is actually driven by molecular structure and molecular symmetry. Biology makes use in a big way of molecular structure. For example, sulfur drugs, which are often given to you for certain infections, bacterial infections, which is actually a derivative of para-aminobenzoic acid. The sulfur drug itself is a sulfonamide base, which has got a similarity in structure to para-aminobenzoic acid. The bacteria uses para-aminobenzoic acid for its survival. And what you do is you trick the bacteria by giving a molecule which has got a very similar structure, and therefore trick it into not providing its food so efficiently. And that is how the sulfur drugs work, where you try to mimic the structure of a very important molecule for the bacteria, and therefore arresting the growth of the bacteria. These are called bacteriostatic medicines, and that's how they work. But they essentially make use of the fact that there is a structural similarity between the drug and between the molecule which the bacteria wants. And that is how you arrest the growth of the bacteria. And therefore, there are enough number of examples that one can give, which would convince you that it is very essential to understand molecular structure if you really want to get to the root of any problem. Now, molecular structure studies can be done in many ways. Experimentally, you can use molecular rotation spectroscopy, which is microwave spectroscopy. You can use molecular vibrations, which is what I will be talking to you about. You can use spin, which was spoken to you yesterday. It could be either nuclear magnetic resonance or electron spin. You can do electronic spectroscopy, and there are a whole lot of other techniques. That's why I put etc., 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 not to leave out X-ray studies. On the theoretical side, of course, today almost everybody uses ab initio methods to arrive at structural information, and very often you have to use theoretical methods and experimental methods to support each other to understand the problem better. In fact, in my own group, people would do experiments, people would also do calculations, and then see how to explain my experiments based on these calculations. Experiments alone sometimes is not enough. Theory alone is no use unless you have experiments, and these two should go hand in hand. And today what we will be doing is we'll be looking at molecular vibrations. Of course, this would have been shown to you by, I'm very sure, by other speakers too, where essentially you are given the frequency of light and what each wavelength actually does. You know, if you are in the microwave region, then of course you do rotation. If you are in radio frequency region, you do nuclear magnetic resonance. If you are in infrared region, you do vibration spectroscopy. And of course, if you go any shorter, you will be doing electronic. And if you go into the gamma ray region, you will essentially be doing Moss-Boy spectroscopy. And as I said earlier, it is very essential for you to be able to use all of these techniques, or at least a combination of these techniques, in order to understand problems in greater detail. You will hardly ever understand the problem in great detail if you only use one of them. You need to have a combination in some complementary fashion to be able to understand the problem in great detail. Today, we will be looking at vibration spectroscopy. which molecular vibrations is basically what is induced by infrared spectroscopy. So if you shine infrared light on molecules, what the molecules basically will start doing is they will start to vibrate in a little more crazy fashion. If I put microwave spectroscopy, the molecule will start to rotate, and therefore you can see that I can excite different degrees of freedom depending on the frequency region that I am using in my experiment. In molecular vibrations, I will be using infrared spectroscopy and very popularly called as just IR spectroscopy. Now, vibrational spectroscopy can give you molecular structure information, which I said is very, very important for you as a scientist. Vibrational spectroscopy or infrared spectroscopy can also be used to do analytical applications, maybe to find out concentrations and so on and so forth. So you can get both structural, very fundamental information. You can also use it for finding out what is there and how much is there, which is an analytical application. So both these can be used, and this is not true of just infrared. It is true of any other spectroscopic technique. You can use fluorescence for structural information. You can also use fluorescence for analytical applications and so on. So this is a general phenomena, but you should keep in mind that I can use spectroscopy to get basic information about the molecular structure and bonding, and I can also get information on the analytical processes. What wavelength of electromagnetic radiation? I said infrared, but what numbers? Well, the wavelength essentially ranges from about 2.5 microns to 25 microns, and you call that as a mid-infrared region, which is what you would be using very often if you're an organic chemist. Or in terms of wave numbers, that would be 4,000 to 400 wave numbers. So all your vibrations, carbonyl, correct, but what numbers? Well, the wavelength essentially ranges from about 2.5 microns to 25 microns. Yeah, I will, pardon me? I didn't get you. Okay, so when I say it ranges from 2.5 to 25 microns, I'm talking about the one that is popularly used. If you want to go to shorter wavelengths, yes, you can go down to shorter wavelengths, and then you'll be starting to look at overtones and combination bands and so on. But most of the fundamental vibrations will show up in the region 2.5 to 25 microns, and that is what is very popularly used in the mid-IR region if you're an organic chemist. Of course, you can go to longer wavelengths, 400, my wave numbers to 20 wave numbers, in which case, of course, you would be looking at many of these very low frequency vibrations. Hydrogen bonding interactions would show up in these regions. Many inorganic molecules will show up in these regions. And therefore, depending on what it is you want to look at, if you want to look at the fundamentals of most organic molecules, is 2.5 to 25. That's essentially 4,000 to 400 wave numbers. So most spectral regions that are covered is this. If you want to look at overtones and other combination bands, of course, you can go to shorter wavelengths, as somebody mentioned, you can go to 0.5, but then you're looking at the higher frequency combination bands or overtones and so on. But there is no point in looking at overtones if you have not understood your fundamentals. You will not be able to make assignments of the overtones if you don't know where the fundamental really shows up. And of course, then you have the far infrared, which essentially is for looking at very low frequency vibrations and inorganic molecules and so on and so forth. So this is how generally, and these are typical numbers, and this is what you'll be looking at. Now let's look at get a feel for these numbers. If I say that I have a nitric oxide molecule and has a vibration of around 1900 wave numbers. Now, so that is that's a vibrational wave number that I have given to you. That is the number of wavelengths per centimeter. Now, what is the frequency with which this molecule will vibrate? The frequency with which this molecule will vibrate, of course, can be given by this very simple equation, nu equals C nu bar, and it will turn out that it's about 57 into 10 power 12 vibrations per second. That's an enormously large number. Or in terms of time, every vibration takes about a femtosecond or about tens of femtoseconds. And that's a time scale you are looking at, and that's the magnitude in terms of vibrations per second you're looking at. Put it more bluntly, it's about 57 trillion vibrations per second, and this is what you have set out to study. It looks a little horrendous, but it is not really that bad, as you will see. These can be studied quite elegantly. Now look at how can molecules vibrate. When I say the molecules are vibrating, if it's a diatomic, there is no issue. There's only one, like the nitric oxide molecule. There's only one way it can do, and that is just this. It doesn't know of any other way by which it can vibrate. So a diatomic molecule has only one mode of vibration, which is essentially just a stretching vibration, and that's it. But if you go to higher atomic molecules, triatomic and polyatomic molecules, then the picture starts to get a little complicated. For example, in the stretching vibrations in water, and I will see whether I can share that for you. Yes, I have shared this. I hope you can see the vibrational pattern of water. That's, of course, the bending vibration, which, of course, you would never have in a diatomic. There's no way a diatomic can bend. But triatomic, yes, you have a bending vibration, or you can have this, which is the symmetric stretch, or you can have one more, which is the antisymmetric stretch. I like to call it antisymmetric stretch rather than asymmetric stretch, because asymmetric means no symmetry. But if you go to group theory and look at it, there is a group theoretical representation that you can give for this vibration. Therefore, it is better to call it as an antisymmetric stretch, because it is symmetric with respect to some operations and antisymmetric with respect to some operations. And the little arrow that I have shown is the arrow of the dipole moment and the direction of the dipole moment, which is changing during that vibration. So if I have an antisymmetric stretch, the dipole moment changes along that direction. If it's a stretching vibration, it changes along the direction shown by the arrow. And if it's a bending, it's also very, very similar. And in fact, if you have, those of you who have done group theory, you will recognize that the bending and the symmetric stretch behave in group theoretical terms very similarly, and the antisymmetric stretch behaves differently. And that's basically what it is. Now, let me show you one more. That's the carbon dioxide molecule. And you can see the carbon dioxide molecule. This one is actually a bending vibration. And it has got two different bends. It can either bend one in the horizontal plane or in a vertical plane, depending on what you want to call it, horizontal or vertical, but in two orthogonal planes. And you can see the dipole moment vector pointing in a direction in which the dipole moment is actually changing. And you can see this for the bending. And the point here is that two bending vibrations have exactly the same frequency, and that is driven by symmetry of the molecule, and we call them as degenerate vibrations. You can also have a symmetric stretch, which of course there is no dipole change, and therefore there is no arrow to tell you that. And finally, of course, you have the antisymmetric stretch, in which the dipole moment points along the molecular axis. So you can see that these are different . Yes. So these are, so the water molecule has a symmetric stretch, it has an antisymmetric stretch, and it has a bend. There's three modes of vibration. And I will tell you a little later, we call it as normal modes. And I will also tell you what we mean by a normal mode. Why is it not moving? Yeah. We also saw the symmetric stretch in carbon dioxide. We saw the antisymmetric stretch in carbon dioxide, and we saw the bending vibration in carbon dioxide, which is degenerate. In other words, carbon dioxide has two bending vibrations and a total of 4 normal modes. And if you remember the little relationship we give you, that 3n minus 5 is the number of normal modes for a linear molecule, and 3n minus 6 for a nonlinear molecule, then it works out fine. Water has 3, carbon dioxide has 4. And this is one important aspect. Vibrational spectroscopy, by the way the vibrations pan out, can tell you whether the molecule is linear or not. And that is how you'd be able to figure out structural information from infrared spectroscopy. Now the question is, when I say stretching, how much is the molecule really stretching? You know, I showed you as if it is stretching in a big way. Mind you, in real life situation, if the average bond length was 154 picometers, it is probably stretching by about 10 picometers here and there. That's about it. It's a very small amplitude. So just imagine, this is very high frequency, enormously high frequency, and the displacement is enormously small. And we are saying, I want to study this small displacement and this high frequency. Likewise, bending is a few degrees. It's not like it is flapping back and forth, at least in the fundamental. It's only moving by a very small amount, and it is this small distortion or this small vibrational pattern that we are trying to study when we look at vibrational spectroscopy. I'll also show you, as the molecule gets bigger and bigger, you will actually find that the pattern gets even more weirder. For example, I will show you this. This is benzene, and you can see that there is this benzene back and forth motion, some sort of a rocking motion. And benzene has 12 atoms, and therefore you will find that it has 30 normal modes of vibration, and one can go through all of it one after the other. Some of the interesting ones are here, for example. This is not infrared active, but this is what we call as a benzene breathing mode, which I am very sure Sukumar might have pointed out to you. This is something you can study in Raman, but you cannot study in infrared because there is no change in the dipole moment. And if you go down all the way to the bottom, all you will see is the various CH stretches, the anti-symmetric CH stretches, which are all infrared active. But the point is that benzene has these 13 normal modes. Water has 3 normal modes, and carbon dioxide has 4 normal modes. And a little while later, I will tell you, what do I really mean by these normal modes? Now, let me get back to my slide presentation. Yeah, this is where we were. So what have we done so far? We have learned about normal modes. We have seen that molecules have different numbers of these normal modes depending on the number of atoms they have. And we've also seen that there are different types of vibrations. You can have a stretch, you can have a bend, you can have an anti-symmetric stretch, rocking, wagging, all sorts of torsional motions and all sorts of different motions of the molecules, all of which constitute the normal modes of vibration. And these vibrations is not that they go, like miles. They're only like a few picometers back and forth, a few degrees back and forth. And it is this vibrational motion that I have set out to study. So the normal modes of water, we said, was a symmetric stretch in which the 2 hydrogens go back and forth. The anti-symmetric stretch, even though I put as asymmetric, it is better to be put as anti-symmetric, and it goes while one stretches, the other compresses, and vice versa. And in the bend, the 2 hydrogens come towards each other, constituting a bending motion. And we call these 3 as the normal modes of water. So the question now is, why are these called the normal modes, and what do I mean by saying that these are normal modes? Let me look at this little picture. It's a double pendulum. You can actually make this and test it out yourself. All I have done is there's a thread with 2 weights hanging at the bottom, and the thread goes across a bar that I have put here. So these 2 pendula are coupled. And now I pull both these bobs, I pull them towards me, and I leave it. In other words, I've excited a certain vibrational motion of this pendulum. So I pull both these bobs towards me and I leave it. And what do you expect the pendulum to do? It will start moving back and forth with the 2 bobs moving in unison. Of course, you got to keep in mind that the length of the 2 pendulums must be equal or nearly equal. You must keep them as equal as possible. If you don't do that, that's a complication, which you can try to analyze yourself. But as long as they're equal and I pull them towards me and I leave it, then you will see that the 2 pendula will go back and forth in unison. I can do something else. I can pull one pendulum towards me and the other bob, I can take it away from me, and then I leave it. And then you will find that the 2 pendula will start to move again in unison, but with a different phase relationship. While one bob is towards me, the other bob will be away from me. And when that bob comes towards me, the first bob will go away from me, and this will continue forever. In other words, in the first case, I excited a certain vibration. I induced a certain vibration by pulling both towards me, and the molecule and the system responded by maintaining that relationship. In the second case, I excited or I induced a certain vibration by pulling one towards me and the other away from me, and I left it. And then the system responded by maintaining that relationship further. Now let us say I pull only one towards me and I leave it. What do you think will happen? Do you think that motion will be maintained? No. Make this little pendulum for yourself and see what happens. What will really happen is the first bob will go towards me and back and forth away from me and towards me for a while, and slowly it will slow down. And then the other bob will start oscillating. Then that will stop after some time, and the first one will start to move. In other words, there's a transfer of energy from one to the other. But the point to be noted is the following. I excited one vibration, and the system did not maintain that. System went into a different mode altogether. So while I excited the first bob, I did not excite the second bob, but after a while, the second bob started moving. In other words, in this case, the vibration that I excited was not the one that was maintained by the system. In the first two cases, whatever vibration I excited, the system continued to make that particular motion for the rest of the time. Whereas in the third case, the vibration that I excited was not the one that was maintained. We call the first one, therefore, a normal mode. A normal mode is one which you can excite, and the system will, it's a natural frequency. It will keep doing that. I excite this, it did what I excited. Therefore, it's a normal mode. I excited this, it did not do what I excited, it did something else after a while. Therefore, this is not a normal mode. But I can write this motion that I see here as a linear combination of the normal modes. So the normal modes basically become a basis for representing the molecular vibrations that you will possibly see. Now, in terms of water, what does that mean? If I take the water molecule, and let us say you have the capability to see the water molecule, and supposing you pull the two hydrogens away from you, just like you pull the two bobs, you pull the two molecules away pull the two atoms of hydrogen away from oxygen, and then you left it. What will the water molecule do? It will just do what you did. If I did this, I pulled one hydrogen away and I pushed one hydrogen towards oxygen, and then I left it. What will the system do? It will do whatever you excited. And therefore, these two serve as the normal modes. If I take the water molecule and I bend the two hydrogens, what will it do? Well, it will keep bending and continuing that motion. But if I took the water molecule and I pulled one hydrogen only and I left it, will that one alone do the vibration? No. It will do the vibration. Little while later, the second fellow will start. Little while later, the first fellow will start. In other words, whatever you excited is not maintained by the system. Therefore, that vibration which you excited is not a normal mode. But that motion that you see subsequent to that can always be expressed as a linear combination of the normal modes, which turns out to be a basis for your representations. And this is what it is. Now, very often I ask the students, if I could take the water molecule and hang it up in front of me and I keep looking at it, what do you think the water molecule will do? Will it do a stretch? Will it do an antisymmetric stretch? Or will it do a bend? Or will it do a little while antisymmetric, a little while bend, and a little while symmetric? What is it that you're really going to see? Well, keep in mind that vibrations have a 0-point energy, meaning that all vibrations are active all the time, even at 0 Kelvin. So which means the water molecule is really doing the stretch, the antisymmetric, the symmetric, and the bend all the time. And therefore, what you really will see is some very complicated motion of the water molecule. But you know fully well, whatever be that complicated motion, I can resolve it in terms of these normal modes, which are the basis for the representation of any vibrational pattern the molecule might show you. And that is what the normal vibrations basically are. So if you pluck a normal vibration, the molecule will perform the particular vibration. If you pluck a vibration that is not a normal vibration, the molecule will go crazy. But whatever it does subsequently can always be expressed as a linear combination of these normal modes. And that is how you understand normal modes. The very crisp answer is a normal mode is an uncoupled vibration, meaning if you pluck that vibration, it does not get coupled to any other vibration. It just does what you coupled, what you plucked, provided it's a normal mode. If it is not a normal mode, then of course you go into complicated patterns, and which are actually called Lissajous patterns. And there are many nice experiments that you can do to understand Lissajous patterns. But as of now, a normal mode is the mode that serves as the basis for representations for many of these, for the molecular vibrational pattern, complicated pattern that you might see. And every molecule has a certain number of these, minimum number of vibrations that you need to represent that. So water has 3, carbon dioxide has 4, benzene has 30. A protein molecule would have a large number because it is 3n-6 for a nonlinear molecule and 3n-5 for a linear molecule. And that's basically what it is. So you have 3 modes for a triatomic nonlinear water molecule and 4 modes for a triatomic linear carbon dioxide, for example. How do you do the experiment? Well, I have a source. I send light out. I put it onto the sample. The sample, we will see what it does. It might absorb that light or it may not absorb the light given whatever conditions that exist. And then the detector will see the light. If that molecule has not absorbed any light, the detector will see a higher intensity relative to one where the molecule has absorbed some light. So as I keep changing the frequency of light, some frequencies are absorbed, some frequencies are not absorbed, and therefore the detector will keep telling me what are the frequencies absorbed and what are the frequencies not absorbed. And from that, I can get an information on the vibrational pattern of these molecules. And of course, the same equation, the Beer-Lambert's law that was used for understanding UV visible spectrum can also be used here. Now let's look at the experiment. I have an IR source. I have let's say I have theoretically, it's a thought experiment. I have put one water molecule there and I'm looking at what happens to it. And then I have a detector. Now I know that the symmetric stretch is at 3650, anti-symmetric stretch is at 3750 wave numbers, and bending is at 1600 wave numbers. Of course, I have rounded these numbers. These are not the exact numbers. I have rounded them to the nearest 50 just to make my argument a little easier to make. So what I do is I have this experimental setup. I have a source, I have a sample, I have a detector, I shine light on it. And let us say the light has a frequency 3800 wave numbers. But 3800 wave numbers does not correspond to any of these vibrations. In other words, there is no resonance. If there is no resonance, the molecule is not going to be able to absorb 3800, and therefore the molecule could care less. Light simply goes through the sample and hits the detector, and that is what the detector would see. And the detector would say, well, I'm getting almost 100% of the light you send. The molecule hasn't done anything to it. Therefore, I put a point at 100%. That's a transmission on the y-axis, and on the x-axis, I put wave numbers. I've not labeled it, but that's what it is. The y-axis is transmission, and the x-axis is wave numbers. Then I switch to 3750. The frequency of light, or the wave number of light, is 3750 wave numbers. But 3750 corresponds to the anti-symmetric stage. And therefore, there's an energy transfer because this is a resonance condition. The frequency of the molecule equals the frequency of light. And whenever there's a matching of frequencies, energy exchange can take place. This is what we call as the principle of resonance. Now what happens? I have basically plucked the anti-symmetric vibration. So earlier when I said pluck the vibration, the question would have been, how do I pluck it? Well, I can pluck it this way, by shining light of the right frequency. When I shine light at 3750, which corresponds to the anti-symmetric vibration, the molecule essentially starts to vibrate harder in that particular mode, and it absorbs light. So what does the detector now say? Detector will say, no, look, I'm not getting as much light as I got earlier because the molecule has absorbed light, and therefore the point goes a little lower. It's lower in transmission. Then I change it to 3700 wave numbers. There is no vibrational motion at 3700. Detector gets all the light onto itself. Then I go to 3650. Yeah, 3650 is a symmetric stretch, and therefore again there's a resonance condition that is maintained. And this 3650 wave numbers will now pluck the symmetric stretch, and therefore the molecule will now start to vibrate harder. It is already vibrating, mind you, to begin with. But now what you have done is you selectively excited the symmetric stretch. You have plucked that particular vibration, and then the detector will therefore see a little less light than what it got earlier, and therefore lower percentage transmission. Go to 3600 wave numbers. Back again, because there is no absorption, and I keep going all the way across. I have not shown you all that. But finally, when I come to 1600 wave numbers, again, there's a resonance condition met, because now I'm going to pluck the bending vibration. And when I do that, then of course, that goes right here. And if I were to join all the dots, the spectrum might look something like this. This is what your infrared spectrum really looks. So every time you have a dip, you know that there has been a vibration at that point which absorbed light. And now it is for you to go and figure out what that normal mode corresponding to that absorption really is. That is not so trivial, but today we have good quantum mechanical methods by which you can calculate structures and vibrations and their vibrational frequencies, and use that computational method to be able to make assignments in your infrared spectra. And that is how these things are done. For a diatomic oscillator, we know from the simple harmonic motion system that the frequency is given by 1 over 2 pi root of kappa by mu, where kappa is your force constant and mu is your reduced mass. That's perfectly fine for a diatomic oscillator. So you have a CC system, the vibration is around 1200 wave numbers, double bond is 1650, triple bond is around 2150, and so on. And for every functional group, there is going to be a number associated with that. And these functional groups essentially will operate or will vibrate at about the same frequency, give or take a little, in almost all the molecules. Of course, it can be altered by certain other conditions, but most of the time, for example, if your carbonyl comes at around 1700, it's not going to come at 2800 and something else. It will come around 1700 plus minus, depending on its conjugation with a double bond and conjugation with other groups and so on and so forth. But it will be somewhere around 1700 plus minus, give or take some few tens of wave numbers. Now, how do I remember all this? Well, don't try to remember all this, because if you become an infrared spectroscopist, eventually you'll start using it so often these numbers will just stick in your head. But there's another trick you can always try. You can use as a student. If I know the CC is at 1200, then I know the C single bond O, which is also a single bonded system, diatomic system, a diatomic fragment. So if CC is at 1200, CO cannot be very different. The electronegativities of carbon and oxygen are not terribly different, and therefore you can sort of guess that the CO also should come somewhere around that region, and you will find it is more or less around that region. You can go and check up, you can get at 1030, 1100, depending on the system, but it is not going to be at 1800 or 1900 or 800 or thereabout. So if I know one fragment, I can always take that number and relate it to another fragment which looks something like this. But of course, if it is C double bond O, then it is different. That I have to compare with C double bond C. That is 1650, but C double bond O, I know somewhere around 1700. So you can see the similarities. And why is it similarity? Because the atoms that are involved are atoms with very similar electronegativities, and therefore you will find that the force constant is not very different. Their masses are not very, very different, and therefore the frequencies would turn out to be, give or take, a few between each other. So if you know one, you can guess the other. So if you are caught in an interview where somebody asks you what is the C double bond C frequency and you can't remember, but you know C double bond O is around 1700, just guess any number close to it, and of course you will not be terribly bad. And that is how you decide to relate numbers that you already know. Likewise, C triple bond C is at 2150. I can always guess where C triple bond N, the cyano group, would be, because I know the frequency for C triple bond C. These won't come out to be exact, but you will get into the right ballpark figure. And very often in science, it is not necessary at the first step to get the exact number. You should know where to look for things. You should know how to get into the right ballpark. And that is very, very important in science, to be able to guess when you don't know something. And you have to use your own tricks to be able to make these guesses. And this is one way to do it. And of course, in addition to that, there are isotopic effects, which I can't go into because I only have a few more minutes left. And isotopic effects come in because there's a mu sitting, there's a reduced mass, and that reduced mass changes if I change to an isotope. So if I, instead of H2O, if I take D2O, the reduced masses changes, and therefore the frequencies will change. Of course, for a triatomic system like water and carbon dioxide and so on, the above equation is not the one you should use. There you'll have to start looking at what we call as the FG matrix, the force constant matrix, and the geometry matrix, and so on. Which was given to us by Wilson, and then calculate the normal modes and the frequencies. Now, that is something that, of course, I can't go into here, but keep in mind that the equation that I've given you is only for the diatomic, but for the triatomics and higher polyatomic molecules, you have to look at it in terms of the force constants of all the bonds, their couplings, as well as their geometries. And you use the FG matrix method to be able to arrive at the normal modes and their frequencies. Of course, you'll always see these little charts given to you, charts which tell you where to look for various functional groups. As I said, don't try to memorize them per se, but try to solve as many problems as you can, because then these numbers start to internalize into you, and that is the way to do it. There's no point in sitting and trying to memorize that OH comes around 3500, carbonyl comes around 1700, and so on. But you solve a lot of problems, then these numbers you basically internalize all these numbers. Similarly, OH stretch and the CH stretch. OH stretch comes around 32, 34, 3500, depending on the system. The CH stretch comes around 2900, 3000 again, given the system. So you can see that they all appear as clusters, while the CH and the OH in some ways look similar. And that is how you can start to guess, if you know one, as to what the other would be. These are some typical examples. And you can see the OH stretch is a big, and usually the OH stretches, because of the hydrogen bonding interaction that occur there, tend to be rather broad. Then, of course, you have the CH stretches coming near 2900. Then you have the CH2 bend and the CO single bond O stretch. And therefore, using all this, and once you're sure about their assignments, you can get information. You can simply say that this is a butanol. You might not be in a position to say whether it is, you can say it's an alcohol. You might not be in a position to say, to begin with, that it is butanol, because the differences between the butanols and the pentanols and the hexanols may not be so very different that you could just look at it and say. But at least I can say one thing, that these are alcoholic compounds, and therefore that's a good place to start. And this is, of course, acetone, and you can see the carbonyl very, very predominantly. And then, of course, there is a CH stretch, and that little thing over there is the water impurity that you will always probably have in acetone. And this is your ketone systems. And you can see that there is something happening over here, that in the very low frequency region, there's a big jungle. And these are usually the case with aromatic compounds and large molecules. And we will see a little later that we call them as a fingerprint region, whereas the 1700s and the 3000s and the 1200s and so on all refer to functional groups, and you call them as the functional group region. Now, what are the different types of transitions? If you look at these transitions over here in this acetone, you will see here there's something called the overtone. And these overtones come around 3400, and they can also come at much higher energies because they are twice the frequency of the fundamentals. But as I said, the fundamentals are very strong, and usually you should see the fundamentals. Once you see the fundamentals, you can start looking at overtones. Why do I want to look at the overtones? Because it helps me to get a better understanding of the whole potential surface, and therefore it is essential to look at it. But in the first instance, overtones are not what you're going to be looking at. You first have to solve the problem for the fundamentals. What are fundamentals? They are the vibrations that you will see when the molecule jumps from V equal to 0 level to V equal to 1. If it jumps from V equals 0 to V equals 2, which is not allowed for a harmonic oscillator, but is allowed for an anharmonic oscillator in some ways, that would be the first overtone, and it will be approximately twice the frequency of the fundamental. You can also have the second overtone, where it jumps from V equals 0 to V equals 3, very, very low intensity, and you can have even higher order overtones. All these will show up in much higher frequency regions with very small intensities, and you will need very sensitive techniques to be able to see them. You also have sometimes what is called a hot band, where the molecule jumps from V equals 1 to V equals 2, but for that you must have molecules sitting in V equals 1 in the first place. And the only way I can promote a molecule to V equal to 1 is by heating them. And that is the reason why I say this is a hot band. At very low temperatures, almost all the molecules are sitting in V equal to 0. You will not see a hot band. But if I heat the system, then some molecule will jump into the V equals 1 level given by the Boltzmann distribution. And then I can make a transition from V equals 1 to V equals 2, and then I will see a hot band. Of course, the hot band and the fundamental must have exactly the same frequency in a harmonic situation, but systems are not necessarily harmonic. The hot band generally has a slightly smaller frequency than the fundamental because of the enharmonicity effects. As I said, you can always divide your spectrum into two regions: the functional group region, where you can see the OH, the C double bond O, the C triple bond N, the C triple bond Cs, all functional group effects. And then when you go to the low frequency region, and I showed you in benzene various vibrational modes, and what were you seeing in the low frequency region, where the whole skeleton was distorting itself and doing all sorts of funny things. And that's what we call as the fingerprint region, because while it may not be easy to analyze, it provides one very strong information. Supposing I gave you a molecule, and I said, can you tell me whether this molecule is really this? Supposing I gave you some, let's say a banned substance, some steroid, and I say, can you tell me whether it is this? The best way to do it is to take the known sample of the steroid, record the infrared spectrum, and look in the fingerprint region whether all the bands match exactly. If they match, then you know that this and the other system are the same. You can't use functional group to do that because carbonyl will show up in the same region for many molecules. But the fingerprint region, which consists of basically vibrations, low frequency vibrations, which constitutes wagging mode, the skeletal distortions, and so on, is very unique to each molecule. And therefore, I can use the fingerprint region in a bid to be able to understand them. For example, so here is the benzaldehyde system, and you can see in this fingerprint region, it's pretty crowded, it's pretty like a jungle out there. But there is this jungle, the complexity that helps me to figure out whether what I have been given is really benzaldehyde. Somebody has to mute their mic. Well, you can also see infrared spectra that are shown in the absorbance mode like this. So don't be perturbed by that. Sometimes you see the mode in the transmission and sometimes in the absorption. So I'm going to run quickly. These are all selection rules, where the selection rule tells you that only if the molecule changes its dipole moment during a vibration, you will be able to see that vibration. Because when the dipole moment changes, there's a change in the electrical behavior, and that can interact with the electric field of light. Nitrogen cannot be infrared active, but it can be seen in Raman, which Sukumar would have told you. The molecule need not have a dipole moment, but there must be a change in the dipole moment during vibration, and that is important. CO2 has no dipole, but it is infrared active with respect to its antisymmetric stretch and bend, because these two vibrations change the dipole moment during their stuff. So I will quickly, I think I have only 5 more minutes, right, Margin?
You have 5 minutes more.
Oh, okay. So these are the instrumental aspects. Older systems use dispersive methods, meaning that they do the experiment the way I explained to you earlier. They will go one wavelength after another and see what happens to the system. But today you don't do the experiment that way. You do it by using an interferometer. In interferometer, you shine all the light at the same time, and then you see what the interference pattern is by using what is called a Michelson interferometer. And when you do this, the detector output is something at the top, whatever you see there. It's horrible. There's nothing much you can do with that. It looks like your DRS, the spikes that you see in an ultra edge in a cricket game. But if I do a Fourier transform of that, what I get is at the bottom, the infrared spectrum. So this is the way the experiments are done today using Michelson interferometer. You will never be able to buy an old dispersive machine. Today, all machines that you will buy are only FT machines, and they are very advantageous in terms of sensitivity, throughputs, and so on and so forth, and resolution too. So you can do with liquids, you can do with solids, you can do with gases, and that is how it becomes so powerful that I can have samples in any form, and I would be able to record a spectrum. Of course, if I have a sample that is thick, like a rubber tire, can I do infrared spectroscopy? Well, the light won't go through it, but yes, I can still do it because there is something called an attenuated total deflection. So what I do is I keep the sample on top of a crystal, the light goes to the crystal, and it is totally internally reflected, but a small part of the light will leak out. This is called the evanescent wave, and that will interact with the rubber that is kept on top of it, and the light that comes out will have information about that rubber, and therefore I can use this technique to be able to do it. So I will, here is the experiment. The top is about of a rubber glove, which I have recorded. This is recorded in our lab. So if I want to, if you are buying a rubber glove and you want to know whether it's good quality or the accepted quality, you can record a spectrum like this. You can't do it in transmission mode because light will not go through it, but I can do it in the attenuated total reflection mode, and this is the way it's done. I will skip these two. Before I end, this is the bonding studies. So we know that I skipped the last one. I'll just show you this one. In organic chemistry, we always talk about this d pi to pi star back bonding in metal carbonyls. So you say the ligand gives the electrons to the metal, and the electron gives it back to the carbon monoxide into its anti-bonding orbital. How do I prove that? You prove it because when you do an infrared spectra, record an infrared spectra, you find that while the free carbon monoxide has a frequency at 2143, in all the carbonyls, the frequency is at 1976 or 2000. It is less than what it was in free carbon monoxide, meaning that electron has started populating in pi star orbital, anti-bonding orbital. But the moment you put an electron into an anti-bonding orbital, then you will see that the bond order decreases and the vibrational frequency decreases. So this is a clear proof that back bonding is really occurring in the systems, and that's how you get structural information and bonding information. So I will stop here because the infrared, as I just explained, it's got applications in structural characterization through the functional groups and the fingerprint methodologies. You can understand bonding like what I showed you in the carbonyl case, and you can use it for analytical chemistry like the glove I showed you. You know, whether you want to quantify whether it's good quality glove or the glove that you really ordered for. Because gloves come in very different, you can have neoprene gloves, you can have so many different qualities. You can find out whether it's the right quality sent to you by using attenuated total reflection IR or ATR IR. This is just as a little token of suggestion given to students, since the students who are most of them are looking at it. I just want to tell you about Max Planck, who gave us quantum theory. Planck wanted to do physics, but everybody told him don't do physics because there is nothing much in it. Everything is known in physics. So don't do physics, there's no scope. Because very often you will hear people telling you, don't do this subject, there is no scope. Don't do inorganic, there's no scope. Don't do physical, there is no scope, and so on and so forth. Planck was told, don't do physics, there's no scope. But he still did it because he was interested in it. And you know what happened? He discovered quantum theory, which completely revolutionized physics. So the point to be taken here is, don't listen to experts like us coming and telling you what to do. Just follow your heart and do what you think is what you like to do. And that's how you go on. Thank you very much.
Thank you very much, Professor Vishwanathan. I hope all the participants enjoy this nice talk, and moreover, this will clear the concept regarding the IS spectroscopy to all the participants. Now it's the time to take some quick questions from the participant. Now in the chat box, there are a few questions I'm just reading out.
Yeah, can you just read it for me? Yeah.
Just one second. Will you please explain the little bit of the ab initio first principle with example? Is the one question from the main participant. Explanation of little about the ab initio method for carrying out the structure of the molecule.
It's whoever asked this question has given me a very, very difficult job to do, because in a few minutes it's hard to explain, but I will try to do all that. See, what you essentially do is, in ab initio, what you see when you solve the hydrogen atom, you solve for the wave functions, and you do it in a very rigorous fashion. But supposing I gave you, let us say, the hydrogen molecule, it's hard to do it rigorously. So what you do is you assume that the wave functions of the hydrogen atom or some modifications of that are basically a good basis for your molecule. Make linear combinations of them and try to move the atomic distances back and forth to see where you see a minimum energy. And that is how you start getting your the energetics of the molecule and the structure of the molecule. So basically, you basically are going to be using the variational approach to be able to solving this molecular framework. So you use basis sets, basis functions, which are not really the true functions. They're just starting functions, but then you make linear combinations of them to see whether you can come out finally with as true a systemic representation as possible. And of course, you can get energy information, you can get vibrational frequencies, you can get thermodynamic parameters, all of that. Because once your molecules are known and your wave functions are known, you basically know almost everything about the system. I'm sorry, but it's a one full course really. So this is the.
I'm just taking the one more question and the last one. Chemists come to these values of wave number for first time regarding the OH, CH, and so on.
How do you come across the first time, is it?
First time these values for the OH bond, it is around 3500 centimeter inverse and so on.
Okay. See, there are many ways to do it. As I said, one is to do the calculations and find out where the frequency should appear and then go and see whether in the experiment it appears there. But what you can actually do is to use which is used all the time in infrared spectroscopy. We used to do it all the time. Is to do isotopic effect methods. So let us say I have OH. I take let us say I take methanol. So see, there's a CH stage, there's an OH stage, and the OH stage comes at 3500 or whatever. Then quietly what I do is I take the H and I make it D. So now I have CH3OD. Oh, that 3500 is gone. Because now the OD has a different frequency. It will show up at much lower frequency given by 1 over square root of that mu. So the fact that the 3500 went away when I made OH to OD tells me that what I saw earlier must have been the OH. And the new one that shows up now must be the OD. And that is how I start. So you have to do isotopic effect experiments to get clear or unambiguous assignments of these molecules. So even though you can do calculations, that's not enough. You have to do isotopic experiments. In fact, in all our systems that we studied, if we did experiments with water, we will do experiments with D2O also. If we did experiments with methanol, we will do experiments with CH3OD also. If we did experiments with benzene, we will do an experiment with C6D6. And make sure that the isotopic shifts that we see tells us that our assignments are right.
Okay, thank you, sir. As we are short of time, I just forwarded this question to you and you can respond accordingly to the students.
Sure.
For time again, I'm just saying very, very big thanks to you. Thank you very much, sir.
Yeah, thanks a lot to all of you. Thanks a lot to all the organizers for having me. I have given my email ID at the bottom, which is still on. And therefore, anybody who wants to ask questions or wants to discuss can always call me and send me a mail at that. And I'll be more than happy to help you with address the question that you have. If I know the answer, certainly I will explain that to you as much. Thank you very much.
Thank you very much, sir. Thank you. So now we are just moving ahead towards the next speaker of the day. And next speaker is the Dr. Ravindra Pandey. He is from the IIT Roorkee. He is working as an assistant professor in the Department of Chemistry there. Before that, he is a faculty fellow in the Department of Spectroscopy at IACS Kolkata. He has done the PDF from the University of Texas, and also he has done one more PDF from the Max Planck Institute for Polymer Research. He has done the PhD from the IISc Bangalore during the 2012 and done the MSc at IIT Guwahati. His research expertise involved the charge transfer at organic heterojunction interfaces, protein site interface, and interfacial structure of room temperature ionic liquid. Dr. Pandey received the ASEMDO Indo Professor Fellowship as well as the Ramanathan Fellowship from the DST. With this brief introduction, now I invite the Dr. Pandey, and he will share his views on the molecular perspective on water structure and motion at the surface of climate active ice nucleating protein. So with this, I invite the Dr. Ravindra Pandey.
Thank you, Dr. Mahajan, for the kind introduction. And thank you, Professor Viswanathan, for giving an excellent talk on fundamental of the IR spectroscopy. And if there is a possibility of recording these lectures, if you have that one, I think it will be kind of excellent lecture for the student also. It should be displayed in your department. And with the help of Professor Viswanathan, it had made my life a little bit easy. What I will do that I will talk about how the IR spectroscopy can be coupled with a nonlinear optical technique and can get more information about the system. But before going to that, since this conference is focused for the BSc student also, I decided to give some of the basic fundamental about the spectroscopy. Most of the things are already covered by Professor Viswanathan and other, Professor Kumar gave a talk yesterday, Professor Somansen gave a talk yesterday. So most of the things has been covered, but I will try to summarize it and I will try to give some example that how a simple UV spectroscopy technique can be used to probe and to solve a chemistry problem. So what is spectroscopy? If you look at the any textbook, you will see that one common definition for it, that it is interaction of matter with light. And if we go a little bit about the history of the spectroscopy, in Latin, spectron means ghost. And in Greek, scopy means to see. So when we put light, right, we are not looking at the molecule directly, but we are looking some of its properties which are not visible as such. Depending on the kind of electromagnetic radiation that you use, you use a different kind of spectroscopy for the measurement. For example, if I want to study the rotation of the molecule, what I have to do, I have to study the microwave spectroscopy. If I want to measure the vibration of the molecule, I have to do infrared spectroscopy. Or if I have to measure some electronic property, then I have to measure some UV visible spectroscopy. In fact, yesterday there was one student who was giving a very excellent presentation on the instrument setup of UV spectroscopy. So it's a pretty common technique, but it can solve many different and many challenging problems, which I will try to address in some of my future slides. So in general, when we talk about spectroscopy, it's a general methodology that that is used by different to extract different kind of information: electronic, vibrational, rotational, structure, symmetry of the molecule, and many others. So what is the goal of spectroscopy? The goal is to understand that how the light interact with the matter, and how can one use this property to quantitatively understand our samples. In a simple way, for example, if I have to tell you the time, if I have to ask you what is the time, the tool is watch. If I have to measure the length, the tool is ruler. Similarly, if I want to measure that where the molecule absorb, I have to use spectroscopy as a tool. And then we combine all the information together to get the information and to solve a chemical problem. So what are the immediate questions that we usually address? That what happens when light interacts with a sample, how we produce spectrum, and what exactly the spectrum is a measurement of. To understand these things, first we have to understand that what does a spectrum measure? Usually, when light falls in a sample, it influences the either sample or the input light. So to measure that one, you need two things. One, you need one excitation source, and then you need your detector. So what happens when the light falls in the sample? Either the light intensity gets changed or the sample morphology gets changed. In most of the spectroscopy measurements, we see how is the light before and how is the light after entering with the sample, after interacting with the sample. And by understanding that, we try to understand what actually and how the interaction of the light took place with the sample. So one common example is absorption spectroscopy. And in case of absorption spectroscopy, we measure we allow the electromagnetic radiation to get absorbed either by the atom or by the molecules, which undergoes a transition from a lower energy level to a high energy level that we call it as an excited state. But there is one condition, that absorption will only take place when the radiation matches with the difference of the energy state between the two levels of that molecule. To understand this, I have some molecule in the ground state, which I call as the initial state. You come with a frequency of a light or electromagnetic spectrum, light radiation, and what happens that some of the molecule get absorbed. And the difference of that energy will be that energy of light which will get absorbed is the difference between the initial and final state. And that's a condition we call it resonance. In almost all spectroscopy, this condition has to be masked to see any interaction of light with a matter. Otherwise, you won't see any change in spectra, as Professor Ramanathan explained a few minutes back. And we know that the difference of the energy gap will be h nu. And by using this equation, we can get that what frequency of light is getting absorbed. So in case of simple absorption spectroscopy, what happens that you, as I mentioned before, that you observe the change in intensity of the incident light. You come with the input light, and with this input light, you try to see that how this light has interacted with the sample and how this light has been, after interacting with the sample, how this property has been changed. And the quantity that you measure is usually by transmission, but the transmission can be converted to the absorption or reflectance by by simple mathematical equations. So in actual experimental setup, you have a light source. Then you have a monochromator. This light source gives you different frequency of light. Let's say it gives something from 400 nanometer to 4000, let's say to 800 nanometer if I am in the visible region. Then you have a monochromator. What this monochromator does is that it allows a particular wavelength of light to pass through it. You have a beam splitter, which we call as a 50-50 beam splitter, which means that 50% of light is going in this direction and 50% of light is going in the other direction. In one, you put your reference Q8. For example, if you want to do the measurement in the water, you put in the water here, and in the sample Q8, you put your sample which you have made in the water. So the reason for putting this reference sample is that it accounts for any changes that any light that has been absorbed due to the water, that has to be accounted. Then both the lights goes to the detector, and in one you measure the incident light, in other you measure how the light has been changed, and you get your absorption spectra. We have studied all those things very well in the textbooks. But the question is, this is a very simple technique, and how this technique can be used in a more difficult and more challenging problems. But before going to that, let me tell you that whenever you excite the sample, after some time, the molecule returns back to the ground state. And then that spectroscopy, we called it as an emission spectroscopy. If the excitation takes place if the emission takes place from the singlet states, then it is called fluorescence spectroscopy, which has a time scale of some microseconds. And if it takes place from the triplet state, it is something close to a range of milliseconds, then it is called a phosphorescence spectroscopy. And yesterday, Subhamar has given a very detailed information about how the Raman scattering can also be measured with the excitation. But this is all about the technique. But more importantly, we have to understand that how we can use these technique to measure and to solve a chemical problem, because that is all the goal of all the spectroscopes. So here I have chosen a small molecule. It's a pyridine diamide based molecule, and what has been done, it has been substituted with this kind of group, and this R group here has been substituted with OMe. And what they have done, they have tried to measure the absorption spectra of this molecule. So when they did the experiment at 90 degrees Celsius, which is a little bit at higher temperature, they got the spectra something like this. Then they have not done anything else. In the same solution, what they have done, they have cooled down the solution with a cooling rate of 5 degrees Celsius per minute. And on cooling, eventually the spectra, when it went from 90 degrees Celsius to 10 degrees Celsius, the final spectra was something like this, which means the molecules when you change the temperature, there is some molecular motion in the molecule, and their structure has been changed. And it is labeled as a H here, which means that they are forming H aggregates. So when you take a monomer, and from monomer you make a dimer, and if there is a blue shift takes place, it's called that the H aggregates are forming. All right. Now let's do the same experiment. Instead of 90 degrees Celsius, instead of cooling with the 5 degrees Celsius per minute, let's cool it slowly with 1 degree Celsius per minute. And you can see that the final spectra that when it was cooled with 1 degree Celsius per minute, that spectra is not H aggregate, but it has formed the J aggregates, which means that they are not sitting on one on top of other, but there's a head to tail type kind of arrangement is there. Simply by changing the cooling rate from 5 degrees Celsius to 1 degree Celsius, you can see that the structure of the molecule is changing in the solution. This tells me, and you can see that whatever the fine vibronic structure that I'm getting, that has also, I have lost that effect. Which means that when I'm cooling it fast, I have some kinetically trapped state, which is kind of in the form of H aggregates. But when I am cooling it slowly at 1 degree Celsius, then I'm getting toward a more thermodynamically stable state. In fact, this is a very wonderful example to tell you that depending on the kind of temperature that you choose and depending the rate of cooling that you choose, either you could have some kinetically trapped state, or you could have some thermodynamically stable aggregates. A very simple, from the simple UV visible spectroscopy. Now let me show you one more example. This molecule they have chosen to study the absorbance of the carbon dioxide. So when they have taken the spectra of this molecule, which has been shown with this purple color, right? And when they change the solvent condition from a non-polar to a little bit polar solvent, you can see the spectra has been shifted toward the blue side. This tells me that there is some aggregation taking place, and we all know that if I have to define these aggregate are H aggregate because there is a blue shift in the spectra. All right, but then what they have done, they have added carbon dioxide to that, and this carbon dioxide is kind of attached somewhere here, forming the side group, modify the side group, something like this. And due to the modification of this side group, these aggregates no longer remain stable in the system and they break to the monomer. If that is true, then after the absorption of CO2, then again I should see the shift in my spectrum. This is what I have shown you in my previous slide, where the monomer has formed the aggregates, and because of the aggregation, there is a shift in the spectra. But when the carbon dioxide was added to it, you can see that the spectra has gone back to the monomer kind of structure, which tells me that the aggregation has been dropped. Aggregation has been broken. In fact, they have measured this thing with the emission spectroscopy also, and you can see the spectra of the aggregated system the intensity was very high, and as the CO2 was added, slowly the fluorescent intensity has gone down. This is also telling me that the aggregation is leading to the very strong emission, and the monomer is not emitting at all. Not only this, but the spectroscopy can also be used to determine the band gap of the material. This was the data which was done by one of my colleagues in my department, and they have synthesized the two different kind of molecule. If you look, and they want to use it for different application based on the optoelectronic devices. If you look at the absorption spectra, they look more and less similar, but the same by using the UV visual spectra and by using the TOC plot, in which you plot this in terms of wavelength, and depending on the kind of your band gap material, you plot alpha HV versus as a function of H nu, and then you put a tangent on that system and you get the band gap information of the two systems. You can clearly see the band gap of two material is entirely different, though the absorption spectra look like the same. this kind of experiment, the simple UV visible experiment, again can be used to get a very specific information which was not available by, which can be used by using the UV visible spectroscopy. As I said that when you excite the molecule, they also emit. I have shown you the emission spectra of different peroxide. This is again a very different kind of research groups are working to design different peroxide which has emission in different range, and to quantify that where the emission is coming, what they have done that they have synthesized with chlorine, with bromine, and with iodine, and you can see that by changing this chlorine to iodine, they have get the different shift in the absorption spectra. Not only this, if you remove this cesium with methyl ammonium, then what happens that you can get the emission in the IR range also. And to quantify, one can use the fluorescence spectroscopy in that case. If one has to do more quantitative analysis, for example, here they have systematically changed the X values from 0 to 1.2, and you can see that they can quantitatively measure that how the absorption band is changing, as well as they have also shown that how the emission intensity and emission peak is changing. So though these are the very, very simple and easy technique, but these can be used to quantify where your absorption band is there. And not only this, but also it quantified at where the emission is taking place. So far, whatever the talk we have discussed today, we were mostly focused in the linear region, whether it's IR, whether it's a UV, or whether it's a Raman. We see that how the intensity of light is changing with the applied electric field. But the things become more interesting when instead of linear region, you go to a non-linear region. What does it mean? When you apply a very high electric field with the help of laser light, then what happens? Then the dipole moment which is induced in the molecule not only depend on the linear electric field, but it depends on the higher electric field also, like E square and E cube. And these kind of, for example, if two electric field I'm applying and I'm trying to see that how my system is changing, then it's called a second order nonlinear process. Or if if 3 electric field I'm applying, then it's called third order nonlinear process. So here, since my polarization of the light depend on the single power of the electric field, I'm in the linear response. And when I'm going to a high electric field, I'm in a non-linear response. And this gives me some information which I cannot get by the traditional IR or UV spectroscopy. That is what I'm going to show in the next few slides. So this is the topic of my main presentation today, where I'm going to talk about the molecular perspective on water structure at the surface of the climate ice nucleating protein. Here, one important word is the surface. All these ice nucleating proteins, they sit on the surface of the water molecule, and all the changes take place at the surfaces. So we have to study surfaces and interfaces to understand how these ice nucleating proteins are changing the things. But the question is that why should we focus on surface and interfaces? Not only for ice nucleating protein, but for many different systems also, the surfaces and interfaces plays a very important role. For example, if I talk about catalysis, in case of catalysis, molecule comes and sit on the surface of the catalyst. So if I have to design a very smart catalyst, I have to understand how the molecule is interacting at the interface. Or in a complex biological environment where the interaction takes place at the membrane protein surface. That also takes place in the interface. Or in a modern optoelectronic devices, like just as a thin film electronics, all the separation of the charges, that also takes place at the interface. So we have to understand, if all those things we have to understand, then we need an interface specific molecular level information. But probing interface is a challenge. Few minutes back in the previous presentation, Professor Viswanathan has shown the simple absorption spectra of the water. The absorption spectra of water which he has shown was the gas phase water. If I want to take a spectra of the water, what I have to do, absorption spectra of the water, what I have to do, I will come with the IR light and I will measure the simple absorption spectra of the water. And I know that when I collect this absorption spectra of the water, it will look something like this. And I know that it's broad compared to the gas phase because I have now hydrogen, different kind of hydrogen bonding is playing a role. But if you remember the Professor Viswanathan's spectra, he mentioned that there is a peak should be at 3750 wave numbers, which matches with the gas phase of the water. If I want to measure the interface, right, you can see that there are some OHs which are coming out of the surface, which are not very strongly hydrogen bonded like the bulk molecule. But in this spectra, I cannot see these water molecules. Therefore, I need a technique which can separate the bulk and interface if I want to study, let's say, the interfacial region of the air-water interface. So that's where the some frequency generation spectroscopy comes into the picture. It is more or less, you can say that it is providing a vibrational spectrum at the surface monolayer. In this technique, you come with an IR beam, like the one you are doing in the IR spectroscopy, right? Which excite your vibration level from the, let's say, ground state to the excited state. But then you come with a non-resonant beam, and then you go to a virtual state. And when these two beams comes together at same time and same space, you get a beautiful SFG signal, which means it's a some frequency generation, which is a some frequency of IR plus your visible light that you have added. And the beauty of this technique is that if you go to the bulk, it is forbidden. You don't see any signal. This allows you to study the interfacial property of any system. But the question is that why it is not permitted in the bulk. To understand this, we have to understand little bit basic of nonlinear optics. So when you are measuring your output signal is a function of your two electric field. And all these quantities are kind of, we can say, as vector quantities. And when you go in a bulk, the environment is kind of centrosymmetric, which means the vectors change sign, right? And if I compare now these two equations, I get my output polarization negative sign is equal to the input polarization, but as a positive sign. That is not possible because chi2 is a molecular property, etc. So to satisfy this relation, that is only possible if chi2 is equal to 0, right? And that is why in the bulk, since the chi2 is 0 because the symmetry is the centrosymmetry kind of environment, but at the interface, because you have one side air and the other side you have water, this condition, this is not equal to 0. And therefore, you see a beautiful SFG signal. Now, let me show you the same water spectra which I have shown you a few minutes back. This is the vibration spectra of the bulk water. Now I take the same spectra of that water, but I am focused by beam at this interface. What I get is bonded hydrogen water region, plus I get a one very sharp peak which matches with the gas phase of water, and this peak corresponds to these OHs which is coming out from the surface. This information was not possible to get from the simple IR spectroscopy. And therefore, this nonlinear optical spectroscopy, where there are interaction of the two beams are there, you get some additional information which can be used to get more information about your system and to solve more challenging problems. So now, as I mentioned that I was going to talk about the ice nucleating proteins. So these are one of the example of such proteins is the outer cell membrane wall of Pseudomonas syringe. What they do that when the temperature is not that much high, they are close to freezing temperature, they activate the water molecule in such a way that the water, the freezing point of water, instead of 0 degrees Celsius, it does the freezing at some higher temperature. And by that, the reason of doing that is that so that they can rupture the cell membrane of the plant and can enter and get the food. And because of that, there's a economical loss to the farmers and others. This might you have seen during winters also. During in the small plant, you might have seen a small freezing kind of things on the plant surfaces. But the interesting part is that because they have the ability to make more ice, therefore in the Sochi Olympics, when the temperature was much higher, the organizing committee has injected these bacteria into the atmosphere so that they can get more formation of ice so that they can do the winter games properly. In fact, very recently there are many research papers are coming where people claim that these bacteria, they control the environmental patterns such as rain and the formation of what is that called, snow, and they control the atmospheric patterns. So what is known about ice nucleating protein? These are membrane protein, and the protein has a structure something like this. And if you look at as we know that the proteins are made of the amino acid, and most of these proteins has a repetitive unit as SLTA, and these amino acids such as serine and threonine, they have kind of OH bonding group which forms the hydrogen bond with the water and help in the formation of ice. The way it does, people have done a lot of molecular dynamic calculation and other stuff, and they found that the protein traps the water molecule in such a way that the structure of the ice matches with the basal plane of the ice, and once it provides a kind of a seed, and then the ice water molecule orient on them, and the formation of ice takes place. So if you look at this system, here is my protein and here's my water. So it's a kind of perfect interface. So it's a kind of perfect system to be probed with the help of some frequency generation spectroscopy to probe interface specific submonolayer molecular level information. So now let me show you the spectra of water. And as Professor Ramanathan has mentioned, that if you do an isotopic substitution, then the spectra shifted toward the lower wave numbers, right? So this spectra, you can see that usually the water spectra, which I have shown before, is something 3,400 wave number to 3,700 wave numbers. But this spectra that I'm showing you in the range from 2200 to 3000 wave numbers, and it is because all the measurements were done in D2O. Going from D2O to S2O, nothing much changes. The only thing is that the spectra will be shifted toward the left-hand side. So this is the spectra that I have shown you before. Here is you have the bonded water. Here is the free OHs which is coming out of the surface, which we can see with the help of some frequency generation measurement. And then what we did, that we injected our ice nucleating proteins to it. All right. And when we inject the proteins to it, then what happens that because protein has some charge, and if you look at D2O, O will have some partial negative charge, and D2O, D will have some positive charge. And because of the protein has some charge, there will be the orientation of the water molecule will take place. And once that takes place, since now you have more water or ordered water at the interface, and therefore you observe an increase in the IR intensity, because now the dipole moment are more well aligned compared to the simple water. And you can see the CH stretches also, which is due to the protein backbone, and CH is another thing which are present there. If you add anything to the water, whether it's a protein or some lipid or some charge, you will observe the more ordering of the water molecule at the interface. But that is not what we are interested in. We want to understand that how this ice nucleating protein control the orientation of water molecule at the interface. So this is a kind of lab temperature measurement that we have done. So what we did to understand this process very well, we decreased the temperature from 22 degrees Celsius to 5 degrees Celsius. So going from 15 degrees Celsius, you can see that water is more ordered, water is further more ordered, and at 5 degrees Celsius, it is again there's an increase in the intensity. So this tells me two things. One, the P correspond to here, it correspond to a weakly hydrogen bonded water, and the P correspond here is correspond to a strongly hydrogen bonded water molecule, and the P corresponding here correspond to a weakly hydrogen bonded water molecule. So going from 22 degrees Celsius to 5 degrees Celsius, not only my water is more ordered, but I can see that I have more strongly hydrogen bonded water molecule compared to the weakly hydrogen bonded water molecule, which was kind of same. The intensity was same at the room temperature, but going from room temperature to 5 degrees Celsius, I have more strongly hydrogen bonded water molecule. All right. So this tells me that when you decrease the temperature, your water molecule is more ordered, and that is what is one of the requirements for the formation of the ice. But now the question is that, is it happens only with the ice nucleating protein, or there could be any other source for that, right? So what we did, that we did the measurement with the ice nucleating protein. As I mentioned, that it's a membrane protein. So what we did, that we took a kind of fragment of it, which means that scientists have studied that, okay, this particular part has a kind of activity of it. And when we did with the fragment and we did the same experiment, you can see that we have not observed any changes in the spectra. Similarly, we extracted only the protein part, but once you pull out something from the membrane protein, then it loses its activity, and that is what we have observed, that the intensity is not changing at all, which means that after extracting out the protein from it, then you are not observing that activity, ice nucleating activity of that protein getting lost. Then we did the same experiment with another that is called lysozyme, which is very stable protein. And in that case also, but that we know already that it does not have any ice nucleating property. But in that case also, we have not observed any changes. So the only thing which is left is the membrane. So we make a kind of lipid membrane from that. And there are some small changes, but they are not up to that extent that we observed in the case of ice nucleating protein. So what what we concluded, that going from room temperature from 22 degrees Celsius to 5 degrees Celsius, the water is becoming more ordered. And since we have not observed this phenomena on any other kind of protein, that's why it's an exclusive ice-nucleating protein effect. So whenever the ice formation takes place, then thermodynamically some heat is released, and the heat has to be dissipated into the medium. That's what actually happens if you have more ordering of the water molecule, right? So to understand that part, that where that energy is going, so far you have seen the experiment with a 2 beam. You are coming with a 2 beam, and you want to study that how your water intensity has been changed. But if you want to understand that how this energy is moving in the system, one can do a time resolved measurement. What you do in that one, that you come with an IR pump and you excite some fraction of the molecule. And when you excite some fraction of the molecule, now you have less number of molecule in the ground state, and because of that, your SFG intensity has gone down. But what happens that after some time, this molecule come back to the ground state and your SFG intensity recovers. To understand this could be understood by using this picture. Let's assume that this is your SFG intensity. When you turn on the pump, some of the water molecule are already excited to a high energy state. So there's a drop in the intensity, and then slowly they come back to the ground. They come back to ground state, and this recovers. So this gives you the idea about how the system is relaxing in the system. So we performed this experiment, and what we did, that we excite with some particular frequency in the weakly hydrogen bonded water molecule, and we try to see that how the system behaves. So when we use these ice nucleating protein, we excite here, the signal after some time should come back here again. But instead of coming here, the signal is coming here, which means that these weakly hydrogen bonded water molecule are kind of coupled with a strongly hydrogen bonded molecule, and within no time, the energy is getting transferred very well to the strongly hydrogen bonded water molecule. So to understand this in a little bit better way, we did the measurement with simple D2O, and you can see that in case of D2O, that coupling is not that much strong. So in the case of ice nucleating protein, the energy has been quickly transferred to the strongly hydrogen bonded water molecule, while in case of D2O, that energy has not transferred to the strongly hydrogen bonded water molecule. And that is how there are two ways the ice nucleating protein works. The one is that it orders the water molecule very well, and it efficiently transfer the energy to the strongly hydrogen bonded water molecule. So we try to quantify it. You can always use some kinetic models, and you can get the information. In case of D2O, that transfer take around 800 femtosecond, and in case of ice nucleating protein, it takes something around 100 femtoseconds. All right. So when we excite the water molecule, so this is a pictorial representation that what actually happening in the system. You excite the water molecule, and within no time, the energy has been transferred to the other water molecule. And when the ice nucleating proteins are present there, it does very efficiently. So this is a cartoon character, the cartoon character named Iceman, and it kills its enemies by forming the ice. And I think that it uses these ice nucleating protein to make more efficient ice. So this is one part that I have talked about. This is a kind of fundamental understanding that how water molecules are getting oriented and the dynamics and other things. But it can also be used in the modern devices, right? These are some of the example that I have used and that I have shown here. These are the organic semiconductors, and these are the small molecules which are used in case of organic photovoltaics or organic light emitting diodes. And if you study a little bit of basics of organic molecule-based photovoltaics, when you excite the molecule, it forms the excitons, and these excitons diffuses at the interface. And at interface, the charge separation takes place. But depending on how the molecule are oriented at the interface, the density of state could be entirely different. And therefore, if we have to understand what actually happening, and if we want to improve our device efficiency, we have to understand how molecules are oriented at the interface. So we did some simple studies that we have done the experiment with the CuPC, that is copper phthalocyanine. And if you look at the spectra look broad, something like this. All right. And this is a simple UV visible spectra. In fact, this is the information generally used by all the, what is that called? All the spectroscopists to design the devices. But when we measure the interfacial density of state, remember, this is the bulk. We are talking about the bulk here. But if we go to the interface and we try to collect the spectra in the same way that I have explained you earlier, the spectra is entirely different. Right? And this is the kind of experimental setup which I have shown here. You come with a laser beam and then you fall in a water cell. It generates a beautiful white light. And then you can, the other part act as a non-resonant beam. You come together and you get the spectrum. So you can control the polarization of the light here, and you can get the, as I've shown here, that the interfacial spectra, which I have shown here, is entirely different compared to the bulk spectra which is there. And this has a tremendous potential in designing the devices. How? Because since the interfacial spectra is different, which means that molecule oriented at the interface is completely different. And one can do the polarization experiment and can get the information about how the molecules are oriented at the interface. We did that experiment, and what we found that in our case, the CuPC molecule are sitting perpendicular to the surface. So how that information can be used to get the information about to design the more efficient devices. I've shown this example here. In this example, they have used one organic solar cell, which was based on the peroxides. And what they did, they changed this polythiophenes, which means that they have changed these only systematically. They changed this. First, they did the measurement P3DDT, P3DT, P3OT, and P3ST. The only difference is the alkyl chain, the number of alkyl chains here. And when they did made the device, the efficiency was completely different, from 3% to almost close to 10%. So they tried to figure out the reason that why that is happening, and what they found that they try to figure it out, that why that particular, why the efficiency has been increasing by 3 times. So to that, they have done the UV measurement. But if you look at the UV measurement, which is used to get the band gap information, you can see that they are more and less similar. Then what they did, they performed the SFG experiments, and what they found when they performed the SFG experiment, that the P3DT is sitting something like this, while P3ST is sitting something like this to the surface. If this is my peroxide solar cell, these alkyl chain are sitting something like this to the surface in case of P3DDT, while in case of P3ST, it is sitting perpendicular to the surface. So what they concluded, that when the molecule sits perpendicular to the surface, then this whole transport becomes very efficient compared to when the molecules sit parallel to the surface. And therefore, if looking at this picture, if I ask you that how one has to, if I have to still further improve the efficiency of the device, what I have to do, I have to make this molecule sit perpendicular to the surface, and I will, the efficiency of device will further can be improved. So these are the very small thing that is taking place at the interface, but playing a very important role in designing more efficient and more smart devices. So what I have told you today is that there are specific ice-nucleating bacteria, ice-nucleating protein, which control the molecular structure and energy transfer in the interfacial water. They increase the ordered water at the close to the temperature of freezing, and the freezing transition further facilitated by highly effective removal of the energy from the nucleating site, which means that energy has been transferred from the weakly hydrogen bonded to the strongly hydrogen bonded water molecules. And we can use electronic sum frequency generation to probe the buried organic interfaces, and we can use such kind of information to optimize the efficiency of the devices. So with this, my group at IIT Roorkee is pretty new, and we are working on a different kind of problems like charge transfer at heterojunction interfaces. We want to study that how the charge transfer takes place and how one can control in a step by manner by changing the orientation or the coupling. We can control that one, and we can find it out that in which cases that efficient charge transfer is taking place. We are working on to understand nature's strategy to form the functional material. This is the kind of calcium oxalate crystal which is responsible for the kidney growth. And there's a protein called osteopontin, and this osteopontin, if it interacts with -101 phase in a kidney stone patient people, then it helps in the growth keeps on going on. But in normal human being, this osteopontin prefer to interact with 010. So what are the physiological things that changes that helps to understand the kidney stone formation that we are trying to understand? We are also trying to understand that the aggregation, how the protein aggregation takes place at the interface, that is particularly the membrane interface. And that has a kind of, that will shed some light in the diseases like such as Parkinson and Alzheimer. We are also trying to design more efficient peptides, which can be used for drug carrier. And since all the action of such peptides takes place at the interface, we are trying to understand that how, what are the driving forces which plays a very important role in case of this cell-penetrating peptides. Our group, as I mentioned, that is pretty new, and we are using different spectroscopy tools. And those who are here and MSc students, they are welcome to submit their application to IIT Roorkee, and if they are interested in doing these kind of experiment. With this, I would like to thank you all for listening me for 45 to 50 minutes, and thank you for giving me opportunity to present my work.
Thank you very much, Dr. Pandey. I'm audible?
Yes.
Okay. So now just we proceed towards some quick question.
Yes.
The first of all is that, can some frequency generation experiment compete with the XPS regarding the surface interface study?
Right. So XPS and some frequency generation are entirely different experiments. They are complementary to each other. But in case of XPS, if I have to study the buried interface, right, I have to break my device and then only I can measure it, because it gives the information only from the top surface. But since here I am using the IR light and or the visible light, I can penetrate through my system and I can specially probe my buried interface. So that's the biggest advantage of the proposed technique compared to the XPS. But they are complementary to each other.
So next question is that, in the case of the perovskite UV visible spectroscopy that is shown here, if sample has been affected by humidity, then what would be the change in the spectra there?
Well, usually this is one of the major problem with the peroxide stability, right? Whenever you put the humidity there, they lose their stability. The peroxide lose their stability. So definitely, whatever the kind of efficient emission spectra that you are observing, slowly it will start degrading, and eventually they will disappear. And this is one of the major challenge in the research field to improve their stability, particularly from the humidity. One of the idea that researchers are trying to encapsulate that one, so that no humidity can enter into the system.
So there are a number of other questions that will send to you. You can respond accordingly. So with this, I once again
Martin,
thank you very much.
can I ask a quick question? Martin?
Yes.
One quick question.
Yes,
very
sir,
impressive, very impressive work, Pandey. I was really very interesting, very impressive. Have you thought of using polarization infrared spectroscopy to look at orientations at surfaces? Because
Professor Viswanathan, I got your question very correctly. But since it was mostly focused to other students, so I have not gone into detail of that one. So here the spectra which I have shown you is with the PPP polarization, which means P is your SFG light. The other two P's are your input resonant light and the output. So you can control the, basically you can do the experiment with the 4 different polarization. One is PPP, the other one is SSP, the third one is SPS, and the fourth one is PSP. So by combining all this polarization, whatever the orientation information that I have shown, we have done all the different 4 polarization experiment, and then we get the information about the orientation of the molecule at the interface.
Okay, thank you, Dr. Pandey. So now just we are moving towards the next session regarding the poster. in which the number of the students participants will show their poster here. So now I'm just proceeding towards the organizer, so that's why they can conduct the poster session. Once again, I'm thankful to you.
Thanks, Dr. Aman Mahajan. So here we'll start our first live poster session for the day. Those who are interested may stay back. The scientific talks will resume around 11:50 a.m. So here I invite Abhijit, a final year MSc student at Physics Department GNU. He is also a senior core committee member of CyROX and technical head for committee. So here I request him to host the first live poster session.
Am I audible?
Yes, you're audible.
Good morning, a very good morning to all. I welcome you to the poster session number 1 that will be held just in a few minutes. The poster presentation has been divided into 2 sessions. One will be beginning now only, and the second one will begin at 12:45 p.m. as you had already seen the schedule. Since we had received a large number of participations, we had shortlisted a few of them, and those posters will be presented live and they will be available for the live Q&A session. The judges panel for the poster presentation includes Professor Jaya Murugan Govindaswamy, Scientist E, INST Mohali, Professor Ravi Chand Singh, Professor GND Amritsar, Professor Saptarshi Mukherjee from IISER Bhopal, Professor Tejban Singh Kang, Assistant Professor from Guru Nanak Dev University Amritsar, Professor Palani Natarajan from Punjab University Chandigarh, Professor Subra Singh from Anna University Chennai, and Professor William Yu from United States. I would like to thank all the judges for spending their worthy time and coming here and judging the posters and all. In addition to the poster presentation, we had also organized a demonstration competition. The participants had uploaded their videos on YouTube, and those demonstration videos are available to be judged and seen on the YouTube channel of the NSCoS. So for the demonstrations part, the judges include Professor Prasanjit Kar, Assistant Professor from Guru Nanak Dev University Amritsar, Professor Prabpreet Singh, Guru Nanak Dev University Amritsar, Professor Mandeep Singh, Assistant Professor from Guru Nanak Dev University Amritsar, and Professor Nupur Gupta, Assistant Professor GND College, Pathankot. So wasting no more time, I would like to head on to the poster session. And I would like to invite Dr. Prabpreet Singh from Guru Nanak Dev University Amritsar itself. And his poster title is Fluorescent Imaging of Latent Fingerprints.
Hello, can my voice is audible?
Yes, sir.
So my screens are visible on.
I would like to interrupt for 2 minutes. I'm sorry. The guidelines for the poster presentation will be as follows: that each participant will be given 7 to 8 minutes for presenting the poster, and thereafter there will be a Q&A session for that poster only. The participant will be intimated after he or she crosses the 7 minutes mark, and not sticking to the time schedule may result in disqualification of the poster. And I request you to please stick to the time schedule. Dr. Prab, please.
So, madam, my slides are visible or not?
Abhijit, you have to stop sharing your screen so that Professor, yeah.
Yes. Please present your screen, sir.
Yeah, I have already presented. Are you seeing my screen or not?
No, sir.
Just a minute. So now?
Yes, sir.
Okay, the slides are visible?
Yes, sir.
So, okay, thank you very much for the introduction, and I'm thankful to the organizer for shortlisting this poster for the presentation. So, myself is Dr. Prabpreet Singh from Guru Nanak Dev University, Amritsar. So, I'm a assistant professor there. So, basically, I'm going to discuss about the fluorescent imaging of the latent fingerprints. So as we know that from yesterday, a lot of speakers have already told about the fluorescence phenomena. That is, it is an excited state phenomena where the molecule can lose its energy and they come back to the ground state, and that energy may appear as a radiation So it is like a fluorescence phenomena. So my focus is on the latent fingerprints. So latent means invisible. So means how we can see the fingerprints that is formed on the palm. So it is like a ridges and there are some furrows. So it is most like we have a crest and a trough for the wavelength for a wave. So that is the upper part is called a ridge and the lower part is called the furrows, and that make a some pattern on the palm. So can we use our organic compounds which are fluorescent in nature to see these fingerprints? So for over a century, the identity, one unique identity that is given by the individual to the by the nature is a fingerprint. So nowadays, the fingerprints are being utilized as a marker for many purpose or in many contexts, like to provide the medical facility, uh, to provide the entrance to the machine room, which are of a security concern, or even some criminal and forensic investigation. We can use these type of later fingerprints. So later fingerprints can provide us up to 3 level of information. So the first level of information is a pattern that is being formed by the ridges. So that pattern on the finger may be like a whirl, or it may be like a loop, or maybe it's like a arc that shown here. So that is making a pattern by the ridges. So second level of information includes very minute details that we cannot see by the naked eye. So that includes like we can see the termination of the ridge, we can see such type of a formation of a lake, and we can see the crossover of two ridges. So normally we are using some techniques like a powder dusting method, which the forensic scientists are using to develop the fingerprints, or some methods are there which includes the chemicals like ninhydrins or iodine, but that are toxic in nature. So nowadays, quantum dots, nanoparticles, and some other spectroscopic techniques are available, which can be used for developing the latent fingerprints. But our concern in the lab is how we can use that fluorescent-based derivative for developing the latent fingerprints. So basically, my lab is working on the pi conjugated system, which is called a coronium diamide. So that is a member of the rhyolin diamide family. And we also developed some phenylene diamine based, that is a diphenyl pyrimidine based derivative for developing such type of a fluorescent materials. So first I'm going to see the two molecules. These are a coronium diamides. So that are simply, we synthesize them via Suzuki coupling, and then photochemical cyclization in the sunlight. We got these two, that is a CD3 and CD4, that is a coronium diamides having a hydrophobic region. So why we are using that type of a molecule? Because the basic concept is the sebum rich fingerprints. That is, we have oil glands in our palm, so that releases little bit oil each time. So that oil is a hydrophobic in nature. So if our molecule is a hydrophobic in nature, so they are going to bind that material and they will stick to or adhere to the fingerprints, and then we can visualize our molecule. So that's why we are using such type of a hydrophobic material for developing such type of latent fingerprints. So we have characterized them by using the NMR and other technique. So first we look into the photophysical property, because we need to see that whether they are going to give me fluorescent in the solid state or in the solution state. So you see there is a red fluorescence. So that is always a beneficial, because it is a longer wavelength and it cannot interfere with other light. So you can see we have, when we increase the water fraction up to 70, 80, and 90, so that are giving a very good red fluorescence. So then we check our other molecules. That is, you see this insert figure, that is a solid state red color that we can use for the powder dusting. That means we can directly pour that solid on the fingerprint, and then we can develop the fingerprints. So this is something we have done for the AFM spectroscopy. That is not the concern here, that our molecule is showing some fiber structure, and then slowly they are moving toward the disc-like spherical particles. So my concern is this one. So first we have developed the fingerprints on the aluminum surface. So you can see there is some word is there. So from this we can see the first level of information, and then you can see with the minute details we magnify this image, and we can see such type of a bifurcation of the ridges. There is a ridge ending or ridge termination. So it is an independent ridge. So we have a ridge dot. So this is a formation of a core. So this is all constitute the second level of information which we have developed by using our organic molecules. So then we use different type of a substrate, like we use the steel, glass, metal coin, it's a CD or it's a OHP film. So in all surface, we have seen very beautiful images that can be developed by using our organic molecule. So then we move to our powder dusting method, which forensic science are rapidly using, but due to the use of black carbon and involvement of some other protocols, they usually destroy the sample. So we try to see that can we see in the daylight, that is with the naked eye, or under UV light, that is a fluorescence based. So you can see that we have used different substrate like a porous and non-porous material, which includes the glass, even the ceramic tiles, and then it's a OHP film again, it's a paper, which is a porous material, even the metal coin or stainless steel. So in all the surface we have seen, I can say it's not an excellent fingerprints, but we can have a very good images that can be used for identification. So next other molecule, that is a CDI4, similar, we done the same experiment by using the different types of substrate. We have developed these different fingerprints. You see, it's clearly a world shape is that indicates our first level. So next our target was, can we change the fluorescence? So we synthesize this molecule, and you can see that at the higher concentration of the water, we can see the green color appears. And this is the solid state material that can be used for the powder dusting. So then we go on to develop again the fingerprint by using this type of a green fluorescent imaging. Again, you can see different type of substrate we have used, and we try to identify that the second level information, that is the lake. Again, it's a core material, it is forming the delta, and we have developed different fingerprints on the different fingers. So this is something, I'm going
Please
to
come to the concluding slide.
I'm going to finish. So nitro, again, we developed this type of materials. So one thing that I would like to see, that even we can validate that different subject. So just I will take 30 seconds. So if we have taken the three subject, that is 1, 2, and 3 fingers. So this is showing the loop pattern. This is a whirl pattern, and that's a loop pattern. So it means the whirl can be separated from these two loop patterns. So it means a whirl pattern is a different. So we can validate our subject that this is a different. So now the question is how we can differentiate between these two loop by using our second level of information. So if you see the loop, so it's a lake is there, but you cannot see the lake in the right hand side of the figure. So that is a subject 1, and this is a subject 3. So similarly, ridge dot is absent, but here the ridge dot is present. And then you can see the pattern of the arc. So this pattern is different. So that LFP3, that is a fingerprint from the subject 3. So pattern is different. So it means we can even validate the subject by using our molecule that will help in the forensic science investigation. So in conclusion, we have developed some material based on the pyrimidine and our cornene diamide derivative, and that can be used for developing the latent fingerprints on common household objects. So this is a financial support from the DST, and CSIR is gratefully acknowledged. And for further reference, you can see our papers that we have published in recent year. So thank you very much for your attention.
Thank you for the informative talk, Dr. Prasanjit. Sorry for the disturbance. Now I would like to request our judges, Professor R.C. Singh, Professor Saptarshi, Professor Jaya, Professor Palani, and Professor Subra to please ask the questions related to the poster.
Yeah, can I chip in here? This is Saptarshi Mukherjee from ISA Bhopal.
Yeah, good morning, sir.
Yes, sir.
Good morning, Dr. Singh. Nice work. Just a quick question. This is a fluorescent-based method.
Yeah.
As I can understand, it is you have synthesized a fluorophore and then you have imaged that.
Yeah.
How will it be different from a conventional fluorophore?
So normally, not all fluorophores give the fluorescence in the solid state. So they prefer to have a aggregation caused quenching. That is a ACQ phenomena. But only some fluorophore which prefer to make a AIE, that is a aggregation induced emission. So only that fluorophore can be used for developing such type of fingerprints. Even some organic molecules, due to their hydrophobicity, they easily precipitate out in the water when we increase the water ratio. So then we cannot use that material for developing the fingerprints.
No, my question is much more simple. Suppose you take fluorescein, which is a very standard dye, and dissolve it in, say, any aqueous or non-aqueous solvent, and then you just use it for the imaging, that will give you the similar result.
No, sir. That's I give you reply in the first query that only that fluorophore which will give the fluorescence in the solid state, or when in the water, like 90% or 100%. So normally fluorescein they use, so they have to be, they have to be fluorescent in the solid state, because
any idea about the quantum yield
for this one, for molecule which I have developed? So they have a quantum yield in the range like 0.2 to 0.3, because that have a very strong pi-pi interaction. So naturally they are showing more ACQ feature rather than AIE. Only the DPPS molecule which shows very good AIE phenomena. In that case, we have seen the quantum yield up to 0.6 to 0.7.
Okay, thank you.
Hello.
Hello, Hanji sir.
Prapreet, just one simple question. Have you compared
good morning, Hanji.
Your products with the existing chemicals available?
For the powder testing method, we have used people used carbon black, which is a little bit toxic, because it is maybe like asbestos like material, and that can cause your hazardous in nature. So in that comparison, because even more the background, so if the background is in black in color, so you cannot use your black material. But if you have such type of a fluorescent material like a green or a red in nature or yellow in nature, so we can develop the contrast between the background, and that will give us more benefit for developing the latent fingerprints.
That's good. That's good. I appreciate your work.
Yeah, thank you, sir.
Hello.
Hello.
Yeah, hi, this is Shubhra from Anna University. So I have an layman question. How is the role, of inorganic fluorescent materials in your work? Do they play any role, or if you compare it with them? I mean, I'm sure you have used mainly organic dye molecules here. Is there by any chance, is it possible to have inorganic fluorescent materials for your application?
Yeah, madam, if you see this slide, I have written here that nowadays people are using the quantum dots and even nanoparticles.
So these are inorganic
materials. Inorganic material, madam. Even I have got some paper for reviewing on this later fingerprints. They have used like tellurium. They have used ruthenium metals like this one. And recently we are trying to make our complex, like it's a paper is not being published now, but I'm just rapidly, you can discuss with me. I have make one molecule which can bind with the lead. And when it binds with the lead, it gives the very high fluorescence, and that even stable in the solid state. So now we are planning to use this type of the metal complex for developing the later fingerprints. So let's see that can we get the success or not. So my limitation is up to here. So because I cannot use inorganic material, I'm organic chemist, so I can use this type of the metal complex material for developing the later fingerprints.
Thank you.
Thank you, sir. Thank you, ma'am. Now, I would like to move on to our second participant and request Prapreet sir to please stop the screen sharing.
Just a minute.
Our next participant is Amita Singh from University of Lucknow, and the title is based on some supramolecular polymer, its synthesis, crystallographic, computational, and photoluminescent analysis. So I would like to request Amita Singh to kindly present the screen and present the poster. And I would also like to request the judges to kindly limit their questions to only 1 or 2, because we are already We would run short of time if we ask more and more questions. Thank you. Amita Singh, please.
Okay. Sir, am I audible?
Yes, you're audible.
Will it be possible for you to switch on your videos as well?
Yes, ma'am, I am trying to.
If there is any problem, then you can directly start with your presentation. We have very less time.
We can present the screen from here.
Yes, sir. आपका screen sir show हो रहा है.
Yeah, we can see your screen.
Okay, ma'am. Ma'am, am I visible? My screen is visible, ma'am?
Yes.
Okay, ma'am, can I start?
Yes, please.
Okay, I Amita Singh from Department of Chemistry, University of Lucknow, and my topic of presentation is diaminopyridine mercury-based 1D supramolecular polymer synthesis, crystallographic computation, and its photoluminescence analysis. And the supramolecular polymer are a class of functional materials where building blocks are developed by repetition of monomeric units, which are held together with a directional and reversible secondary interaction. And these interactions encompass intermolecular hydrogen bonding, metal coordination, halogen bonding, and various other sigma hole interactions with high directional properties and reversibilities. So to explore the role of various unusual supramolecular interaction in building of supramolecular polymer, we have investigated a new diaminopyridine mercury-based 1D single crystal supramolecular polymer, and it was obtained by dropwise addition of mercury chloride into 2,6-diaminopyridine, and first it was refluxed and then followed by normal room temperature stirring, and it is a 1D polymerase chain of supramolecular polymer 1, and it is the ORTF diagram which was drawn with the 30% probability level, and to check the polarity of these four-membered ring, the plane was drawn, and the bond angle with 60.94 degree indicates that there was a formation of non-covalent bonding interaction with the mercury center and the chlorine atoms. And it is the crystal data of supramolecular polymer 1 was obtained with the help of molybdenum radiation source, and the electronic absorption spectra of the polymer was recorded in the solution phase. The two major bands were observed. The first band in the region of 640 to 264 nanometer was due to the metal to ligand charge transfer transition, while another band at 360 nanometer was probably due to the aromatic pi to pi star transition. And along with the solution phase electronic absorption spectra, the solution and solid phase photoluminescent spectra of the supramolecular polymer were also recorded to detect the luminescent property of the mercury-based polymer. And in the solution phase, upon excitation at 260 nanometer, intense broad band emission at 356 nanometer was observed in the solution phase, while in the solid phase, a series of multiple bands at 360 nanometer, at 421 nanometer, and at 485 nanometer was observed. And in the solid phase, the formation of the series of multiple bands was due to probably the involvement of non-covalent interaction operating in the solid state, and this may be probably the reason of the red shift of the bands towards the 360 nanometer region. Various kind of non-covalent interactions involved in the solid state structure were also studied. Here, it is the figure which depicts the weak HGH and HgCl hydrogen bonding interaction. The mercury center was the interaction between the hydrogen atom of NH2 group and the mercury center was a long-range weak electrostatic interaction with the 2.692 angstrom bond length, while the intramolecular Cl and H interaction was 2.903 angstrom. Bond length was a weak intramolecular hydrogen bonding interaction. Along with these interaction, a new kind of interaction was mercury and chlorine non-covalent interaction was also observed, and it can be concluded that that was a sodium bond interaction with a covalent bond length of Hg and Cl 2.443 angstrom, and the bond length between the mercury center and the non-covalently bonded chlorine atom was 2.920 angstrom, which was the shorter than their sum of their van der Waals radii, but longer the sum of their covalent radii. And the crystal void calculation was obtained from Hertzfeld analysis, and it is a figure which depicts that the void was generated from crystal radius of 5.0 angstrom, and the data obtained from calculation indicates that the lattice void volume was 31.07 angstrom, and with the void area of 164.90 angstrom, and the globality and asphericity was 0.055 and 0.2 at 5 units, indicates that the void space present in the crystal is very small, and which indicates that there was formation of various kind of non-covalent interactions was involved in the solid state molecular structure of the supramolecular polymer of 1, and it is the crystal from crystal void calculation, and the result was confirmed that the formation of various kind of non-covalent interactions. And I want to acknowledge CSIR for in the form of project and senior research fellowship. Thank you.
Thank you, Amita, for this wonderful talk and post-presentation. Now the poster is open for questions. I would like to request the judges to kindly proceed with the question session.
Amita?
Hello, yes, sir.
Yeah, this is Natarajan from Punjab University.
Okay, sir.
So your talk was quite good.
Okay, sir.
So I want to understand what is the application of this polymer.
Sir, we have synthesized the mercury polymer, and we have tried to study its luminescent properties. As you have seen that in the photoluminescent spectra in the solution and solid phase, the result was not so much appropriate. So, sir, we had targeted to study the various kind of non-covalent interactions. So, sir, then we have sir, I have shown only few pictures of non-covalent interaction beside HgCl interaction, HgH interaction, and HgH interaction. A kind of bifurcated interaction was also observed.
I got your point, but why the mercury? Mercury seems to be quite poisonous, na? Is comparatively toxic than other element.
Yes, sir. Yes, sir. So
why you are interested in mercury?
Sir, actually, sir, we had planned the scheme to study on the luminescent properties of the mercury, but the result are not so much appropriate, sir.
Okay,
During
all right. Yeah.
Okay, sir. Okay, sir. Sir, during the preparation of the supramolecular polymer, while working in the mercury compound, sir, we have adopted sir, precautions.
Are there any other judges, questions from the judges?
Amita, hello.
Yes, ma'am. Yes, ma'am.
Yeah, I have one question. I think one of your slides, you showed red shift in the PL, I think from solid to liquid state or something like that. What happens?
In the solution phase photoluminescence
solution. Okay, so what happens to the relative intensity of the PL spectra compared to solid and liquid? You have shown a shift.
Ma'am, in the solution phase and in the solid phase.
Yes. So yes, what is happening to the intensity in solid compared to liquid?
Ma'am, intensity was same. The intensity range was same, ma'am. There was no, when there was no, ma'am, no shift observed, which gives our satisfactory result.
So you could, I mean, the application was the same. There was no problem with intensity.
No, ma'am. Intensity was same.
Okay. Okay. Thank you.
Thank you very much, ma'am.
Any more questions? I guess there are no more questions for this poster. So I would like to request Amita to stop her screen sharing.
Okay. Thank you very much.
Thank you, Amita. Now I would like to proceed to the next, the poster number 7. That is from Deepika Sardana. She's from Jawaharlal Nehru University, New Delhi, and the poster title will be Origin of Slow Solvation Dynamics in DNA, DAPI in Minor Groove of Dickerson-Drew DNA. You may proceed, Deepika. Thank you.
Hi, good morning. Are my slides visible?
Yes,
they're visible.
Okay, very good morning, everyone. My name is Deepika, and I'm pursuing my PhD from Jawaharlal Nehru University. The question that I'm trying to address through this poster is, what is the origin of slow solvation dynamics in DNA? So historically, it was considered that certain biomolecular structures, they only perform the biological function, whereas the water remains as a passive matrix. But now it's very well known that it's not the case. Water molecules are not mere spectators, and they are really important. They are very crucial for any biomolecular structure to perform its function. Now, experiments on this time-resolved fluorescence Stokes shifts probed by fluorescent probes has shown that such kind of dynamics varies from few picoseconds to nanoseconds, but the origin of such a dispersed dynamics is not clearly understood. Why? Because of the complex electrostatic interaction between the large ionic DNA and the surrounding water molecules and ions. So what we have done here, we have taken a minor groove binder, DAPI, which goes and binds to the minor groove of this well-known Dickerson DNA sequence. And we confirm the binding through CD spectrum, where we see upon binding, this achiral ligand shows the induced CD spectrum around 350 nanometer, and the fluorescence quantum yield changes drastically once this molecule binds to the DNA. And we measure the binding constant, which is very high, that is of the order of 10⁸. And in fact, this rotational anisotropy constant of 0.35 nanoseconds shows that once this molecule binds to DNA, the whole complex rotates with single rotation constant. So now we know that DAPI binds to this minor groove, but how to measure the dynamics? It's impossible using one single experimental technique to measure this broad time range. So what we have done, we have collected wavelength-dependent decays using two time-resolved fluorescence techniques. One is fluorescence upconversion and time-correlated single photon counting, from where we construct the time-resolved emission spectrum to calculate the absolute Stokes shift. Now, if I had only water, or you can say pure water, my dynamics would have finished within 2 picoseconds. Whereas here we can see the dynamics continues till nanosecond. But why does that happen? To find out, what we have done using the same minor groove binder DAPI and the same DNA sequence, we have carried out microsecond long MD simulation, where post-running simulation, what we calculate is the interaction of this probe with all the atoms of my system using this equation, which is nothing but Q1 Q2 by R with some complementary error function. So what I get is the electrostatic fluctuations, electrostatic energy fluctuations of this total. This is black is representing the total electrostatic energy fluctuations, whereas green representing the fluctuations of DNA, blue representing the electrostatic fluctuations of water, red representing the sodium plus ion, and chloride is represented in violet. So we get this solvation response through this electrostatic interaction energy calculations. And then what we do, we directly compare our experimental simulation results by calculating the solvation correlation function. Now what we see is beyond 2 picosecond, the dynamics measured from these simulations is capturing the dynamics that we have seen in the experiment, but still the origin is not known. So to address or to find out this origin, what we did, so if you carefully look at these fluctuations, what you see, there is a large anti-correlation between the DNA and water and ions and water. And if you calculate the correlation function, what you see is that the water, which is represented in blue, contributes to the overall dynamics, including the effect beyond 5 picosecond. And sodium plus ions contribute to a much lesser extent. And this DNA, the time correlation function of DNA couples with water to give rise to this total correlation function. But is that really so, or is it really water, or is it DNA? To get the clear answer, what we did is what we cannot do in the experiment. What we did, we froze down the DNA fluctuations. Is the animation clear, visible?
Yes, they are.
So, okay. So what we do is we freeze down the DNA. All the atoms are fluctuating. So there is no fluctuations from DNA. You can see green is almost zero. But what you see here is that once you freeze down the DNA fluctuation, the long-term dynamics is completely suppressed, and the time correlation function of DNA and the ion become faster. But is it really the water or is it really DNA? To exactly find out the answer, what we did next is we froze down the water. And what we see is that the dynamics completely eliminates. There is no, in one single snapshot of 100 femtoseconds, the dynamics finishes. So this means that water fluctuations are really important for any biomolecular structure to perform its function. So to conclude, this fluctuations or this origin of slow dynamics lies in the fluctuations of DNA, which controls the nearby water and ions to give rise to this collective solvation dynamics. But you may ask, what is the physical significance of such dynamics? Now, in case of DNA mismatches or DNA mutations, which are cause of more than 30 to 40% cancer, these fluctuations, these coupling of water and DNA motion is what that gives signals or mismatch specific signatures to the repair enzymes to come and repair them. And I'm happy to share that this work has been published as a cover page. And with that, I would like to thank the organizers for giving me this opportunity and my supervisor, Dr. Shobhan Singh, and all my lab members. Thank you.
Okay, Deepika,
Yes, sir.
Saptarshi here.
Good morning, sir.
Morning. Very nice work.
Thank you, sir.
Just a few, couple of questions. Number one, you said that the binding constant is of the order of 10 to the power of 8.
Yes, sir.
How did you determine that?
So we determined this using simple fluorescence, steady-state fluorescent titrations.
Why not ITC?
We could have done ITC as well, but with ITC we were not able to get this sensitive value of binding constant. We were getting always lesser somehow.
Yeah, that is my question. Why is the difference between ITC result and your fluorescent result?
Because in the range of because the sensitivity of the instrument that we have used is able to has helped us to perform this experiment in the nanomolar range, whereas we could not do this same experiment in the ITC with the nanomolar concentration. We would need a micromolar concentration to perform the experiment.
Okay, just a last question. Go to your, there was one CT. The correlation function was less than 0. It is going below 0. Go next. Yeah, this one.
Here.
No, the previous slide.
Yes.
If you look at the correlation function, it is going less than 0. Why?
Yes, because the total or the overall response of the correlation function is governed by the coupling. So if my time correlation function of DNA is going up, at the same time the time correlation function of water is going down to compensate for the overall dynamics.
Okay, thank you.
Thank you, sir.
Any more questions? I guess there are no more questions from the judges. So I thank Ms. Deepika for
Thank
this
you.
wonderful poster presentation, and I would like to request you to stop the screen share. Next participant is Hira S. The title of the poster is Enhanced Optical Activity in Naphthalocyanine Dope Silver Nanocolloids. I would like to request Mr. Hira to kindly present their screen.
Abhijit, I don't see him in the audience right now, but he was there. I think there was some network issue with his part because I saw him earlier. Maybe we can have the other next participant.
Okay, sure. Okay. The next participant we have with us is Navleen Kaur from Guru Nanak Dev University itself. The title of the poster is Impact of Cationic Head Group in Cytotoxicity of Ionic Liquids, probing changes in phospholipid bilayer architecture using fluorescence and solid-state NMR spectroscopy.
Hello,
Yes,
is my screen visible?
yes, it's visible. Please go ahead.
Okay, thank you.
Okay.
Myself Navleen Kaur. I am working as PhD scholar in Guru Nanak Dev University, Amritsar. Today I shall give the presentation on the topic which highlights my work, impact of cationic head group in cytotoxicity of ionic liquids, probing changes in bilayer architecture using fluorescence and solid-state NMR spectroscopy. To begin, I shall introduce ionic liquids, which are the organic salts with melting point generally below 100 degrees Celsius. These can be prepared by using combinations of variety of cations with varying cationic head groups and alkyl chain lengths and variety of anions. Due to these different designs of ionic liquids, they possess various physicochemical properties. These tunable physicochemical properties make ionic liquids to be capable of to be used in various applications. And due to these increasing applications of ionic liquids, it becomes quite important that we understand their ecotoxicological impact. So here are some of the literature reports which have already shown that ionic liquids are quite toxic in nature and they are not as green which they were once considered to be. Both in vivo and in vitro studies can be performed with the ionic liquids. So the cell membranes, which are the first targets of ionic liquids, when the ionic liquids interact with the cell, we are mimicking the cell membranes with the phospholipid vesicles. The phospholipids POPC are the major constituents of the cell membranes in the mammalian cells. So these form the vesicles in the aqueous solution. We are working with the large unilamellar vesicle, and the Bartlett assay is performed to determine the concentration of these phospholipids in these vesicles. This is a UV visible spectrophotometric based method. These are some of the techniques which can be used to determine the interaction of ionic liquids with the liposomes, and also the studies can be performed with the live cells which can be microbial or mammalian. The objective of our study is to synthesize the ionic liquids with different cationic head groups and to study their cytotoxicity on HeLa cells using MTT assay. Then to further gain the structural insights into the ionic liquid and membrane interaction, solid-state NMR spectroscopy was performed, which was correlated to the cytotoxic effects of ionic liquids with their disrupting behavior towards the POPC vesicles. Finally, the aim is to develop a structural property model which detailing the interaction of ionic liquids with the lipid membranes, which will be capable of predicting the biological activity of ionic liquids. This is the synthetic scheme of ionic liquids where we have synthesized with, ionic liquids with different cationic head groups and the same dodecyl alkyl chain and same anion, the bromide anion. This is the solution state NMR spectra for all the ionic liquids which we will be studying to characterize and to see the purity of synthesized ionic liquids. This is a schematic representation of interaction of ionic liquid with the POPC LUVs, which is encapsulating the calcium dye within its hydrophilic core. When the ionic liquid permeates into these vesicles, the dye leaks out and the fluorescence is enhanced. Also, the binding can be determined by using the zeta potential measurements. This is a result of a study, the MTT assay, which was performed on the HeLa cells to determine the number of viable cells after the addition of ionic liquids. The EC50 was determined where half of the cells were killed on addition of these ionic liquids, and it was found that piperidinium, benzimidazolium, and imidazolium had the least EC50 values and were the most toxic, and morpholinium was the least toxic among all the studied ionic liquids. Then the dye leakage assay was performed on the LUVs where 2.2 millimolar of ionic liquids were added to the POPC LUVs, and it was found that benz was most permeabilizing. However, ammonium and morpholinium were least permeabilizing. When the ionic liquid concentration was increased, it was found that the permeability of benzimidazolium decreased with the increasing concentration, but for all the other ionic liquids, the permeability increased with the increasing concentration. Same was the effect seen in the zeta potential measurements, where the positive potential development increased with increasing concentration for all the ionic liquids, but for benzimidazolium, the positive potential decreased. This might be due to the fusion of the LUVs when higher concentration of benzimidazolium was added to the POPC LUVs. The DLS measurements showed that the size of the POPC LUVs remain intact even after addition of 1 millimolar of ionic liquids. Solid state 1H magic angle spinning NMR spectra of POPC and on the addition of ionic liquids is shown here. This was performed to see the location of ionic liquids within the POPC lipid bilayers. The cross-relaxation rates were determined from the 1H NOESY NMR spectra, and it was found that the hydrophobic dodecyl chain was buried deep into the hydrophobic core of this lipid bilayer, while the cationic head group stayed in the lipid-water interface. Then to see the interaction of the ionic liquid with the head group of these phospholipids, 31P NMR was performed, and to see the effect of this chain on the order parameter of these lipid chains, 2H NMR spectra were recorded. These line shapes of 31P NMR spectra are the characteristic of the lipid bilayer. These are the parameters, order parameters. Order parameter was reduced on addition of all the ionic liquids, and the spin lattice relaxation when plotted against the squared order parameter, the curvature shows that the elasticity or the softness of these lipid bilayer increased on the addition of ionic liquids. 31P CSA, that is the chemical shift anisotropy. CNA, this gives the ellipsoid ratio. This gives the degree of orientation of the head group, and this gives the CSA of the phosphorus group. And it was found that the benzimidazolium, imidazolium, and ammonium ionic liquids were affecting the most the head group of these lipids, but the order parameter was affected the most in the case of benzimidazolium and piperidinium, which can be seen in this image. So finally concluding, the cytotoxic effects of ionic liquids on HeLa cells can be correlated with their destructive behavior towards the model lipid membranes, which are composed of POPC phospholipids in our work, and the structure of cationic head groups, their size, aromaticity, hydrophobicity, and number of heteroatoms. They all play a major role in dictating the cytotoxicity and physical properties of the ionic liquids. Finally, acknowledging my supervisor, Dr. Venus Singh Mittu, for all his support and guidance, our collaborators from Germany who performed the solid state NMR studies, UGC for fellowship, GNDU for infrastructure, and my lab mates. This is my publication, and thank you.
Thanks a lot.
Thank you.
It's now open for questions. I would like to request judges to please go ahead with the Q&A section. Professor.
Yeah, Navleen.
Yes, sir.
Excellent work. I'm very happy to see this work.
Thank you, sir.
What is HeLa?
HeLa cells are the cancerous cells. They from the human body. They are mammalian cells.
No, no, okay, but what is HeLa? H-E-L-A.
That is on the name of the lady from which the cells were
What is the name?
Henrietta. I don't actually remember Henrietta.
Henrietta Lacks.
Yes.
Okay. Why
That
did you
was on.
study? Yeah. Okay, that is fine. Just the last question. Why did you study only HeLa and not any other cancer cell?
This time we have studied with the for the mammalian cells we have studied with the HeLa cells only, but further we are increasing our studies towards the microbial cells, but yes, no other mammalian cells we have studied so far.
Try others. Okay. Okay.
Okay, sir. Thank you.
Any other questions? Okay, I guess the question Q&A is over for Navleen. So I thank you, Navleen, for this wonderful poster presentation. I would like to move to the next poster.
Yes.
That is from Arshdeep from Guru Nanak Dev University, Amritsar. The title of the poster is Detection of Phenolic Compounds in Wine.
Abhijit, she has sent a pre-recorded video.
Yes, ma'am.
So I'm going to share my screen, and because she lives in a place where there's not good connectivity of the internet, so she has sent a pre-recorded video. I'm sharing that, but she's present in the audience so that if judges have any questions from her, they can interact with her.
Yes, ma'am.
Yeah.
A very good afternoon to all of you. Today I'm here to present poster on the behalf of our team, which includes Priyal Sharma, Jasmine Gupta, Namika Mehta and me. So I am Arshdeep Kaur, a student of Guru Nanak Dev University, and topic of my poster presentation is the detection of phenolic compounds in the wine. Phenolic compounds are very important in the wine because they have many properties like antioxidant, anti-diabetic and anti-cancer properties, and also they determine the quality of the wine. There are many phenolic compounds which is present in the wine, which are further divided into the various subclasses. As we can see, there are many methods to determine the phenolic content in the wine, but we focus on the UV visible spectroscopy method because almost all the phenolic compounds, whether anthocyanin, tannins, flavonols, contain at least one benzene ring in which pi electrons undergo pi to pi star transition, and they also contain some non-bonding electrons which undergo n to pi star transition using UV visible light. So basically UV visible spectroscopy is a molecular spectroscopy and a region in the spectrum from 200 to 800 nanometer which is absorbed by the molecule and result in the excitations from the ground state to excited state of the electrons. So as we can see, 4 type of transitions are allowed type, that is pi to pi star transition, n to pi star transition, sigma to sigma star and n to sigma star transition. And according to selection rules that the symmetry of the orbital should remain same in the ground state and the excited state, n to pi star and n to sigma star are forbidden type of transitions. So here we can see absorbance peak of the various phenolic compounds present in the wine, and all of them show a characteristic peak at the 280 nanometer, which is due to pi to pi star transition. Let us consider an example of UV spectra of the melvedin thioglucoside, which show an extra peak at around 531 nanometer because of presence of suitable oxochrome, which make it an chromophore, and it will absorb the light in the visible region, that is green color, and give us a complementary color of the wine, that is red color wine. So during fermentation, different phenolic compounds are present in the different parts of the grapes, that is skin, seed and the flesh, which are converted into the grape juice. So here is the UV visible spectrum of the red wine grape juice during first 15 days of the fermentation at the peak at 280 nanometer, which is a characteristic peak of the phenolic compound, and the peak at 320 nanometer, which is the peak of hydroxycinnamic acid, and the peak at 520 nanometer, which is due to anthocyanin, show a hyperchromic shift, that is increase in the absorption intensity due to presence of the different phenolic compounds at the different stages in the grape juice. So spectroscopy can be used to determine phenolic compounds during any new wine formation. During fermentation process, different skin contact period result in variable content and composition of the phenolic compounds in the wine. So basically two type of wine, red and the white wine. And the main difference between them is their skin contact period and also the peak at 520 nanometer, which is due to anthocyanin, which is clearly seen in the red wine and almost lack in the white wine due to less amount of anthocyanin in the white wine. Cyanidine, which is a type of anthocyanin at a low pH that is less than 4 is red in color, and at high pH that is more than 7 is blue in color. Because cyanidine at a low pH show a low conjugation, so we require high energy to excite it from low energy level to high energy level. So it will absorb wavelength of it will absorb light of less wavelength and transmit the light of high wavelength, that is red light. So anthocyanin as a pH indicator show a hyperchromic shift at a low pH that is less than 4 and show a hypochromic shift at a high pH that is more than 7. So color of wine can be determined by these three terms, that is intensity, tone on chromaticity, brightness or purity, which can be further measured by using these two methods. First method is Scilab space method, which use three chromatic coordinates, that is X, Y, and Z, to determine the chromatic characteristics of the wine. If A star greater than 0, wine is red in color. If less than 0, wine is green in color. Similarly, we can use L star and B star coordinates to find the different colors of the wine. In Sodreth method, we measure the absorption spectrum using double beam spectrophotometer, and the absorbance values are measured using the Beer-Lambert law, according to which absorbance is equal to epsilon LC. Epsilon is equal to molar absorptivity. L stands for length, that is 1 centimeter, and C stands for the concentration. And these absorbance values are used in the formula to measure intensity and the tone respectively. But nowadays there is a modification in the measurement of the intensity by the formula, and intensity is measured as the sum of the absorbance at 420 nanometer, 520 nanometer plus 620 nanometer. And spectroscopy can be used to tell us the chemical age of the wine. Red wine changes from lead and to orange color, so peak at 520 nanometer decreases. Similarly, white wine darkens from white to golden yellow color, so peak at 420 nanometer will increase. So the change in the color with the chemical age due to the transition of the monomeric anthocyanin and tannins into their polymeric form. So as we know that phenolic compounds are very important in the wine, so their quantification is also important and can be done by using Follen-Cisaltio method. Follen-Cisaltio reagent react with many reagents in the method, and upon reduction, it will generate a blue colored complex that is chromogene, which is absorbed strongly at the 740 nanometer and can be measured by using spectrophotometer. So here gallic acid used as a standard because gallic acid is almost present in all the phenolic compounds, and the calibration curve of the gallic acid can be constructed by this method at 740 nanometer. Similarly, we can construct the calibration curve of the various sample of the wine we are given by using lambda PDA UV spectrophotometer, and it is observed that red wine always contain more phenolic content as compared to white wine. So as we have already studied that tannin polymerizes with age, so their content in the wine decreases, so that make the wine less astringent. So we in the poster tell us about the various benefits of the wine and also the methods of the phenolic compounds, but it is not but we don't tell that to consume wine daily. It should be taken if prescribed by the doctor, but if it is excessively taken, ethanol in our body can convert into acetaldehyde and congeners, and according to the study, congeners are harmful for our body. So at last, I would like to thank judges and also the audience.
I would like to request judges to please go ahead with the questions.
Good morning, everyone.
Hello.
Yes, sir.
So I want you to comment on the selectivity and sensitivity of your detection method. You know, you'll have different polyphenols in wine.
Yes, ma'am.
Can you tell me something about the selectivity, how good or bad it is compared to other methods?
Ma'am, basically in the wine method, we focus on the anthocyanin, which is responsible for almost all the properties of the wine, like color, and also focus on tannin, which is responsible for its taste, bitterness, and all.
Your
So there are
method
also some limitations in the method, like Sodrat method. Firstly, the absorbance is measured at 420 nanometer plus 520 nanometer, but later on a modification is done by Glorious method.
So the selectivity and sensitivity is quite comparable to pre-existing methods. The different methods
Excuse
you
me,
have
ma'am,
shown already.
please repeat the question.
What about the selectivity and sensitivity of your method as compared to other? You have shown in the first slide itself the different methods of detection, isn't it?
Yes, ma'am, because in the UV spectroscopy, mainly it is for electronic energy level transitions, and we focus on the phenolic compounds in the wine. And in phenolic compounds, mainly pi to pi star and n to pi star transitions, and the other methods like chromatographic method, or we can say that mass spectrometry methods. So they require high instrumentations and also expensive methods. So we mainly focus on the UV spectroscopy method.
Okay, thank you.
Actually, very nice work, Saptarshi here. Just a very quick question. What was the control of your experiment?
Sir, repeat the question, please.
What was the control of your experiment? Do you understand the control?
Yes, sir, mainly, but...
Huh?
Yes, sir.
Yeah, tell me, what did you use any control?
Sir. No, sir.
No, my question is, let me rephrase it. Perhaps you have done it instead of wine. Did you
yes, sir,
use any other solvent or any other mixture, any other liquid?
No, sir, we haven't used any other liquid.
Okay, okay, fair enough. Thank you.
Thank you, sir.
Okay. Asif, this is Natarajan.
Good morning, sir.
Good morning. So this work you have done, or is it just only literature survey?
Sir, being an undergraduate student of the university, it's
that
not
point
possible.
I want, some other referee I want to inform this one. These are the undergraduate students who have been compiled this
Yes, sir.
Yeah, that you should have clearly mentioned.
Sorry, sir, I would like to apologize firstly for the inconvenience that I have to send a pre-recorded video.
Yeah, because the other judge also asking selectivity, sensitive and all. This, I hope naturally you will not be knowing the bachelor students, and also the another teacher was asking about what kind of standard. Naturally, I hope you will be not knowing such details. Okay?
So it's just a literature work because I hadn't
So
performed
fantastic.
any
I think fantastic.
experimental.
The topic you have done with the fantastic topic. So I enjoyed by
Thank
seeing
you, sir.
Yeah, enjoyed by seeing your talk. Good. Best of luck.
Yeah, very nice.
Thank you, sir.
For judges, I would like to quickly point out that this is poster number 13 and not 9. 9 had some issues, so she is going to present in the next session. Now we can go ahead with our scientific talks. I think the next speaker and the chairperson is already here. So Professor Raman Mahajan, I would request you to introduce our next speaker. Thank you, sir.
Okay, thank you, Dr. Bindia. So now just we are moving towards the next talk of the first session. The speaker in this talk is the Professor Sudipta Mathi. He is from the TFR. Here he is the fellow, Department of Chemical Sciences. He served as assistant professor, Department of Physics, IIT Kanpur. He also done the PDF from the Cornell University. And moreover, he has done the PhD in the biophysics from the University of the Pennsylvania. He has done the MSc Physics from the IIT Kanpur. He is a recipient of the Wellcome Trust Senior Overseas Research Fellowship in Biomedical Sciences. He has been awarded with the Excellence in Teaching from University of the Rochester. His research area are protein interaction, protein misfolding, and neuronal interaction, cutting edge instrument and modifying commercial ones to suit the experimental requirements. The journal of high repute. With this brief introduction, I invite the Professor Sudipta. Now he will share his views on the membrane is the place of action. So, Professor Sudipta, please.
Thank you very much. Can you all hear me? Can somebody tell me that everything is fine? You can see me and hear me?
Yes, sir.
Okay, good. And thank you very much, Professor Mahajan.
Hello.
Yeah, can you hear me? Yeah.
Yes, sir, we can hear you. I think there are some issues with Dr. Mahajan's audios, but everyone can hear you and your slides are visible.
Excellent. Thank you very much. And thank you very much, Professor Mahajan. And that made me feel young, because you probably were reading from some CV which must be 20 years old. That fellow thing reminded me. But that really feels good. And what I'll talk to you guys today is about this little boundary of a cell. Okay, so the whole thing that you see here is the cell, and it has many organelles, the nucleus, many things. This thing, if you could see a cell under a microscope, that would be roughly 20 microns wide. And within that, the boundary of that, which we call the cell membrane, is about 4 to 5 nanometers thick. So it looks like just the boundary of the balloon, and not so significant, because together with all the membranes in the cell, it occupies about 1% of the volume. So probably a negligible thing, but it is not. And that's the story today. Okay, so let's just go forward. Before I go to the membrane and the story, two things at you. I think Skyrox rocks, and it's fantastic that the students have a conference organized on spectroscopy. Thank you very much for inviting me here. And the second thing I need to do is my own students, and they work on very different things, only a little bit of which I'll be able to talk about today. So I'll quickly go through and tell you what are the different things that we do in the lab. That may be of interest to you, mostly who are, I think, undergraduate students. So you should know what are the different things going on in different places. So the questions I have divided into a few parts. So we are a biophysics team. And that's a very convenient term, because under biophysics, I can put in pretty much anything that I want. Anything that has a hint of biology and a hint of physics, a hint of physical chemistry is all biophysics. In fact, chemistry, any part of chemistry that has to do with biology, I can sort of conjure up biophysics. So it's a term that is reasonably vague, but it's also something that actually encompasses many areas. And you'll see this in my talk, how the abilities of a physicist for building equipment, thinking about modeling and analysis, to the abilities of a chemist, who are the physical chemist, knows about preparing solutions, preparing materials such as proteins, knowing about spectroscopy, to that of a biologist, which is cell culture, etc. They're all required to answer some of the questions. And almost all of my students here would be, if not masters of all those, at least jack of all those trades. So there are some examples of things that we work on, the questions they're very interested in. And each of these questions we are very passionate about. In TIFR, we don't do anything for thinking about extraneous factors. We love these things. We come in even Sunday mornings just to ask, okay, today what do I see? So, some things that you will hear me talk about is protein aggregation that Professor Mahajan said that I'm interested in. I was interested in about even 17 years ago. I'm still interested in work. A part of my lab works on that. And that has to do with combining techniques. And here is something that where we found the structure of some of the things that cause Alzheimer's disease. This and that, and this is Alzheimer's, the disease causing peptide in membranes. I'll talk about this, so I will not say anything here. There is another area where we'll actually look at brain cells. Okay, and of course, these are brain cells from the rat. I can take your neurons out. So these are rat neurons, and some part of the lab works on rat neurons and looking at how these peptides interact with rat neurons and asking other questions, such as neurotransmitters. Neurotransmitters are the messenger molecules. As you and I are talking and you are looking at me, the little neurons firing out neurotransmitter bullets to the next neurons, and they're catching it, and the message is being passed on so that you actually perceive what you're seeing and perceive what I'm talking about. So we have developed a lot of tools and we have a lot of interest in knowing how this process works. It's ultimately a chemical process. It's really at the boundary between chemistry and biology that little molecules actually carry information and finally perception happens. And we have done a lot of work on visualizing this process. This is a little bit about also instrument building. We know and we are passionate about building instruments. Some things that we build are actually have been commercialized by Indian companies who have indigenized all our designs. And you can look at a single molecule spectrometer that's fully built in India, at least assembled in India. Some parts are built and some parts are imported, but the instrument is built in India and you can buy it. This is some other thing that we are also interested in. And this is our newest interest. Interaction between neurotransmitters, which I just talked about here. But when I talk about that here, is the neurotransmitters carrying messages to another receptor molecule. When I talk about it here, we have taken out the receptor molecules from the equation. We still see an effect. And the question is, why do you see an effect? And if I get time, I'll come to that a little bit. I hopefully get time because I haven't put too many slides together. I want to go slow. And if any of you have a pressing question, please unmute yourself or at least request the chair's permission to unmute yourself and ask it. And I'm more interested in conveying meaning and the excitement rather than telling you some complete story from A to Z. Okay, so let's come back to our story today. There is a cell that I talked to you about. And this is the membrane that I talked to you about. There are other cells, other membranes inside the cell, which are also relevant, but today I will concentrate on this outer membrane. Okay, this is really the boundary between the living chemistry and the non-living chemistry. Okay, the way the evolution happened is because to have something living, you have an out of thermodynamic equilibrium system, right? Things are going on completely out of equilibrium, not very far out, but somewhat out of equilibrium. That's what has meaning. That's what can lower the entropy and have organization by increasing the entropy of the surrounding. So the inside and the outside has to be separated by a boundary. Otherwise, the energetic molecules that you create by metabolism will all diffuse out. So you have to, and the information of life, which is contained in the DNA, which is in the nucleus somewhere here, will go out everywhere. You don't want that to happen. So, so you need a boundary, and that boundary is made up of what are called lipid molecules. Okay, they're fat with a little head group, which can be zwitterionic, polar typically, but also can be charged or zwitterionic. So this is what it looks like. So this thing is about 4 to 5 nanometer thick. It is really a bilayer, not completely symmetric because of different things, but it's a bilayer. So you have the head groups, which like to face the water because either they are charged or they are zwitterionic. And the fat, the lipid tails are then with each other because they don't like the water. You cannot solubilize fat in water, and they automatically organize themselves into, let's say, vesicles, things which are actually, they have a boundary, they can hold some water inside, or in this case, all of the cell material inside, and separate the water, separate the inside things from the water outside. The reason that becomes interesting is not just because of the lipids, but there are a lot of other stuff in here. The moment you create a boundary, the cell cannot exist by itself. It needs to have food, needs to have materials, small molecules, and need to carry information inside and out. You know, neurons won't work if they couldn't talk to another neuron. Your brain won't work. Basically, you know, we won't be talking about science if the human brain didn't evolve to signal. So all of these have to work through the membrane. It's easy to put a membrane where nothing goes this side and nothing comes in, but that won't create life. So it's a big challenge for evolution that it had to give pathways for things which can carry stuff, which could be material, could be information in and out. Some of these are ion channels, and they will carry ions across. And it's extremely important for the neurons that some ions are kept outside and let in only when you are thinking. You know, that neuron is quote unquote thinking. So it's selective opening of ion channels. And this all has a connection to the story I'm going to tell you. Okay, so this is how the ion channels. So there are many proteins, transporters, ion channels, sensors, etc. But I will concentrate on the ion channels. And these are how, this is a cartoon of how ion channels work. These are your lipid bilayer. They don't let in water or ions very well because they are lipid, fat molecules. Okay, they hide in themselves from water and they don't let water in. And if you do a little bit of physical chemistry, you can see that they also won't have charge inside them. It takes huge amount of energy free energy to keep a charge inside a lipid bilayer. But the water outside and inside, here's the cell, and here's the outside of the cell, and here's the boundary. They have lots of ions. And these ions selectively, exactly when the cell needs it, go through by a channel. That's called an ion channel. The ion channel can be closed most of the time, but due to some signaling, again by neurotransmitters, for example, it can open up. So the ion channels are open and they conduct ions and therefore electricity. And this is how neuronal spikes happen. So you can read about neuronal spikes and how we think, etc. separately. But this is the fundamental basis of that ions come in. Okay, and your neurons get excited. And on the right side, you see there's some color indicator put in, There are many neurons here. Only few are lighting up. The fluorescence indicator is lighting up, which are receiving the ions at the moment from the outside. So it's an extremely well-regulated event because you don't want the high state all the time. You want the high state only periodically. If you look at how your cell phone is actually looking at receiving data. Right now, many of you may be just looking at this talk with the cell phone. If you're looking at the data, then it's coming in zeros and ones. And the neurons have zeros and ones. Ion channel open, ion channel closed. There is a potential that goes up and potential that comes down. If it were open all the time, then it would be a problem. Or open in an unregulated fashion, it would be a huge problem. So why am I talking about that problem? So let me bring you to the next thing. What you see here is a brain which has been affected by a disease called Alzheimer's. All of you may not have heard about it, but it's a pretty common disease. In fact, if people live older and older, then it becomes more and more common. It's an age-related disease, and if you have a grandma or grandpa who is above 80, and there are chances, reasonable chances. The chance is 1 out of 2 if some person is above 85 that he has one of the related neurodegenerative diseases, and Alzheimer's is the most common, where people forget things. Okay, tend to forget things, and if you could do an MRI of their brain, you'll see that the normal boundary would be like this, and the brain has actually shrunk because a lot of the neurons have died. And inside the brain, you'll see deposits of proteins. Okay, if you cut open, and people have donated their brains, so you can cut open human brains and look at it, and you can see that they have deposits in their brain of a protein called amyloid beta. Okay. And to this, of course, from time immemorial, we have had this disease. And just this forgetfulness is not just part of growing old that we typically think about. It's actually a disease caused very specifically by these proteins aggregating, coming together. Okay, amyloid beta coming together. And billions of dollars have been spent in understanding how exactly this coming together of amyloid beta is causing the disease. Because this protein is actually our own protein. It's there in everybody's brain, your brain, my brain. The chances that it has come together a little bit is higher in my brain, okay, 50 plus person's brain, than your brain, and you're about 20, 25. So right now there's a prize has been declared. And since a lot of you are undergraduates and you're looking at literature survey, this actually prize is just for literature survey. It's a $4 million prize money from, it's called the Oscar Fisher Prize that somebody has donated. University of Texas at San Antonio is giving the prize. If you can come up, it's not a solution to Alzheimer's. If you can come up just with a proper understanding based on all your surveys of the literature, which shows what exactly, you have to make a hypothesis that's supported by all parts of the literature that explains how Alzheimer's happens due to amyloid beta aggregation or due to something, whatever it is. Maybe you are looking at a red herring and it's not amyloid beta aggregation, it's something that's possible. But what is the cause of Alzheimer's? What is the biochemical pathway of Alzheimer's? What are the biological pathway of the Alzheimer's disease? So just for understanding that, this is still open, and I'm actually requesting my graduate student, we just had a meeting yesterday, give it a shot. Okay, go for it. Let's see what you get. At least you have some understanding about a disease which is, there is no cure, and it's a lot of us as people are growing older in all societies because they're living longer with advancement of medical science that we face again and again, more and more. So here's our take. So our lab has been working on this question. Well, how does amyloid beta make, how does amyloid beta become toxic? How does it kill a cell? How does it bother a cell? Okay. So here is amyloid beta. And you say, oh, that's just a noodle that I had this morning. Yes, it exactly looks like that. Okay. Because typical proteins have a structure, but amyloid beta, it's a shorter protein. Sometimes it's called a peptide. Doesn't have a structure. Okay. So you leave it in water and it takes any structure. So it's an unstructured protein. Intrinsically disordered is the fashionable name for it. However, it does pick up a structure when they aggregate. Why exactly they aggregate in some people's brains and not others, we do not know. But we have sort of figured it out in a test tube, exactly why it happens, when it happens more, when it happens less, with what mutation it can happen more. We have figured it out in the test tube, but we still don't know exactly how that is happening in the brain, because test tube and the brain are, of course, very different things. But anyway, a lot is known about when they come together. A lot of these, hundreds, thousands, few, starting with a few, then hundreds, thousands of these proteins come together. They make these fiber-like objects. They're called amyloid fibrils. Okay, amyloid fibrils. And for the last 20 years, a race has been on to know that this is a, not a molecular level picture. There is a transmission electron micrograph picture. You see it's pretty large error, but these fibrils can be 6 nanometers, 10 nanometers, 12 nanometers wide. How is the molecular structure? The hope is to understand the molecular structure, you'll understand how it is becoming toxic. So normally they don't have a structure, they come together and you can see them under a transmission electron microscope forming a structure. And there are techniques which one of the I think organizers of Skyrocks, our own Veena Singh Mittu, had helped solve to some extent. Solid-state NMR has given some pictures, and now this is from cryo-TEM, how the molecules are organized. And a lot of work has gone into this by the best labs in the world. And the structure is nearly solved. It hasn't told us why it is toxic. Okay? So that's one big elephant in the room, that you will go on and get these structures done, but you can't tell. These structures are not telling us why it is toxic. You cannot guess from the structure, which the atomic level structure is given here. It's the stack of amyloid beta, why it is toxic. So one hypothesis that has gained ground is that it's not in these things which are formed by thousands and millions of these, but the initial aggregates, which are maybe the dimer, trimer, tetramer, pentamer of these, they actually form unregulated ion channel-like structures. So from these unstructured things, they go into this, sit in the membrane. So this is my cartoon of the membrane. Sit in the membrane and make unregulated ion channels. So I told you a little while ago, cells do need ion channels that are perfectly regulated. They open up when they need it, they close it down when they don't need it. But these are unregulated ion channels, and probably they're open all the time or most of the time and do not obey the cell. And the cell goes into an excitotoxic state, and perhaps other things happen, which ultimately kill the neuron. Okay, it's worse for the neurons. So this structure is a cartoon taken from an actual structure of an antimicrobial peptide. Nothing to do with amyloid beta or Alzheimer's disease, but people think this is the kind of structure that perhaps amyloid beta makes. And it makes a hole in the membrane. There's a barrel. It's called a beta barrel because this structure, few of you know, would be an anti-parallel beta sheet. And there's a hole through it, and ions can go through. So the whole of the rest of the talk is about how, whether amyloid beta really fits this picture. So let's ask. So the two questions I'll ask is, first, is amyloid beta causing Alzheimer's by acting like an ion channel in the membrane? The hypothesis has been given by many people. We also somewhat believe it, but we are scientists who don't have a fixated idea, oh, we must prove it. Either we prove it or we disprove it. But we want to figure out whether it works. To the extent we understand the larger structure, the fibril structure, it shouldn't work, because that larger structure has something called a parallel beta sheet. And as I said, these structures that have been proposed are anti-parallel beta sheet, and they're very different. Okay, so first question, is the oligomer different at the secondary structure level? That is it anti-parallel while the large aggregates are parallel? Is it maintaining that structure in the membrane? Does it have a defined non-random orientation in the membrane? Because the structure needs to sit through properly in the membrane to be an ion channel. If it goes in all orientations in the membrane, let's say is like this, it is likely not acting as an ion channel. And finally, the structure that I showed, the beta barrel, is made of 8 strands. And people think that maybe there are a particular number of monomers that come together in an oligomer of amyloid beta that makes such a structure. One single amyloid beta has a turn, so it is 2 strands by itself. So 4 of these will make an octameric ion channel. That could be possible. So nobody even has shown any of these. So if we say A, B, C, D are yes, then I know that yes, it is possible. It will still not prove in the brain that's how it is doing it, but it is possible. And the last part, as I said, I'll talk about only if I get time. Do neurotransmitters prepare the ground for amyloid attachment? So these are 2 different halves of my lab, or different parts of my lab. Why am I talking about neurotransmitters and amyloids? That's because amyloid disease, especially Alzheimer's and some other amyloid disease, there are many of these, Parkinson's and ALS, which Stephen Hawking had, and all that. They seem to have their favorite types of neurons. The types of neurons are separated by the types of chemical messenger molecules that they use. For example, serotonin. So one molecule, it's a monoamine, and it's one type of neurons. So it has been seen that amyloid beta attacks only 1 or 2 types of neuron to start with. Then everything starts dying, but initially. And those are acetylcholinergic, that is acetylcholine is the messenger molecule, serotonergic, norepinephrinergic. Norepinephrine is alcohol. So we wanted to understand, is nature telling us something by showing, look, not all neurons are dying at first, it's only the neurons carrying these molecules which are getting attacked. So one side is a membrane attacked by the amyloids, the other side is that are all membranes in presence of all kinds of neurotransmitters the same, or do the neurotransmitters have an effect? Okay. So let's start with 1A, the amyloid beta oligomers story. And this structure was very difficult to solve because, as I said, the larger structures are well solved. That's also difficult. I'm not taking anything away from anyone, but the smaller structures are unstable. So any structure that you solve, for example, by NMR, and I know you guys in GNDU have an NMR machine, you need hours of data taking to solve the structure at millimolar concentrations. Here, this protein will be a micromolar concentration, and a particular oligomer will stay like that only for perhaps, I don't know, minutes. Okay? So it's impossible. So 2 very gifted graduate students, one is Bidyut Sarkar and another is Venus Singh Mithu, when he was here 6 years ago or so, they sat together, came up with ideas, mixed different techniques. So Bidyut Sarkar was in my lab and Venus was in the lab of my colleague Prasanjit Kar, and they sat together and came up with these ideas that by combining those techniques, they will be able to solve this. Okay, I'll not get into the story because Venus is right there, he can take you the story someday. But finally, they had a structure which showed that yes, there is a fold somewhere, and this looks like an anti-parallel beta sheet. It was followed up by other people who completely shown everything. It was not possible to do it. It was too much work. So 5 years worth of work that we finished in 2017. And so finally we knew it is an anti-parallel beta sheet. So first thing was proven. But it was harder to prove the second thing. Okay, it's an anti-parallel beta sheet in the solution, but if it goes to the membrane, does it look like that? Because as I said, it has to set in the membrane. That's the hypothesis for processing. Well, other set of students led by Varun Maiti actually built again other methodologies. This is why I said you need to be a little bit of a physicist, a little bit of a physical chemist, a little bit of a biologist to solve these problems. He built something, an extremely sensitive line confocal Raman spectrometer. He did about 2-3 years ago, and looked at different things. He and Debanjan Bhone looked at plasmonics. I won't get into plasmonics. That's something that you should read separately. But this is about using nanoparticles of gold or silver to ask about conformations of proteins in the membrane. So you see there is a lipid bilayer that wrapped around nanoparticles. This bar is about 50 nanometer. This is a silver nanoparticle. And you can see there is about a 4 or 5 nanometer wrapper. And that wrapper had amyloid beta in it, and all these lasers, etc. that you see by using Raman spectroscopy, we could figure out we could ask the question, not at the atomic level, but we could ask the question, is it parallel or anti-parallel? Roughly atomic level structure we already have. And the answer was, yes, it was anti-parallel. So different from how it aggregates and makes larger aggregates, but very similar to the barrel kind of structure that antimicrobial peptides have, which I showed. So it's all consistency. We are coming closer to the picture. One by one is like an onion. We are unwrapping the thing, and we are saying, yes, it agrees with our notion that it could be a beta barrel in the membrane. All right. So if you take one of these, I know that one of these is like that. Okay, so if you go like this, I just pick one of these strands, and one of these strands can be represented by one A beta, and one A beta can make a figure like that. Okay, and then question is, how many A betas do you need? First, okay, before that, I asked, how is their orientation? Is their orientation a proper orientation or random orientation? Because a random orientation, then it's unlikely that you'll have something meaningful there. So another gifted student, Bappa Chandra, he did some of these experiments using again plasmonics and fluorescence quenching. Okay, some of you probably have heard about techniques where you measure lifetime, and it's a lifetime can be actually a function of the plasmonic field if you put it close to a plasmonic particle, nanoparticle. So there's a nanoparticle, there's a plasmonic field that decays across 4 nanometers. It's not to scale. The nanoparticle actually is big, it's 50 nanometers, and this cartoon is 4 nanometers. But anyway, the field decays, and if it's close, they put a fluorophore at some part of the protein. If it's close to the nanoparticle, to gold, it whitens down, and if it's far, then it's happy as it is in water. So it was asking if I put a fluorophore at one end versus the other. You know, proteins have C terminal versus N terminal. At one end, always I find it closer to the nanoparticle. The other end, suppose I find it away from the nanoparticle, then there is a particular orientation, right? Otherwise, I'll see half and half and sort of all random orientations. That doesn't happen. We could see by looking at quenching, which shortens the lifetime, that C terminal is always closer to the inside, N terminal is always closer to the outside. So there is a particular orientation of this thing, the membrane. So we had to see that. I had to put a model which is not quite like a U but like an S, but I will not get into it. But we could figure out that yes, there is a particular orientation. So one by one and coming. Okay, so it is made up of anti-parallel beta sheets, the oligomers, the fumers. Oligo means few, so these are not large aggregates. B, that anti-parallel beta sheet is maintained in the membrane, that is got by Raman plasmonics, and C or 3, which is the C terminal tends to be inside and they are oriented in a particular way. So far, so good. Okay. The last question is, does it have a particular number of monomers? Because if you want to make a particular structure that would, and you piece together these monomers, then that would need a particular number. Otherwise, if it's a random number, then it's unlikely to be an ordered structure, an ordered chain. So this required, this is our newest toy that is built in the lab, a single molecule imaging microscope. You can see single molecules, okay? And the better thing it can tell is that suppose you have 2 single molecules together, optics has a resolution. It can tell if 2 single molecules are closer than what is called a diffraction limit, closer than about 250 nanometers, okay? So it will see a single molecule if a single molecule is there, but you won't be able to know its size, but it will be like defocused. Sometimes you know there is a very far out, there is a light, but you can't tell if it's a car lamp, which is this big, or if it's a tiny bulb, which is this big. But you know there is light because you can see the light. Similarly, the single molecule spectrometer can see very sensitive, so see light from a single molecule. But if two molecules are together, you won't see a separate two spots. It will say a spot. But yes, it will be a brighter spot. And to know how much, how many molecules are together, now we're asking the last question: is it really a monomer or a dimer or a trimer or a tetramer or a pentamer? What is it when they sit in the membrane? We decided, Shimli Dey is a person who decided, well, we'll keep looking at it. And if you were looking at these Diwali lights, after they have burned for hours and hours, especially if you buy the cheaper ones, slowly one will go off, and then the next one will go off. There's no correlation, but after if you have them on for days, they'll all burn off. It's exactly the same experiment. She's looking at this single spot, which is bright, but I don't know if it's bright because there are 10 there or 5 molecules there. Because with intrinsic brightness, we don't know much idea. But if you keep looking at it, they will occasionally fuse. In this case, one fluorophore will get photo bleached. It's like photochemistry. And you will lose a little bit of the intensity. So no matter what the intensity was, you will see a step. Then another one will go off, photo bleach, you'll see another step, another step. If you count till the whole thing becomes dark, you know how many steps there were, and therefore how many molecules there were. Okay? So this is the experiment, and this is some of the data. For example, here she was looking at one spot. There are many spots, some of the multi-molecule spots, some of the single molecule, that is oligomers, which are, say, N-mer. N-mer can be 1, 2, 3, 4, 5, 6, whatever. Okay? And if you look at each of these spots and follow this with time, and you see, if you trace the intensity of any given spot with time, they go down, okay, in one step, they go down in another step, and they have come to the background. You know, in hindsight, that was a dimer you are looking at because it bleached in 2 steps. If it bleaches in 1 step like here, it is a monomer. If it bleaches in multiple steps, it's a tetramer or trimer. So that's how she counted. And she found out that, yes, there are all kinds of things that sit on the membrane, but the highest population is of tetramers. Okay, each monomer has 2 strands if it folds. Tetramer will have 8 strands. That exactly matches the kind of structures that these beta valence make. Of course, there are 8 mers, 10 mers, 12 mers, etc. But it has a specific preference, though not by no means exclusive, specific preference for a tetramer. This part is shadowed out. We are still working that out. The statistics is poor, so don't look at this part. Just look at this part. We are very sure about that. So sure that we have published it, and we have more tetramers. So now we have all the things out. Yes, it's at least preferentially a specific type of oligomer, which is a tetramer. Yes, it is oriented in the membrane. Yes, it is antiparallel in the membrane. So all these things check out, and we know that story of ion channel is perhaps right. As I said, we haven't yet proven it, because we have to really see it in the brain somehow. That is not possible as yet. Maybe possible, will be possible someday. But it's a very, I would say, consistent story that gives us a lot of confidence that perhaps what we are thinking is right. Okay, Chair, how much time do I have? Can somebody tell me how much time I have? Because then I'll go to the second part, or I will not. I will stop here. Somebody saying something?
Yeah, Professor, you have 15 minutes left for your talk.
Okay, good. Excellent. I'd like to leave some time for question answer. So I'll try to finish in 5 minutes. Thank you very much. So the second question, right? What is nature trying to tell us by showing us that all neurons are not the same? Some die first, some die later. Those that die first due to these attacks, and these are not just one disease, amyloid beta for Alzheimer's, there is amylin, IAPP for these things. In fact, the last result I forgot to mention was from IAPP, not A beta. But there are different things that attack different neurons. So you wanted to know, is it something? So the first part of the story was about attachment of the amyloids. And the second part is about whether the neurotransmitters do anything. So does the neurotransmitter do anything to the membrane? This is not something that how biologists understand neurotransmission, that is not a message exchange between neurons, because there are receptor molecules, proteins, which sit on the membrane, and they are the targets of the neurotransmitters. Nobody thinks that the membrane is the target, but we found something very funny. Again, Shimli De and Ankur Gupta, two of my students, found something very funny. If you look at a membrane which has some structure, some membranes have structures. In biological context, they will be called rafts, and in physical chemistry context, these brighter things. So this is 1 micron. So you see, brighter things would be called ordered domains, and darker things who have disordered domains. Is a atomic force microscopy picture, and you see them differently because atomic force microscopy judge the height, and these domains are about 1 nanometer higher than these domains. So you're looking at like a scanning thing. You're looking at a membrane which has little bumps, and these are the lighter things are the bumps. If you keep looking at it after you put in some serotonin, you see that the ordered domains, the higher bumps, are actually, let's look at this thing, okay? Let's look at some area like this. You see, it gets some disordered region in it, right here. You can see this same thing. It's just a function of time, and that hole grows. If you look at this, you see suddenly there is a disordered region in here. That disordered region grows, and that disordered region completely grows much more. So the membrane becomes disordered in presence of serotonin. This is something that nobody knew, but then people will say, okay, so what? I mean, you have some observation, and this is admittedly not on cells, this is on artificial lipid bilayer. Maybe it doesn't have any observation. But you wanted to know whether that does anything to the mechanical properties of the membrane. And it does. So AFM can also measure force. You can sort of poke like a balloon. You can poke it and then you make a hole in it, and you can measure that force. Of course, there's a 4 nanometers thick thing, and the force that you require is tiny. These are nanonewton forces. And what you see is a measurement of pressing in, and you get a little kink there is where the force, with a pin you are pressing down, and the pin punctures the membrane. And that tells you how tough the membrane was. And this shows you that without serotonin, the membrane is tougher. With serotonin, the membrane is much less tough. And you can do, I'll take you to a story with NMR, the solid state NMR, you can also find out how disordered, so this is the lipid molecule, one lipid. So there's the lipid head group, cartoon of course, and these are the 2 lipid tails. They make up this membrane, and you can look at how close the serotonin is to any of these when they sit in the membrane. They do sit in the membrane, and they are about in here by looking at some cross relaxation experiments that are done by my collaborator Daniel Huster in Germany, and we could figure out that yes, all the story is consistent. Neurotransmitters do affect membranes. This is, I think, my last slide, and they do affect amyloid attachment. But you see on the right, on the left, are brain cells that we culture on dishes, okay? And the bright objects are one kind of amyloid, in this case not amyloid beta, but IAPP, which is related to type 2 diabetes. They seem to attack the membrane much more in presence of serotonin. So this is without serotonin, they attack the membrane anyway. And this, before we add this fluorescent thing, there's some intrinsic fluorescence in the cells, but you see a lot more fluorescence because these things attack. But if you have serotonin in there, they attack a lot more, lot brighter. And you can do this extra attachment of these things. You can plot it by analyzing these data, this image data, and it shows, yes, neurotransmitters and specific types, not all types, do change properties of the membranes, which do induce more attachment of these oligomers. Now, if you put 2 and 2 together, those higher attachment may mean higher number of barrels and therefore higher toxicity, a higher number of unregulated ion channels, higher toxicity for a class of cells which have that particular neurotransmitter. Again, I'll caution, we never jump into conclusions because there are lots of do's and don'ts. It's kind of a in vitro, I mean, with live cells, but still in a dish that we are showing, yes, if you have these kinds of neurotransmitters around, then you can have in principle higher toxicity. So it doesn't prove that that's how exactly it's happening in the brain, but it opens up a very exciting possibility that shows how the observation, which that some neurons die faster in real brains, can be, in principle, explained by this. At least there is a very possible explanation. Okay, so let me conclude here. What did we learn after all of this? Well, first question we asked is that is amyloid beta is causing Alzheimer's by acting like an ion channel? Again, no direct answers, but 4 questions we asked and we have answers to all 4. Is the oligomer different at the secondary structure level? Is it anti-parallel? Yes. That's the solid state NMR. Is it maintaining that structure, anti-parallel structure in the membrane? Yes, that's the Raman thing. Does it have a defined non-random orientation in the membrane? Yes, that is the lifetime with plasmonics thing. And does it have a defined number of strands in the membrane? Yes, this is the single molecule photobleaching thing. Okay, so all of these we have answered. They are all consistent with the picture that we have in our mind right now. Second part was, do neurotransmitters have anything to do with amyloid attachment? Yes, they do prepare the ground by making the membrane more disorder for amyloid attachment. So this also we found out. The answer is yes. Okay. I stop there by thanking the people who really actually not only work very, very hard to make all these possible, but most of the times they also think about the solutions. You know, I get to talk to you about it because I am with them. I know all the stories, but really the credit goes to all of them. These are my graduate students, mostly current, but some have left these shores, mostly have gone for their postdoctoral assignments to the US. And the story I talked to you about today, actually the last bit of story is from Shimli, the single molecule photobleaching, and both Shimli and Ankur doing the AFM. Bappa did the last part of that solid state NMR kind of things, and there are other people doing other things, all fantastic, and we're very lucky to have the students. And you see all the new students, current students, and many past students, including these 2 gentlemen, without which all this work wouldn't have been possible. And of course, lots of collaborators. Madhu and Daniel Huster are 2 of the people who have helped a lot in this kind of work. Financial supports come from Department of Atomic Energy and Department of Biotechnology of the government. Without government support, it's very tough to do basic science. And thank you very much for sticking with me close to an hour.
Thank you, sir. Now the time for 1 or 2 quick questions from the participant. There is one question regarding the how many oligomers are required for this process?
Okay, so that's a question we tried to answer at the last bit when you did the single molecule photobleaching. So if we just look at all the oligomers sitting in the membrane and do a relative population study, then you'll find that the affinity for the tetramers for the membrane is the highest. So it's not a 1 or 0 answer. It's not like only tetramers bind to the membrane and all the other mers don't, but the tetramers are most likely to bind. So that's the answer that we have.
Okay.
Can I have a question if here allows?
Yes. Yes.
Hello, Professor Mehdi. This is Dr. Pandey from IIT Roorkee. Not a kind of question. It's a kind of, I just want to know your comment. So when these oligomerization we try to study in the lab, we do in extreme environment, either at a very high pH, or we need some kind of tagging agent to see them kind of things, right? But in actual process, the Alzheimer process is pretty slow, right? So could you kindly comment on that?
Right. So I take it in 2 parts. First is the kind of environment we have to study it in. And our lab, we shun all kinds of non-physiological solutions. So we do have only physiological pH, pH 7.4, and all the physiological buffers, and the same buffers where our neurons can be. And yes, for fluorescence experiment, we do have to tag them, but we do have a corroboration of the kind of data that we get between that and the NMR where they're not tagged. Well, some of them are isotopically labeled, but that's of course not extra tagged, same atoms. So that's the first part of the question. Second part is the question that time taken for Alzheimer's is very long, and you are looking at the lab very short. And yes, it takes maybe 20 years for somebody from the start to full-blown Alzheimer's. And I won't have a student left in the lab if they said, well, you keep looking at it for 20 years. So yes, we do these experiments typically at a slightly higher concentration, and the hope is at that higher concentration, at a faster time scale, we look at the same phenomenon. It may be wrong, and one of the things that we are doing at the moment is actually multiple test tubes at low concentrations. We see, instead of having it very long time, you have a lot of variance, a lot of statistics. It's the ergodic principle. If in the phase space, if you increase the phase space, then everything is happening at least in one corner of the phase space, versus in one test tube for 20 years, if you look at it, something will happen. So that's those are the approaches we are taking, but it's a hard problem because it's not like potassium cyanide. You dump it on the cells die, and you figure out how it happens. This does happen, and it's difficult to capture.
Thank you very much, Professor Mehta.
Okay, thank you. Dr. Venus, are you here?
Yeah. Hi, Shilpala.
Hi, Venus. How are you?
I'm doing fine. Yes.
Go ahead.
Yeah. So I mean, I shouldn't be asking many questions, but yes, there is one specific question which I want to ask. That when you say that you follow one spot of light to count the number of monomers in the oligomers. Now the thing is, I mean, how do you follow a light? I mean, is it in the solution, or I mean, how do you do it experimentally when you say you follow?
Experimentally, you put a bilayer, deposit a bilayer on a piece of glass, and then you incubate that with a solution of oligomers, and you let it be for a while, and then you gently wash off the solution oligomers, because some will go and stick in the membrane. They might slowly come off, but that takes a long time. So now you have some oligomers sitting in the membrane, and they are not that dynamic because diffusion is much slower in the membrane, especially for oligomers which have been inserted. So you wait for a long time. Oligomers which are not very well inserted, just absorbed on the membrane, they go on. So then you can follow them, and they're moving a little bit, but you can still say, oh, that's if I name that spot Venus, then that's Venus going around, and then I see that Venus moves in one of the molecules and the second of the molecules.
No, I thought it was LUVs, but yeah, if it is a membrane bilayer, then
it's membrane bilayer.
Okay. And the second question is that when you say that IAPP binds more when serotonin is present in the membrane. Now the thing is, I mean, IAPP and serotonin together, I mean, isn't it a bit of, I mean, we don't have IAPP in the brain. I mean,
okay. Actually, I also thought so. IAPP is not in the brain. It turns out that IAPP does go to the brain. Okay, this is part of the signaling mechanism. But the reverse is also true. There's a lot of serotonin in the, so IAPP comes out secreted together with insulin, and those things also secrete serotonin. Nobody knows why.
Okay.
So in the pancreatic beta cells, they're very strong serotonin exocytosing agents, and it's together in the same vesicle to come out IAPP, insulin, and serotonin. There is a connection, obviously, somewhere. Need not be the connection that we are looking at, but I'd be really surprised if you ask me if this is not one of the things that the nature wanted, that let it go and stick and under normal condition, and that's why the serotonin is there. Could have other answers, but yeah, it's a biologically relevant topic. Putting this.
Okay, that's very good. Great. Very nice talk, finally.
Thank you.
So there is one more question from the student participant.
Okay.
Do we have any advanced technology to change or replace membrane?
To change or replace
membrane.
Yeah. So see, the membrane is what gives the identity to all your cells, all my cells, and all my neurons. I have about 100 billion of them. Well, I have lost a few in my 50 plus years, but I still have hopefully much of it left. So each of them are individual things which were born with me. Neurons typically don't divide. There are no stem cells, but typically don't divide. I was born with them. They're stuck around for 50 plus years with me, and they're all in close relationship. So the question you should ask instead of replacement is really repair. And the membranes are repaired constantly. Okay, there is membrane traffic. It's a big field in biophysics where parts of membrane go into the cell and new fat molecules come in. So the membrane is in a dynamic thing, and it's repaired. Or partially replace continuous here. The whole of the membrane, of course, has to hold the cell inside. So it's never the whole thing opens up and some other thing comes in. But yes. And so, yes, it's important to keep your membrane healthy. And a lot of people forget, but our especially pregnant mothers should not forget that when especially the baby's brains are developing, they need a lot of cholesterol for the brain neurons to be healthy, the membrane to be healthy. It requires the right amount of rigidity and the right amount of softness to do all of these things. And cholesterol is a very important part of neuronal cell membrane. So you have to eat balanced diet, etc., and not go just one way saying, oh, reduce cholesterol everywhere. That's okay for when you have as old as me, but remember that the membrane also needs to be nurtured. Yeah.
Okay, now all the questions has been answered. So once again, I thank Professor Sudipta for such a nice talk.
Thank you for this opportunity. Bye, guys.
Thank you. Thank you.
Yeah, thank you so much, Professor Mehti, and thank you so much, Dr. Raman Mahajan, for sharing.
Thank you, madam.
It was perfect, and we are back on track, back in time. We are going to start with the next poster session before taking a lunch break, and after lunch, we are going to resume our scientific sessions. So over to you, Jasmine.
Yes, ma'am. So without any further delays, switching back to our enthusiastic poster presentees, let's start with second live poster session of the day. I'll invite Ms. Simran, final year MSc student at Physics Department GNU. She is senior core committee member of CyROX and mainly creative head for the committee. So I would request her to start with the session. Over to her.
Good afternoon, everyone. Am I audible, Jasmine?
Yes, you're audible.
Yeah. So I welcome you all to the second session dedicated to poster presentations. So now we are going to listen to the remaining 7 posters in this session. And to judge these posters, we again have with us Professor Jaya Murugan Govindsamy, Professor Ravichandra Singh, Professor Tejwant Singh Kang, Professor Saptarshi Mukherjee, Professor Palani Natarajan, Professor Shubhra Singh, and Professor William Yu. For those who weren't present in the first session, I would like to repeat the guidelines for you. So please listen carefully. In all, each presenter has to present his or poster in 8 minutes, which will further be followed up by a 4-minute Q&A session. I will intimate you after 7 minutes, and I expect you all to abide by the time limit as we don't want to run short of time. With this, without any further ado, I call upon our first presenter of the session, Ms. Hira. Her title is Enhanced Optical Activity in Naphthalocyanide Doped Silver Nanocolloids, and she is from Catholicate College. So over to you, Hira.
Simran, it would be better if you also announce the poster number because judges are grading them according to their poster numbers.
Yeah, sure. Her poster number is 909. So over to you, Hira. Hira, kindly unmute yourself and turn on your video. You are not audible, Hira. Please unmute yourself.
Okay.
Yeah, now perfect. Please go.
Okay, ma'am, 1 minute. Sorry for the disturbance.
Yeah, sure.
Hira, if you have problems sharing screen,
No,
I
no,
can
ma'am.
play your pre-recorded video.
No, ma'am, I will.
I think your videos will not be yeah, you can turn off your video and then share the screen and keep yourself unmuted.
Okay, ma'am. Ma'am, give me 1 second.
Sure.
Ma'am, is that clear? Can you see something?
Yeah, it's visible.
Yeah, can you see my presentation?
Yeah, I can see your first slide.
Okay. Okay, ma'am. Okay, good afternoon, everyone. My presentation is about photoluminescence enhancement studies of naphthalocyanidide of silver nanocolloid. It is done as an MSc work with my guide, Dr. Dhanya I. Okay, the main objectives of my study are green synthesis of silver nanoparticles using the leaf extract of ashogam leaf, which is Saraca declinata, and to find out the effects of gamma irradiation which made on the samples, and the characterization of the samples by different characterization techniques like TEM, SAED analysis, UV spectral analysis, and photoluminescence, and to finally carry out the luminescence studies. This is the method of preparation I followed. First of all, I weighed out 20 milligram of silver nitrate and dissolved it in 150 ml of deionized water. To eat 10 gram of leaf extract, a freshly prepared leaf extract is boiled for 5 minutes, and it is suitably divided into 1 ml, 3 ml, and 5 ml of concentration. To each of these solutions, 30 ml of silver nitrate solution is added, and it is mixed well and kept for 2 to 3 days at room temperature for the formation of silver nanoparticles. And after 2 to 3 days of observation, we can see a change in color of the samples from pale yellow to orange red color, which signifies the formation of silver nanoparticles. Okay, this is the first result that I obtained after 2 to 3 days of observation. The first picture shows the samples as it is prepared from the leaf extract. That is the samples without irradiation. We can see a change in color from pale yellow to dark red as the concentration of the leaf extract increases in the first picture. Then the second picture shows, towards the right picture shows the gamma irradiated silver nanoparticles. On comparing with the first picture, we can see in the second picture, there is a color change from dark color to pale yellow color after gamma irradiation. I will explain why it occurs. Okay, this is the characterization I have followed. That is the TEM analysis and the SAED analysis. This is for the samples without irradiation. From this figure, we can understand the average particle size of the nanoparticles are 43.89 nanometer. And we can see the particles are in like agglomerated. They are not individual particles, they are like agglomerated, and they have some hexagonal morphology. And from the SAED analysis, the particle shows an FCC crystalline structure. This is the TEM analysis, SAED analysis of the samples after irradiation. From this, we can see individual particles after gamma irradiation, and also the particle size got extremely reduced. Earlier, it was 43.89 nanometer. Now, it is 21.33 nanometer. That is, the size of the particles got reduced like to half of the initial size. It got reduced by gamma irradiation. Now, the particles are spherical in morphology. Also, it retains its FCC crystalline pattern. This is what we have got from gamma irradiation. That is, we obtained individual nanoparticles without any clustering. The gamma irradiation eliminated the clustering of the nanoparticles. That's why they increased, gamma irradiation increased the activity of the silver nanoparticles by making them some individual particles without any clustering. Okay, these are the studies I made with the samples. That is UV visible absorption spectra of the samples before and after irradiation. This UV visible spectra is for the sample 5, that is sample with 5 ml concentration of the leaf extract. Here the leaf extract acts as a reducing agent. So from the first graph, that is for the sample without irradiation, we can see as the A1 represents the sample with 1 ml of leaf extract concentration and 3 ml of concentration and 5 ml of concentration. That is respectively A1, A3 and A5. That is for the sample A5, the absorbance is maximum, somewhat like 1.35 absorbance. The absorbance increases with the increase in the concentration of the reducing agent. That is what we obtained from the first graph. In the second graph, it is for the UV visible spectra of the gamma irradiated sample. From this, we can understand that it is for the A5 sample, that is the sample with a 5 ml concentration of leaf extract. As the concentration, as the dose rate, gamma irradiation dose rate increases, the absorption got decreased. That is, the maximum absorbance is for 1 gray irradiated gamma irradiated sample. That is, for minimum dose rate, the absorbance got increased. For high concentration of dose rate, the absorbance got reduced much. This is because by high irradiation, gamma particles got extremely separated. That is, they become individual particles without any agglomeration. So the absorbance also decreases by that extent. This is the band gap energy of silver nanoparticles. The first one is the band gap energy I have calculated for the samples without irradiation, and the second one is for the samples with gamma ray irradiation. From the first sample, this is the top plot, and I obtained 2.35 electron volt of band gap energy for the sample without irradiation. And for the samples with gamma ray irradiation, the band gap is found to be 2.14 electron volt. In both cases, the band gap is comparable with that of the original values, which is 2.5 and 2.8 respectively for gamma non-irradiated and gamma irradiated samples. This is the verification law of Beer-Lambert's law. From the first figure, it is for gamma irradiated A5 sample. First figure shows that as the concentration increases, as the concentration of the leaf extract increases from 1 ml, 3 ml, and 5 ml, the absorbance increases linearly, somewhat in a linear extent. That is, with the increase of concentration, the absorbance also got increases. In the second picture, I want to show that with increase in the dose rate, that we used 1 gray, 2 gray, and 3 gray of radiation dose rate. With the increase in the dose rate, the absorbance got highly reduced. This is what I explained earlier. With high dose rates, the agglomeration of the particles got reduced much. That's why the intensity of absorption also got reduced. Okay, this is the main study I want to, this is the main study of my work, that is the photoluminescence study, and how we can make an application of the silver nanoparticle with gamma. What? Sorry?
Just a minute left.
Okay. So I use the preparation is given here, and with the result says with naphthalocyanin dye-doped silver nanoparticles, when it is allowed for excitation with different wavelengths, it gives an emission in the 486.5 nanometer, that is in the blue-green region. This is the main result of my study. So my summary and conclusions of my study are: we can synthesize silver nanoparticles by Ashogam leaf extract, and with proper gamma ray irradiation, we can enhance the properties of the silver nanoparticles, and also the band gap energy of the silver nanoparticles are comparable with that of the standard value. I got an emission with the naphthalocyanin dye-doped silver nanoparticles gives an emission in the blue-green region, so it can be effectively used for the fabrication of blue LED. So that's all my presentation. Thank you.
Okay. Thank you, Hira, for this intriguing presentation. So now I would request the judges to go ahead with the questions.
Okay.
Hello.
Hello, sir.
Ms. Hira,
Okay.
you said that with the gamma radiation, the size of particle has been reduced almost to half.
Yes, sir.
What is the probable reason for that?
Main reason, I think, we concluded from that the agglomeration got eliminated. Earlier, the particles are mainly agglomerated, and that's why the size got increased.
It has nothing to do with the size. Even if the size is small, they get agglomerated. The question is why the size has been reduced.
Okay, we considered about the agglomeration, sir. That's why
agglomeration will be more if particles are small. See, because they have high surface energy, so agglomeration will increase. It has nothing to do with the size. So what is the difference? I mean, effect of gamma radiation on the size? Why it is reduced size of the particle?
Okay, sir. From gamma irradiation, the particles become more stable. I think it become more individual particles and become more stable. That's why I think of reduction in size is the reason.
Probably this is not the right reason for that. There must be some other reason for that.
Okay, sir. I will definitely check, sir. I thought of this reason. That's why.
Okay. Thank you.
Okay, thank you.
Hira, this is Shubhra. Hi, this is Shubhra from Anna University. So I just want to know what is the significance or motivation behind your work? Why are you choosing gamma radiation? And if there is any other method where you can achieve a similar effect or modification?
Yeah, ma'am. As because I have read some paper about this technique, so I want to just do my MSc work based on this. So I choose this method. Let's like a trial and error method. I have choose this and verified the results. So simply I choose this. That's why I want to make some other works regarding
Yeah,
this with some other
but I
technique.
think your motivation should be more strong. You know, it's obviously very difficult to get access to these. Not all can get. So if you have a proper motivation and significance which you are planning, I think that would be much better for your future work. Okay.
Okay, sir. Okay, ma'am.
Thank you.
Thank you.
Okay, here this is Natarajan from Punjab University.
Okay, sir.
The silver is normally, I mean, the silver nitrate are light active compounds.
Okay, sir.
So how you have done this nanoparticle synthesis? Is it dark or maybe in presence of light?
Yes, it's more. We tried to reduce the light, but in main cases we have to put them in light itself. But we tried the presence of light to illuminate. We tried to eliminate the presence because we tried many results in the dark region without a very feeble light. But in some cases we have to put them open in the light itself.
So it was not completely done in the dark.
No, sir, not completely, because we made to.
How you can correlate your reduction with, I mean, like a plant extract only done the reduction, because light also equally can do the role, na?
But I reduced the probability of light, sir, because we have we have to travel with that sample to take the TEM analysis. That's why there's a little bit of light incorporated.
Good. Thank you.
Okay.
So I guess we don't have any more questions. So with this, I thank you, Hira. With this,
Hira, can I ask one question?
Yes, sure.
Just a quick question. If you go back to your Lambert-Beer verification graph.
Okay, sir. Okay.
Yeah. So on the lower concentration, you are saying it is linear, but linear with 2 points is not correct.
Okay.
Any 2 points will always give you a straight line, correct?
Yeah, sir. Okay.
So when you're plotting the graph 1 to 3, there should be minimum 5, 6 more points between 1 and 3.
Okay.
Then only you can say it is linear. Otherwise, if you try to connect 2 points, it will always can be done by a straight line.
Okay. Okay, sir.
Okay.
I thought it is somewhat linear. That's what I want to say. I thought it is somewhat linear. Not fully, but to some extent.
It may be linear, but you need more points. Otherwise, the graph becomes invalid.
Okay,
Anyways,
sir,
thank you.
Sir. Okay, sir. Thank you.
So thank you, Hira. So now I would like to call upon our second speaker, Ms. Gitanjali Chopra from Guru Nanak Dev University, Amritsar. Judges, please note her poster number is 2020 and her title is Modeling Protein-Protein Interactions through Proline Amide Hydrogen Bonds. So over to you, Gitanjali.
Hello. Hello, ma'am.
Yes, hello.
Ma'am, I am not able to share my screen.
Can the first, Hira, can you please stop sharing your screen? I think you can try now.
Okay, ma'am. My sincere greetings to all the viewers. My name is Gitanjali Chopra, and I'm going to present my poster titled Modeling Protein-Protein Interactions Through Proline-Amide Hydrogen Bonds. Proline is a cyclic amino acid in which N-terminus is a secondary amine fixed within a pyrrolidine ring. And it is a mimic of many biological receptors. And I have studied the hydrogen bonding interaction of a proline with amides, as amides are the pharmacophore for many drugs. Thus, the hydrogen bonding interaction between the proline and the amides can act as a mimic for a drug receptor interactions. Thus, understanding the nature and strength of these hydrogen bond interactions can be very useful to the medicinal chemists who are working on the drug protein interactions or a drug receptor interactions. In the present times, the most important advantage of the computational studies is in the field of computer-aided drug design. And there are at least 12 to 13 drugs available in the market right now, which have been designed with the help of computer-aided drug design technique. These are some of those drugs. And there are many softwares such as Schrödinger, Gaussian, SAP, and Bio, molecular docking available for adopting this approach. And I have used many of these softwares in my work. And I have used these computational methodologies. Now, in the coming slides, I will show you the beauty of the computational studies, that how complex and very difficult problems can be answered in a very easy and a very effective manner with the help of the computational studies. There are total 18 conformers of the proline, out of which we have selected only the first 4 most stable proline conformers, which we have further categorized into 2 pairs, Pro-A, Pro-B and Pro-C, Pro-D, on the basis of the configuration of this carboxyl group. Within a conformer pair, in one of the conformer, pyrrolidine ring is puckered down, and in another conformer, pyrrolidine ring is puckered up. And to identify the most potential sites for the hydrogen bonding interaction, we have studied the molecular electrostatic potential, MAPS. I have tried to study all the possible modes with which amide can bind to the proline. And I have optimized nearly 60 hydrogen bonded proline amide complexes, which I have further categorized into 9 groups on the basis of hydrogen bond donor and the acceptor sites involved in hydrogen bond formation. On viewing this slide, or one question can come in the viewer's mind, that why I have chosen 1:1 complex system and not 1:2 or 1:3 and so on. The reason is 1:1 complex system can exist in gas phase and can be isolated very easily, and hence can be studied experimentally. So that my work can be beneficial to the experimental chemist, I have chosen 1:1 complex system. On analyzing all these 9 groups, I have found the following observations, that the most stable complexes are those in which carboxyl group of proline interacts with carbonyl oxygen and amino hydrogen of amide, forming 8-membered ring structure. And this is also in consonance with the molecular electrostatic potential data, according to which carbonyl oxygen and hydroxyl hydrogen are the most potential sites for hydrogen bonding interaction. The stabilization energy of these complexes lie in this range. Usually, it has been observed that the most stable hydrogen bonding network have a stabilization energies lie in the range 8 to 12 kilocalorie per mole. But here, the stabilization energies lie beyond 12 kilocalorie per mole. This indicates that these complexes are extraordinarily highly stable. Then, to find the reason behind the extraordinary stability of these complexes, I have opted NBO analysis, and I have found out that the actual reason behind the stability of these complexes is a strong resonance-assisted hydrogen bonding mechanism. Then I have found that the most stable complexes formed by pro-CD conformer pair are those in which carbonyl oxygen and amino hydrogen are of a proline are involved in hydrogen bond interaction with amide. And this is also in consonance with the molecular electrostatic potential data, according to which carbonyl oxygen and amino hydrogen are the most potential sites for hydrogen bonding interaction in a pro-CD conformer pair. All these hydrogen bonds are prevalent in the biological systems. For example, nearly 75% of hydrogen bonds in proteins are of this type, and this is the strongest hydrogen bond in proteins. And thus, understanding the nature and the strength of these hydrogen bonding interactions will be very beneficial to those chemists who are working on the protein-protein interactions. Now, there are three major components of the stabilization energy arising out of the hydrogen bond interactions. And there is one software available that is known as the SAPT software, which decomposes the stabilization energy into its energy components and thus helps us to identify that which component is contributing more towards the stability of the complexes. And in our case, we have found that the electrostatic interactions are playing a dominant role in stabilizing proline-amide complexes. Further, we have observed that in the red-shifted complexes, induced interactions are contributing more towards the stability than the dispersion interactions. Whereas in the blue-shifted complexes, dispersion interactions are contributing more towards the stability than the induced interactions. This is actually the very interesting observation and can be beneficial to organic chemists as well as pharmacists who are working in the area of these interactions. Actually, with the help of my poster, I have tried to give just a brief review on how, with the help of the computational studies, one can get an estimate about the nature and the strength of the drug receptor interactions before going into the experimental analysis.
Yeah, Gitanjali, just a minute left.
Okay, ma'am. This will not only reduce the time, but will also reduce the cost of a developing drug up to 90%. Thanks to all the viewers. Ma'am, I have completed.
Yeah, thank you, Gitanjali.
Okay, ma'am.
So now I will request the judges to kindly go ahead with the questions, if any.
Hello, Gitanjali.
Okay, hello, sir.
What kind of software you have employed for your studies?
Sir, I have employed the Gaussian, SAPT, NVO, WFA, and Avogadro in my whole study.
Okay, thank you.
Okay, thank you, sir.
Yeah, any other question?
Yeah, Gitanjali, I have one question. Your presentation was quite good.
Okay, thank you, sir.
I just wanted to understand whether it's a gas space calculations or solution space.
Okay. Sir, I have studied both gas phase as well as the solution phase studies. And I have just visualized here gas phase studies. Because of the shortage of time, and but I can give just a brief review about the solution phase studies. I have chosen the three solvents of largely varying dielectric constant, and I have found that the stabilization energy decreases as we move from a gas phase to highly polar solvent cyclohexane via dimethyl sulfoxide to highly polar solvent water, and this indicates that stabilization energy decreases with the increase in the polarity of the solvent.
Okay, fantastic. So outcome is overlapping.
Sir, sorry, I can't understand.
Both the case, gas phase and solvent phase, both of them, the outcome, results are a little bit overlapping, it seems.
Yes, sir. Outcomes, yeah. Sir, I have compared the stabilization energies. I have compared the bond distances, and actually all the properties of these complexes changed in the solution phase. Actually, I have found that in solution phase, these hydrogen bond interactions get weaker, and accordingly, stabilization energy also gets weaker because we are calculating the stabilization energy in this case arising due to the hydrogen bond interactions.
Okay, thank you.
Okay, thank you, sir.
Gitanjali, just a quick question. You did not say anything about the nature of the interaction. What kind of interaction do you expect?
Yeah, sir. Nature of interactions, sir. Actually, in the hydrogen bond interactions, there are actually the three main components: electrostatic, induced, and dispersion. And I have found that 60% of the 60% interactions are electrostatic in nature in my complexes. Because I have said, I have used software SAPT. SAPT did what? SAPT decomposes the stabilization energy into the various components, electrostatic, dispersion, and induced. And I have found that in my complexes, the electrostatic interactions are playing a dominant role in stabilization of my complexes. And as I have further in one of the slide I have showed here, that in the red shifted complexes and the blue shifted complexes, I have just compared that in the red shifted complexes, dispersion component is playing a negligible role, whereas in the blue shifting complexes, dispersion component is quite significant. This is actually, sir, this is what
Just
I
a small
want to say
suggestion,
about the
try to,
yeah. Hello, sir.
yeah, just a small suggestion, you can include sodium chloride and run the Gaussian again.
Okay,
just repeat this in presence of sodium chloride. You will be getting a different result.
Yeah, sir, definitely. Thank you for your suggestion, sir.
So yeah, thank you, Gitanjali, for your wonderful talk. With this, I would like to move on to the next presenter, that is Ms. Poonam Sharma from Gunanga University, Amritsar. Judges, please note her poster number is 2222 and her title is Chromogenic and Fluorogenic Probes for Metal Ions. So over to you, Poonam.
Thank you. Second. My screen is not sharing.
Wait a second.
Sure.
It's visible now.
Okay, thank you. Good afternoon, everyone. Myself, Poonam, Guru Nanak, research scholar from Guru Nanak Dev University. I'm here to present a poster for this conference, that is chromogenic and fluorogenic probes for metal ion using UV visible and fluorescence techniques. So basically, these UV visible and fluorescence technique relies on the Jablonski. Depends on the absorbance techniques, depends upon the Beer-Lambert law, and the fluorescence technique depends on the Jablonski diagram, as yesterday told by Dr. Shogun. So objective of my work is to synthesize the near IR-based chromofluorescent chemical sensor to detect metal ions, because metal ions are very important part of our life. Here my motive is to sense the copper metal ion and palladium species by functionalizing the Bay position of the parylene diamide fluorophore. So here I'm presenting this poster where the parallel I have functionalized the Bay position of this parylene diamide to sense the metal ions, because copper metal ion imbalance in the body leads to neurodegenerative diseases, and palladium species has as such no role in the body, but used in various reactions in coupling reactions and in jewelry and other appliances, electrical appliances. And palladium chloride is very toxic, and it leads to liver damage. If swallowed, inhaled, it leads to damage kidney, liver damage, kidney, etc. So due to this problem, there is a need to synthesize the probes to sense the metal ion. So I have synthesized the parylene diamide based probes by functionalizing this parylene diamide fluorophore. So here is I'm presenting two probes, that is a probe 1 and probe 2. In case of probe 1, that is a OPR PDI probe. Here the PDI fluorophore is connected to the oxime propargyl hybrid moiety connected to the phenyl ring, and to sense the copper metal ion and the palladium species. Here the copper metal ion binds to this nitrogen or oxygen binding moiety, binding sites, so leads to the upfield shift in the NMR protons. And in case of palladium species, here the hydrolysis of shift base or depropargylation take place. That is also confirmed by NMR spectroscopy. So this probe can be utilized to sense this metal ion through different channel. In case of copper ion, here it acts as a chemosensor, but in case of palladium species, it acts as a chemodosimeter. So this probe can utilize to sense these species in solution, solid phase, in bioanalytes, and also in the bioimaging application. Now come to probe 2. In case of probe 2, here I have functionalized the P position of this parylene diamide derivative. Here the 1,4-diaminobutane is appended to this wave position that is further connected to diester moiety to sense copper metal ion. Further, this copper ensemble is used to differentiate the cyanide ion and sulfide ion through fluorescence window. Now, comes to probe 1. Here, this probe 1 have the different propensity to aggregate in the different polarity of solvents, and here the aggregated and the monomer bands are present. So this is the absorbance, and this is the fluorescence band of this OPR PDI in different solvents, showing different color under visible light and under 365 nanometer illumination. So this probe can be used for these solvatochromic and fluorochromic properties also. Now comes to the sensing part. This OPR PDI probe can be used to sense this copper metal ion. Firstly, the selectivity of the probe towards the metal ion. There is high selectivity of this metal ion over the other metal ions to sense of this OPR PDI probe. And now comes to the detection of copper ion. In case of copper ion, here is the hypochromic shift was observed with the color change from pink to light brown at 511 and 547 nanometer with the detection limit of 2.84 micromolar. But in case of fluorescence, here the quenching of the fluorescence take place at 650 nanometer with the detection limit of 0.34 micromolar. Now comes to the palladium species. In case of palladium species, here is the upsurge in the absorption intensity was observed due to the disaggregation mechanism. So here the detection limit observed was 3.27 micromolar, and the color changes to pale tinge of yellow from pink. And in case of fluorescence, there is quenching of the fluorescence intensity take place up to 1 micromolar. And if we further add this palladium 0 in this OPR PDI probe in 90% water, that this emission band at 650 nanometer goes towards the blue shift at a 640 nanometer with the detection limit of 79 nanomolar. So there is a quenching in the fluorescence intensity also observed with the detection limit of 79 nanomolar. This probe can be utilized for the sensing of this palladium 2 species with detection limit of 6.51 micromolar and 0.3 micromolar. And the same mechanism as palladium 0 is followed here. Now, application of this OPR PDI towards palladium species and copper ion in the solid state. In case of solid state, to sense the palladium species, there is a detection limit of 34.6 nanogram per centimeter square. And in case of copper, here is detection limit of 10.5 nanogram per centimeter square. This molecule can be used to sense these species in the biofluids with good recoveries. And further, we have used this probe for the bioimaging of MG63 osteocarcinoma cells with low cytotoxicity, biocompatibility. Here is when we see the OPR PDI probe in 90% water through the red channel, it shows the red color cells. And when we add the 100 micromolar of palladium and copper species, there is a quenching of the fluorescence intensity was shown. So now comes to the probe 2. Here probe 2 is highly selective towards the copper ion, and there is no competition was seen with other metal ions. So these are the images showing this behavior. So now the proposed mechanism of this probe 2, that is the TBP PDI probe towards the copper ion. Firstly, this OPR PDI in this native state is showing the internal charge transfer and the photoelectron transfer phenomenon. And the ICT band in the absorbance was shown at 630 nanometer, and in case of emission, it was shown as 680 nanometer. When copper metal binds to it, internally charged transfer and the PET was stopped.
Yeah, just a minute left, please.
Okay, ma'am.
this combines to this leads to on state of the fluorescence, and there is a quenching of the band at 630 nanometer, and there is a new band formed at 470 nanometer in absorbance, and in emission there is a quenching of the fluorescence at 680 nanometer, and enhancement at 480 nano, and there is a color change was also shown. This probe was further used to sense the cyanide, and when cyanide ion connected to this ensemble, it leads to enhancement of fluorescence intensity and changes from 630 to 6 nanometer, and there is a detection limits for to sense the cyanide ion, and in case of when sulfide ion binds to this ensemble, it leads to the sequestration of the copper from the pocket of the ligand. So these are the graphs showing the changes, and this is the application. These are the color changes with cyanide ion and the cyanide ion and sulfide ion towards the ensemble, and these are the detection limits.
Now comes the concluding slide.
Now come to the conclusion. I have synthesized these two probes to based on parallel diamide to sense this metal ion. So this is these are the references showing you can further connect to these. Now I would like to acknowledge my mentor, Dr. Prasanjit Singh, Dr. DST and CSR for funding, and Guru Nanak Dev University for infrastructure. Thank you, everyone.
Thank you, Poonam, for your presentation. I will request the judges to please go ahead with the questions.
Yeah, can I ask a question? Myself, Jay Murugan from my industry.
Good afternoon, sir.
Yeah, Poonam, it's really good work. I have a couple of questions. So regarding probe 1, you showed that solvatochromism is possible, but you didn't comment about whether it is positive or negative solvatochromism, and if so, what is the reason behind it?
Sir, this molecule shows a monomer and a dimer band in the if the change polarity from non-polar to polar solvent, there is a change in the band towards the longer wavelength. So there is a different in the non-polar solvent there is a blue shifted bands, and in case of polar solvent there is positive solvatochromism.
Okay, so you observe both positive and negative solvatochromism.
Yes, sir.
Okay, and in the case of probe 2, the probe 1, so the functional group like acetylene and ester, why did you choose that particular functional group, and what is the role behind choosing that functional group, like alkyne and ester? Because as per the mechanism, ester not involved, right?
Yes, sir. In case of probe 1, here is the this propagule group is very good. Palladium species is very good for the depropagulation mechanism. It can depropagulate this propagulate group palladium species. And nitrogen and oxygen are the binding site that can bind the copper ion.
Okay, thank you.
Thank you, sir.
Any more questions?
Hi, this is Shubhra. So the selectivity of probe 2 towards copper 2+ ion with respect to other metal ions, it looks really good. Is this the first time you have reported, or what, if anything has been done before, and how does your selectivity compare to those previous reports?
Yes, ma'am, I have checked the selectivity with the previous reports. This was very good selectivity over our previous reports.
Copper 2+ has already been done. This probe has probe 2 towards copper, and this work has been done before, or is this the first time you are reporting?
I'm reporting this first time, but in my lab, my seniors already reported.
Okay, so this is already there in the literature, right?
Yes, ma'am.
Okay, thank you.
Thank you, ma'am.
Okay, Poonam, I have a small question.
Yes, ma'am. Yes, sir.
So this, instead of the copper, can you just protonate this nitrogen by some acids?
Yes, sir. Protonation, there is an enhancement on fluorescence intensity take place, but the band was not as it bind with copper. I have checked the pH titrations also. I have done the pH titrations.
Okay, so you have done already.
Yes, sir.
Okay, good. Okay, thank you.
Thank you, sir.
Okay, Poonam, a quick question. This is Saptarishi.
Hello, sir.
Yeah, so what is the mechanism of your sensing? You did not say anything about that.
So this is the mechanism of sensing.
No, why is it to explain specifically for copper and not for any other ions?
So because its copper is a hard acid and it binds with the nitrogen species.
Is it the only reason?
The nitrogen has a high selectivity towards the copper ions.
Okay, and how do you determine the limit of detections?
Sir, I have multiplied the. I have taken the three readings of the ligand, blank reading of the ligand, and calculated the standard deviation and calculated the slope of the graph, linear graph, and then I have calculated this 3 into standard deviation divided by the slope.
Good. This is the it's called the 3 sigma rule.
Yes, sir, 3 sigma rule.
Okay, good. Thank you.
Thank you, sir.
So thank you, Poonam. Please
Thank you,
stop
ma'am.
sharing your screen. So moving ahead, I would like to call upon our next presenter, Mr. Abhishek Dash from IIT Hyderabad. I would like to mention that judges please note his poster number is 2323 and his title is Fluorescence and Isotropy in the Study of Physical Properties of Proteins and Membranes. So over to you, Abhishek.
Okay, so I'm audible and
Yeah, you're
visible.
audible. Yeah.
Just a minute. So is my screen visible now?
Not yet. Yeah, it's visible now. Please go ahead.
Just a minute. Okay. So hello there. I'm Abhishek and I'm going to present the poster on topic exploring biophysical properties of membranes and proteins using fluorescence and isotropy. So let's get started. So G.G. Stokes in 1852 first proposed the concept of fluorescence. He stated that the absorption wavelength is smaller than the emission wavelength. This is called the Stokes shift. So the concept of fluorescence goes like this. It is the phenomenon where a fluorophore molecule emits photons while it returns from its singlet excited state to its ground state. So here you can see that the fluorophore molecule absorbs the blue photons, which are of high energy, and it emits the photons of green, which are of low energy. And there are also cases where there is no emission of photons that leads to non-radiative decay. So it occurs due to internal conversion where the energy is transferred to vibrational modes of the electronic states, due to external conversion where the energy is transferred to collisional quenching, or due to inter-system crossing where the energy is transferred for spin reversal from singlet excited state to triplet excited state. So this is the configuration of electrons. So these are the different applications of fluorescence: molecular imaging, receptor ligand studies, pH sensing, staining of cellular components, and then drug membrane interaction. So fluorescence and isotropy. It is the phenomenon where light emitted by a fluorophore molecule has unequal intensities across different axes of polarization. So here you can see the dotted lines represent the different emissions from the typical fluorophore molecules, that is TPH. So which is a membrane probe. And these are the different emissions. So this is a typical setup for fluorescence and isotropy measurement. So the xenon flash lamp acts as an excitation source which produces light. The light gets filtered to a single wavelength at the excitation filter. It gets polarized at the polarization filter. It gets reflected by the dichroic mirror and falls on the fluorophore labeled sample. The sample then emits light which passes through the dichroic mirror. It gets split into two at the beam splitter and then gets further filtered and reaches the photomultiplier tube, where it gets transduced into electrical signals and we get the output from the computer screen. And this is the formula to calculate an isotropy. So this R represents an isotropy, and this I parallel is the observed intensity where when the two polarization filters are kept parallel to each other. And in this case, they are perpendicular to each other. So let's take a look at its mechanism. So all the molecules have a tumbling motion in the solution. So let's consider this case. This is a substrate which is tagged to a fluorophore molecule. So here you can see the substrate in its bound state, bound to an enzyme state. It rotates slowly due to its high molecular weight. So when it is excited by a polarized light, the fluorophore produces emissions which are polarized. But in case of the substrate where it is not bound to the enzyme, here you can see the molecule rotates very fast, and when excited by a polarized light, then the emissions are depolarized. So that is the major principle of fluorescence anisotropy. So you can see the different factors, how it influenced the fluorescence anisotropy. So an increase in the rotational motion, viscosity, light scattering, and resonance energy transfer, it decreases the the anisotropy value, while viscosity increase, molecular weight increase, and cholesterol percentage increases the anisotropy value. So as I discussed, and mostly they are based on how the rotational motion or rotational diffusion is affected. So let us take a look at different applications of fluorescence anisotropy and interpret its plots. So this is a typical membrane drug interaction. Here the membranes are isolated from the mitochondria and are labeled by the membrane probe TPH. So here you can see that in the control case, the anisotropy value is very high, but upon administration of the drug, this is propranolol is used to treat the high blood pressure, and this is a local anesthetic. So here you can see that the membrane fluidity increases because this anisotropy value is sharply decreases. So this suggests that the increase in membrane fluidity is due to these drugs, and it enables or facilitates its entry into the cells. So this is a cholesterol membrane interaction plot where the membranes are synthetic and they are made out of the liposomes, and it is labeled by DPH membrane probe. And here you can see that the DPPC at 37 degrees Celsius has the highest anisotropy value, followed by DPPC, POPC, and DOPC at 45 degrees Celsius. So the reason for its highest anisotropy is that the current temperature of DPPC is 37 degrees Celsius, which is lower than its transition temperature of 41 degrees Celsius. Hence, it has high viscosity and it has high anisotropy. But in the other cases, their temperature, the current temperature is higher than its transition temperature. As a result, they are having low anisotropy. But you can see upon increase of the cholesterol concentration, there is a sharp increase in the anisotropy value, which suggests that there is a decrease in the rotational diffusion, and it also suggests that cholesterol helps in rigidifying the membranes. So this is a DNA protein interaction plot. So here you can see, so here the DNA is labeled with fluorescein and it's titrated with protein, that is HMG-B1b. So here you can see that with increase in the protein concentration, the anisotropy value is increasing. So this suggests that there is a decrease in the rotational diffusion, and also suggesting that the protein molecules are getting close to the DNA molecules and hence binding to them. So this is how the DNA protein binding can be inferred from this graph. And this is a typical protein folding kinetics plot. So here the protein is labeled and its folding is observed under different concentrations of GuHCl. This is guanidine hydrochloride, which is a protein denaturant. So you can see at higher concentration of guanidine hydrochloride, the protein seems to have low anisotropy value. So this suggests that it has higher rotational diffusion due to its unfolded state. But when we are gradually decreasing the guanidine hydrochloride concentration, you can see the anisotropy value is increasing. So this is evident of the fact that the rotational diffusion has decreased.
Abhishek, just a 1 minute left, please wind up quickly.
Yes. So the protein folding is assisted when the guanidine hydrochloride is low. So this can be inferred from this graph. So the conclusion is that this fluorescence anisotropy promises to create new avenues in the field of medical diagnosis and research. So keep calm and measure anisotropy. And these are the references. And thank you.
Thank you, Abhishek, for this wonderful talk. So I request the judges to please go ahead with the questions. Any questions, judges?
Hello.
Hello, sir.
Yeah, Abhishek, first of all, are these your data?
No, sir. Actually, I have done my internship at CCMB, but I was not allowed as an intern to publish this result on my own. So I used the data from different papers and I've referred to them as here.
Because I saw that many of the data are from the book of Lakovich.
Yes, sir. Sir, I have also mentioned that same. At the introduction part, I have mentioned it from this Lakovich. And the other parts, actually, I have done my work on something else. I was studying the interaction of a new drug on the different membranes, the synthetic membranes. But due to means I'm not allowed to publish that on my own, so I'm using others. Means the referred papers.
Okay, that is fair enough. Fair enough. Do you know what is G factor?
Sir, G factor is actually a correction factor, which is also included in here. I've just shown a generalized form. So it is included here. So it actually means adds up to this, and it corrects this anisotropy value to the right one. And it is the ratio of, I guess, I perpendicular by I parallel.
Okay, thank
you.
Any more questions, or just we can proceed further? So I guess there are no more questions left. So with this, I would thank you, Abhishek, for your presentation. Now I would like to call upon our next presenter, that is Samantha Yadav from University of Delhi. Judges, please note, Samantha's poster number is 2626, and her title is Ruthenium, Complexes of Amide-Based Ligands Bearing Appended Functional Groups, Requisition Catalytic Applications.
Yeah, hello, is my presentation visible?
Yeah, it's visible.
Yeah, good afternoon, everyone. This is Samantha Yadav, and the title of my poster is Ruthenium Complexes of Amide-Based Ligand Bearing Appended Functional Group, the Characterization and Catalytic Application. So in this poster, I have included two topics. So first topic is N-alkylation of primary amines with alcohol using ruthenium complexes of pyridine carboxamide ligands. So in first topic, we have synthesized ruthenium complexes of benzthiazole and benzimidazole ligands using different ruthenium precursors in different solvents. So after synthesis, we have characterized all these 6 complexes using different techniques like nuclear magnetic resonance, infrared spectroscopy, mass spectrometry, and crystallography. These are the crystal structure of these complexes. We were not able to get the crystal structure of complex 2. We also perform cyclic voltammetry and UV visible this spectroscopy. So after synthesis, we explored the application of these catalysts, and for this we have used these catalysts for the N-alkylation of amine with alcohols. So first we optimized the reaction condition by varying the solvent, base, and temperature, and it was found that the first catalyst, complex 1 was the best catalyst in the presence of toluene as the solvent, potassium hydroxide as the base at 100-degree temperature. These amine obtained are the N-alkylated amine and are very useful in different agricultural, industrial, and pharmaceutical areas. So we have also shown the mechanism of the reaction, and there is a ruthenium hydride species formed during the reaction mechanism. We were not able to trap this during the reaction, but we prepared it independently by reacting the complex 1 with sodium borohydride. It gave us this hydride, ruthenium hydride complex, and we characterized it using crystallography, proton NMR, and phosphorus NMR. So in conclusion, ruthenium complexes have been designed and synthesized of benzthiazole and benzimidazole ligand utilized for homogeneous catalysis, and the product were N-alkylation amine, which are obtained with a greener environmental bending and cost-effective method. The second topic is I use ruthenium complexes of phosphine amide-based ligand. In this topic, also we have prepared ruthenium complexes, but of phosphine amide-based ligands. So these 3 different ligands use the synthesis. We did the characterization and obtained the crystal. We obtained different NMR like proton NMR and phosphorus NMR. Also performed the IR spectroscopy and cyclic voltammetry. So as these catalysts have labile sites, so they can be utilized for the catalysis. And this topic we have utilized these complexes for transfer hydrogenation of ketones. So first we performed the optimization of reactants, and it was found this, that catalyst 2 in isopropanol with potassium hydroxide at as the base and 80-degree temperature gave the best results. So this is the mechanism of the reaction. Here we have trapped this ruthenium hydride species in situ, and we have shown the NMR of the reaction mixture. So in conclusion, we have synthesized very bench stable NNP ruthenium complexes of NNP type ligand and successfully applied them for the homogeneous catalyst for the transfer hydrogenation of ketone. And these system tolerate both electron withdrawing and electron donating group for the phenyl ring. Thank you.
Thank you, Samantha, for this presentation. I will request the judges to kindly proceed with the questions.
Samantha?
Yes, sir. Good afternoon,
Yes,
sir.
Ramanathan from PU. Yeah.
Yes, sir.
I mean, it's a very good work.
Thank you, sir.
Samantha, can you please stop sharing your screen?
Okay, yeah, sure. Yes.
Yeah, any questions? I guess we don't have any questions.
Am I audible?
Yeah, you're audible.
Any comment on the solubility of these compounds?
Yes, sir. So they were very soluble in like chloroform, DCM, methanol, and like almost all solvents. They have very good solubility.
Okay. And the crystal structure of the second compound is not known any specific reason?
Sorry. Yes, sir. Sir, in the first topic, we tried a lot, but sir, we were not able to get good crystals. So we were able to get 5 crystals only, and not for that complex. Sir, they were not of very good quality. So. Hello.
Any other questions? Yeah, any other questions, judges? I guess we don't have any other questions for you. So thank you, Samantha, for your crisp presentation. With this, I would like to move forward to our second last presenter, that is Manveer Kaur from Guru Nanak Dev University, Amritsar. Judges, please note Manveer's poster number is 3636 and her title is Ionic liquid-based microemulsions and applications characterized by conductance, dynamic light scattering, UV visible, and fluorescence spectroscopy. So over to you, Manveer.
Is my presentation visible?
Yeah, good to go.
Okay, good afternoon to all. Today I'm going to present my poster on the topic Ionic liquid-based microemulsions and applications, which are characterized with conductance, dynamic light scattering, UV visible, and fluorescence spectroscopy. First of all, what are microemulsions? Microemulsions generally represent a class of thermodynamically stable, transparent dispersion of two immiscible liquids that are stabilized with the help of surfactant. Generally, microemulsions possesses 3 components: polar, non-polar, and surfactant, and possesses different regions like oil and water microemulsion, water in oil microemulsion, and bicontinuous microemulsion. Basically, oil in water microemulsion is known as normal microemulsion, and water in oil microemulsion is known as reverse microemulsion. Microemulsion possesses a wide area of applications in the field of nanoparticle synthesis, drug delivery, oil recovery, etc. But due to the use of organic solvents, there are certain limitations due to which these microemulsions cannot be used extensively for biological purposes like storage of enzyme, biocatalytic activities, etc. So to overcome these limitations, ionic liquid has emerged as a good substituent in microemulsions. Ionic liquids are generally defined as the compounds having only ions and melting point below 100 degrees Celsius. Ionic liquid possesses good physiochemical properties such as negligible vapor pressure, low flammability, conductive nature, thermal stability, and tunable nature. And due to its tunable nature, depending upon the choice of cation and anion, ionic liquid can be tuned into hydrophilic ionic liquid, surface active ionic liquid, and hydrophobic ionic liquid. And the surface active ionic liquid can aggregate in the form of rod-like micelles, bilayer sheets, micelle, vesicle, or reverse micelles. So here in these studies, with the help of non-polar ionic liquid, surface active ionic liquid, we have formulated microemulsions. With the help of ethylene glycol and ionic liquids, we have formulated highly thermal stabilized microemulsion and studied with the help of dynamic light scattering up to 75 degrees Celsius. But visually, we can see that these microemulsions are stabilized up to 180 degrees Celsius, because when they are heated up to 180 degrees Celsius, there occur no phase separation. So we can say that the microemulsions are highly thermal stabilized. These microemulsions are further used for the storage of lysozyme. And basically, lysozyme is stabilized in buffer up to 75 degrees Celsius. But in here, our case, lysozyme is stabilized up to high temperatures with the help of these thermally stable microemulsions. We have used stock solution of ethylene glycol to store lysozyme in microemulsions, because lysozyme remains undissolved in other components of the microemulsion. And we have studied the stability of lysozyme with the help of fluorescence and circular dichroism spectroscopy. And from here we can see that this is a fluorescence spectra of lysozyme in microemulsion, and here we can see that there occur an isobestic point. This suggests that lysozyme is present somewhere at the interface created by surface active ionic liquid and ethylene glycol in reverse microemulsion. So further, we have studied the fluorescence spectra with temperature, and we have found that lysozyme is stabilized up to 150 degrees Celsius in microemulsions. And after extraction from the microemulsion, we have found that lysozyme is found to be stabilized up to 120 degrees Celsius in microemulsions, because there is somewhat decrease in the all alpha character of lysozyme in microemulsions. So from here we infer that lysozyme is stabilized up to 120 degrees Celsius in these microemulsions. And after extraction, lysozyme is found to be active. And further, we have formulated aqueous ionic liquid microemulsions, and we have studied the different regions of this microemulsion with the help of conductivity measurements. And in these microemulsions, we have stored cytochrome C, that is also an enzyme. And with the help of UV visual measurements, we can see from here that there is somewhat decrease in the Soret band absorbance of cytochrome C in microemulsion as compared to buffer. So from here, we infer that a cytochrome is somewhat deformed in case of microemulsion as compared to buffer. Further, the circular dichroism study also indicates the deformed structure of cytochrome C in microemulsion as compared to buffer. So due to such deformation in microemulsion, cytochrome has given a very good catalytic activity in microemulsion. So with the help of UV visual measurements, we have observed the oxidation of guaiacol to tetraguaiacol in the presence of cytochrome C in microemulsions. And we have calculated the concentration of tetraguaiacol in microemulsion using Beer-Lambert law. And by applying the fit on these concentration values, we have found the rate constant values of catalytic activity of cytochrome C in microemulsions, and 5-fold increase in the rate constant value of cytochrome C in microemulsion, then buffer indicates the good catalytic activity of cytochrome C in these ionic liquid based microemulsions. From here we infer that that these microemulsions are acting as a better catalytic medium than buffer. So in conclusion, I can say that microemulsions are acting as an efficient medium for the storage of enzyme and for Y-catalysis. I would like to acknowledge my supervisor, Dr. Tejwan Singh, for supporting Professor Geeta Hundal, head of the department, Guru Nanak Dev University, for providing the infrastructure, CSIR for fellowship, and finally, I would like to acknowledge Skyrox for providing the platform to present my work. Thank you.
Oh. Okay, thank you, Manveer, for a well-framed presentation. So now I request judges to please take over with the questions.
Manpreet, Saptarshi here, very good presentation, good work.
Thank you, sir.
Can you tell us the difference between a microemulsion and reverse micelle?
Okay, sir. Actually, reverse micelle is microemulsion. Reverse micelle is one of the form of microemulsion, because microemulsion can be. I have just discussed. Here I have discussed that microemulsion possesses three regions, that is oil in water microemulsion, water in oil microemulsion, and biocontinuous microemulsion. So reverse micelle is one of the form of microemulsion where head group of the surfactant is towards inside and it's hydrophobic.
Not exactly. Not exactly. Not exactly.
What?
Reverse micelle is something without water.
Yes, you can say that also.
Microemulsion is that.
Hello?
Okay.
Hello?
When you add water to reverse micelle, it becomes, when you add water to reverse micelle, then only it becomes a microemulsion.
Yes, sir,
So
that's correct. Yeah.
Reverse micelles are not microemulsions.
No, sir.
Okay. Secondly,
okay,
are
sir,
these
thank you.
SUV?
Hello?
Are these SUV? Are these SUV, small unilamellar or multi unilamellar?
Oh, which one, sir?
Do you know this?
Hello?
Yeah, are these small unilamellar vesicles?
No, sir. I have just given a representation. These are not vesicles. I have just given a representation.
Okay. Okay. Very good.
Hello.
Hello. Hello, sir.
Where you have conducted all these studies?
Sir,
Which lab?
in my own lab, physical chemistry lab.
Okay.
Yes, sir. So do we have any other questions? I guess we're done with the questions for you, Manveer. So thank you, Manveer, for your wonderful presentation. I will request you to please stop sharing your screen. With this, I would move forward to our last presenter for the poster session, that is Ms. Sunita Behra from Veer Surendra Sai University of Technology, Burla. Judges, please note her poster number is 3737 and her title is Recognition of Bromide Ion by a protonated form of 2,1H amidazole to 3-methyl naphthalene 1,4-dione. So over to you, Sunita.
Hello, may I audible, ma'am?
Yeah, you're audible.
Okay, thank you, ma'am.
Can you please share your
My
screen?
is visible or not, ma'am?
Not yet.
Ma'am?
Not yet.
Okay, ma'am.
Yeah, it's visible now. It's visible now.
Visible, ma'am? Okay,
Yeah, it's perfect. You're ready to go.
Can I start, ma'am?
Yeah, sure. Please go ahead.
Thank you. I am Sunita Behra from VSSUT, going to present you my topic, recognition of a bromide ion by a protonated form of 1H21 in thionap, 3-methyl naphthalene 1,4-dione. The topic is based on supramolecular chemistry. As we know, supramolecular chemistry is an important field of research in environmental and biological.
Sunita, can you please put your presentation in the presentation mode? The slideshow, yeah. Can you put it?
Presentation, ma'am. How should?
Okay, that's okay. Please go ahead. Please go ahead. Please go ahead.
Okay. Okay. As we know, supramolecular chemistry is an important field of research in biological and environmental science. So, it is a wide area of research. So we have taken this area as my topic. So the ligand which I synthesized is this ligand, which contains the imidazole part and a naphthalene part. The imidazole part resembles to the amino acid of the natural protein, while the naphthalene part resembles to the vitamin K. So this ligand is resembles to a biological is very important in the biological point of view and various application, various field. So before moving further, let me explain you some of the some of the examples of imidazole compound which was reported earlier, showing anion binding properties in both solid and solution state. But before moving further, let me explain you all this binds to anion when protonated. As we know that there is a host-guest chemistry molecule, host-guest chemistry complex. So the host of the neutral molecule first get protonated to bind with the anion by electrostatic interaction. So first the ligand get protonated. So in this case, all the ligands first get protonated to bind with anion. Then the ligand which we synthesized shows a binding site. Anion sites is the imidazole part, shows various anions are bind to the imidazole part of the protonated H. That is by hydrogen bonding, as shown by different anions in this figure. So on moving further, what the reaction is going on with the ligand and the anion is shown by taking various anions. I come to consider that when the ligand bind with the suitable solvent, different anions give various product as shown in my tabulation forms. I am giving similar product, nearby similar product, but but in case of phosphoric acid, we get direct by the cleavage of the CS bond. And on moving further, when we compare with the different anions which are binding with the ligand, first we come to consider the two anions, that is chloride and bromide salt, which shows some isometric structure, which isostructure with each other. But the difference is that the hydrogen bonding interaction of the ligand and the anion, hydrogen bonding interaction of the bromide salt are slightly greater than, because it's of a larger size and larger ionic radii and have lower basicity as compared to the chloride salt. But when we consider other salts like nitrate salt and perchlorate salts, nitrate salts forms some similar hydrogen bond which is shown in this form. But in case of perchlorate and tetrafluorobromide salt, this shows a channel-like structure. So on moving further, the nitrate salt shows a two different types of tetrahedral manner by hydrogen, which is also intermolecular hydrogen bonding in a cycle manner as in these two figures. Then the chloride salt showing a isostructure compound. So what is going on with chloride and bromide salt? So giving isostructural compound. So when we study in the fluorescence spectra, we get a hydrochloric salt gives a peak at 433 nanometer. But in case of hydrobromic acid, it gives two peaks at 480 nanometer and then 480 nanometer. So the enhancement of the peak conclude us to analyze that bromide salts create a competitive environment as compared to the other salt to bind with the ligand. Then the reaction which is taking place with the bromide salt and the ligand, which results in the enhancement of the peak, is that the two peak which was obtained is due to the structure A at 480 nanometer and the structure B which is at 480 nanometer. The structure A were obtained by limited addition of the bromide salt to this ligand, and on further addition of the bromide salt, the peak enhances to 480 nanometer, which shows that there is the existence of a form of keto and enol form. The keto and enol form. The enol form binds with the bromide ion, which stabilizes the bromide ion to bind with the ligand. So, and moving further, the conformation of the bromide ion with the ligand is which come to consideration on the basis of the NMR proton NMR spectra. The three prominent peaks are observed at del is for 7.21 ppm, 7.08 ppm, and 6.95 ppm. Three peaks which you observed distinguish the bromide salts from the other salts, and then it is for homocosy spectrum. The homocosy spectrum also shows up three prominent peaks, as I told you before. out of this, the three are the two are exchangeable with heavy water to give to show us that the one that they are bonded to a electronegative atom. Then the nature of the spectrum is analyzed by the heteronuclear single quadruple correlation spectrum,
Yes,
which
Sunita.
shows that the
Excuse me, just a minute. Let please wind up quickly.
Ma'am?
Just a minute. Let please wind up quickly.
Okay, ma'am. Let me continue. It bind with the carbon atom, so that out of the 3 peaks, only 1 peak is obtained at 7.21 ppm, which shows that it binds with the carbon atom of the imidazole ring, and the 2 peaks are olefinic at CH of the enol form. So the binding constant is shown in this form. The binding, the bromide had the effective binding with the enol form of the salt. On my conclusion part, solitude of the pattern 2 compounds are different. The methyl group present in the nitrogen atom of L1 changes in the packing pattern drastically. The bromide and chloride source are the isostructure, but the effective binding of the ligand is shown by the bromide salt. The selective recognition of bromide salt by the protected form of the receptor L was observed, whereas the receptor L1 is silent towards the mineral acid. Thank you. Thank you, ma'am. Thank you. Hello.
Thank you, Sunita. Hello.
Okay.
Yeah.
Okay.
Judges, please go ahead with your questions.
Yeah, myself Jai Murugan. So, you have tried acid-based anion, right? HBr. What happens with the sodium salt or potassium salt of same? You understand?
Sodium?
If you use potassium bromide, will it bind again? Or
Potassium
acid
bromide?
Yes.
Okay. Yes. Sir, I have already shown you that bromide ion binds with the ligand.
Now, my question is, instead of hydrogen bromide, if you use potassium bromide, will it bind or not?
Since it is a supramolecular host guest molecule, so nice. I think it bind.
No, you're not studied, right? Did you study that? You're not studied.
No, sir, not that much.
Okay.
I'm not
Okay.
related that.
Yeah, another point. See, what is the use of detecting bromide ion? See, usually fluoride ion is extensively studied because fluoride causes fluorosis disorder disease. As far as I know, bromide is quite not dangerous. What is the purpose of studying binding with bromide ion? You understand?
Sir, since sir, I have taken bromide because I have taken, but fluoride is a very reactive substance. So the ligand which I synthesized is effectively bind with the bromide and chloride, but the result which you obtain is by bromide. That is why I have taken bromide ion.
No, I understand. Did you also study fluoride ion? Because fluoride ion detection is a very important area. Maybe your compound is sensible for fluoride also. Did you try?
No, sir, I have not tried. But since this is my first year, I'm going on.
Okay. Fine.
Okay. Yes.
Fine. Thanks.
Okay, sir.
Okay, Sunita.
Okay.
Hello, Sunita.
Yes, sir.
Hello, Sunita. This is Natarajan. Take it.
Yes.
So you have shown something like a fluorescence spectrum, emission spectroscopy.
Yes, sir.
Emission spectroscopy. What kind of luminescence that one? Whether it's from a singlet or triplet state?
The singlet state. Not
Singlet. How quinone can give the singlet emission in room temperature? Is there any quinone so far?
Sir, I am not able to understand the question.
This is the emission spectra, no? Which you are showing the emission spectra.
Yes, sir. Yes.
So if it is the emission spectra, then quinone, how this can give the fluorescence? You have to check the details and slightly the temperature.
Sir, the binding is taken place with imidazole proton. So the naphthalene part is not taking part in the binding. So the imidazole part is taking in the binding with the ligand, binding with the element. I have shown that.
I agree with you. My concentration is your emission spectra. What kind of emission you are getting, why that has been taking place, which state has been, whether it's a singlet state or triplet state. Are you getting?
No, sir.
Okay. Yeah, I mean, you have to look on the state which has been involved. Normally, quinone never can give emission from singlet state.
No, sir. Okay.
Okay. It's a triplet state emission which will be temperature sensitive.
Achha. Okay, sir.
You have to try to look on the, I mean, particularly with the help of NMR, you may can able to do some titration, I think.
Okay, sir.
Yeah, good.
Okay, sir.
So thank you, Sunita, for the concluding presentation for the session. So this marks the end of the poster session. It was indeed a very lively and informative one. Judges, please note that Yatin has already shared the details to submit the scores with you on your email IDs. So I request you to compile your scores and send them to us as soon as possible. With this, on behalf of the entire organizing committee, I would like to extend a hearty thanks to all the judges who spared out their time to shortlist and then eventually judge the posters as well as demonstrations. I thank you for gracing the conference with your contribution. We are highly obliged. With this, I will request Priya to take over.
Yeah, thank you, Simran. Priyal, sorry to interrupt. I would personally like to thank all the judges. They have done like recommendable job. They have devoted so much time in shortlisting. I think around 37 posters they shortlisted to 12, and then they were present in the audience, had asked so many questions from all the shortlisted participants. So I personally wanted to thank all the judges. Thank you so much for your support and for your time. Okay, over to you, Priyal.
Thank you,
Thank you,
Bindya.
sir.
Thanks.
Thanks.
Okay, so hereby we are finishing with the first session of the day. Now we will have a lunch break for about an hour. Join us back around 2:40 p.m. We will then start with the second session, and the feedback form will be able to fill that one. Thank you.
The feedback form has been shared and it will remain open for another 10 minutes. We are going to start sharp at 2:50 as Priyal said. So we'll take a short break. Sorry, 2:40 as Priyal said. So we'll start sharp at 2:40 again. Thank you.
ਨਾਨਕ ਨਾਮ ਦਾ ਤਾਜ ਇਲਾਹੀ ਸੀਸ ਸਜਾਵਣ ਵਾਲਾ ਜਿਸ ਦੀ ਹੋਂਦ ਚ ਸ਼ਬਦ ਗੁਰੂ ਦਾ ਜਗੇ ਪੁਨੀਤ ਉਜਾਲਾ ਸਦਾ ਸਦਾ ਪੁਰ ਨੂੰ ਨਾਨਕ ਨਾਮ ਦਾ ਤਾਜ ਇਲਾਹੀ ਸੀਸ ਸਜਾਵਣ ਵਾਲਾ ਜਿਸ ਦੀ ਹੋਂਦ ਚ ਸ਼ਬਦ ਗੁਰੂ ਦਾ ਜਗੇ ਪੁਨੀਤ ਉਜਾਲਾ ਸਦਾ ਸਦਾ ਪੁਰਨੂਰ ਰਹੇ ਸਦਾ ਸਦਾ ਪੁਰਨੂਰ ਰਹੇ ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ ਸਦਾ ਸਦਾ ਪੁਰਨੂਰ ਰਹੇ ਪੁਰਨੂਰ ਰਹੇ ਪੁਰਨੂਰ ਰਹੇ ਗੁਰੂ ਨਾਨਕ ਦੇਵ ਵਿਸ਼ਵ ਵਿਦਿਆਲਾ ਅਨਹਤ ਨਾਦ ਬਜੇ आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्व विद्याला धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप देव विश्व विद्याला गुरु नानक देव विश्व विद्याला चिंतक सिरजक रसक विनोदी सहज निमर विसमादी निर्मल निर्भव सच दा खोजी विगसे आद जुगादी रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्व विद्याला गुरु नानक देव विश्व विद्याला ओटने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओटने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला गुरु नानक देव विश्व विद्याला 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 नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे गुरु नानक देव विश्व विद्याला गुरु नानक देव विश्व विद्याला सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्यालय। अनहत नाद बजे आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे। सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्यालय। धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे। सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरु वाक उजाला सदा रहे परगास रूप। गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय। चिंतक सृजक रसक विनोदी सहज निमर विसमादी निर्मल निरपौ सच दा खोजी विगसे आद जुगादी। रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला। गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय। जिथे मिलदी ओटने ओटिया पौंदे मान निमाणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे। जिथे मिलदी ओटने ओटिया पौंदे मान निमाणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे। ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला। गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय। नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला। सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे। गुरु नानक देव विश्वविद्यालय गुरु नानक देव विश्वविद्यालय। सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्यालय। अनहत नाद बजे आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे। सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्यालय। धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला चिंतक निर्मल निर्भव सच दा खोजी विगसे आद जुगादी रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला अनहत नाद बजे आहत जलन बुझे अमृत शब्द वरे तन मन थीण हरे सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप देव विश्वविद्याला गुरु नानक देव विश्वविद्याला चिंतक सृजक रसक विनोदी सहज निमर विसमादी निर्मल निर्भव सच दा खोजी विगसे आद जुगादी रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला जिथे मिलदी ओट ने ओटियां पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओट ने ओटियां पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे ओथे नदर मेहर दी होवे ओथे नदर मेहर दी होवे जिथे नीच समाला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे गुरु नानक देव विश्वविद्याला सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला अनहत नाद बजे आहत जलन बुझे अमृत शब्द वरे तन मन तीन हरे सदा सदा पुरनूर रहे पुरनूर रहे पुरनूर रहे गुरु नानक देव विश्वविद्याला धरती अंबर पवन समुंदर सूरज चंद सितारे एक दी तुन विच गावन वावन राग इलाही सारे सत सुहान सदा मन चाओ सत सुहान सदा मन चाओ एह गुरवाक उजाला सदा रहे परगास रूप गुरु नानक देव विश्वविद्याला गुरु नानक देव विश्वविद्याला चिंतक सिरजक रसक विनोदी सहज निमर विसमादी निर्मल निरभव सच दा खोजी विगसे आद जुगादी रोशन हो वंडे रुशनाई रोशन हो वंडे रुशनाई दिखया पावन वाला गुरु नानक देव विश्व विद्याला गुरु नानक देव विश्व विद्याला जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे ओह दर उसदा ओह कर उसदा एह गुरवाक वखाणे जिथे मिलदी ओट ने ओटिया पौंदे मान ने माणे
Can you hear me?
Yes, sir.
Oh, okay.
Yes. So hi, yeah, okay. So maybe we can start in another 3 minutes or so. Hi, Professor Kar.
Yeah. Hello.
Hi, Venus.
Hello. Hi. Hi, Professor Kar.
Hello. There is no audio from your side. Vindhya, I think there is no audio.
Yeah, I'm talking to my kids.
Oh, okay, okay, okay.
Real, I think maybe we can start because the first speaker is already here.
Yes.
Okay.
Okay. So we welcome you back. Hope you all are recharged to grasp the remaining talks. This session includes 3 scientific talks and a felicitation program. So here I invite Dr. Veena Singh Mittu, convener of Cyrox Club and assistant professor at Department of Chemistry, GNDU, Amritsar. His specializations include structural biology and biophysical chemistry. At present, he is at Max Planck Institute of Biophysical Chemistry, Germany, He is an integral part of CyROX and is always at the forefront for smooth functioning of all the activities. He will be chairing the second session of the day, so I would request Dr. Venus to start the session. Over to you, sir.
I see Venus is having some problems with his internet connection. He just dropped me a message. So
he has rejoined now.
Yes, he has rejoined. If he has problems, then I can take over. That's no problem.
Yeah, my connection is having some problems. I understand. Yeah.
Venus, maybe you can
Could we start?
with this. Yes. Yes.
All right. So yeah, so welcome everyone for this second session of the last day of the student conference, which is being organized by the student club of Guru Nanak Dev University, Amritsar, in collaboration with CRSI and other bodies. And it's been a really my pleasure to be here and act as a chair of one of these sessions. And this session, which we are going to have now, will have two speakers. The first one is Dr. Prasanjit Kar, who is an associate professor at IIT Roorkee, and who will be talking about carbon nanotube particles and their applications in sensing purpose. And this will be followed by a lecture by Dr. V. Ramanathan, who is working at IIT Varanasi, BHU, basically. And he'll be talking about probing disulfide bond by surface enhanced Raman spectroscopy. So we are really looking forward to both the lectures. And first of all, I will invite Dr. Prasanjit Kar to present his lecture, and I'll give a brief introduction about him. And yeah, so Dr. Prasanjit Kar has completed his graduation from and master's from India, and after that he did his doctorate from Central Salt and Marine Chemical Research Institute, CSMCRI, Bhavnagar, in Gujarat, under the supervision of Dr. Amitabh Das, and he completed his doctorate in 2010. After that, he went to Ohio State University for his postdoctoral studies in 2010. And in 2011, he was awarded with the Humboldt Fellowship, and then he moved to University of Ulm to do his further postdoctoral studies with Dr. Peter Burrell. And in 2013, he decided to come back to India and joined IIT Roorkee as an assistant professor, and he has been working there since then, and he was promoted to associate professorship in 2019. He's a member of Royal Society of Chemistry and American Chemical Society, and yeah, so he has done, his main areas of interest are inorganic nanomaterials, perovskite materials, and their applications in photonics, sensors, and energy. And so I'll now invite Dr. Kar to please deliver his lecture. Dr. Kar.
Thank you, Dr. Venus, for your nice introduction. I have never met you, so it is a nice meeting.
Yeah, same here. I've been listening about you from Parul since last 4 or 5 years, and and yeah, so Parul is also one of the organizers in this conference. He has been helping us or guiding the students to mentoring them and how to organize.
Yes. Just a few days before she graduated from here, she got her degree.
Yeah, she recently got graduated. Congratulations to you and her, both of you.
Okay, so I'm sharing the slides now. I think the slides are visible.
Yeah, please carry on.
Yes. Okay. So today I will talk about carbon nanomaterials. One correction from my side. Actually, today I'm going to talk about carbon nanomaterials, carbon nanoparticles, not carbon nanotubes. Okay. This is a small correction from my side. This lecture will be basically for the UG students and PG students. And for some, to some extent, for the PhD students also. So my lecture is comprised for the carbon nanoparticles and their applications in sensing purpose. So before going to discuss about this carbon nanomaterials, we'll talk about a little introduction on nanomaterials or nanocrystals, quantum dots. These nanomaterials are actually nano-sized materials, which is in the range of 100 to 200 nanometer. We say it is nanomaterials. If the material is crystalline in nature, then we say nanocrystals. And we will talk about quantum dot. Quantum dots are actually basically smaller in size than nanomaterials, nanocrystals. It comes in the range of 4 or 5 nanometers, or maximum it goes to less than 10 nanometers. So now my group is involved in organometal halide perovskite synthesis and their characterization and their applications. But today's talk will be basically for the carbon nanomaterials. This nanomaterials actually has a broad application. For example, this nanomaterial can like carbon nanotubes or some dye molecules, some protein molecules interacted with nanomaterials, organic LED devices, or some inorganic LED devices, molecular cell assemblies. All these applications are actually is a vast application. It can be divided into several categories like energy resources, environmental studies, health. So nanomaterial is nowadays big scope for the PhD and means for the research purpose. So my lecture is on carbon nanomaterials. So if the nanomaterial or nanoparticles, the size of the nanoparticles are very less, then we say the quantum dots. Okay, so quantum dots are only few nanometers wide of some materials. It is so tiny that it is effectively concentrated into a single point. So instead of saying one-dimensional, two-dimensional, we say it is a zero-dimensional. Okay, so these quantum dots are just like a points. Okay, just like some dots. That is why we say the quantum dots, and some more physical properties it has to maintain, like it has to be quantum mechanically confined, and some that this part will come later. And for the carbon quantum dots, if the carbon nanomaterials are in the size of less than 5 nanometer, we say these are carbon quantum dots. But there is some debate about this one. Some scientists says that carbon, this quantum dot, we should not say carbon quantum dots, we should say carbon dots, something like that. But taking apart all these controversies, we say it is a carbon dot. Okay. So this carbon quantum dots are first discovered in 2004. Means it is there, but it is someone discovered, like Professor Zhu discovered this one accidentally during the purification of single wall carbon nanotubes. So synthesis of single wall carbon nanotube, there is a lot of different methods for the synthesis of carbon nanotubes, like arc discharge method, laser ablation method. So during this synthesis of carbon nanotubes, some particles, carbon chunk particles are also there. They have found some chunk of carbon particles, and they say that these particles are nothing but carbon quantum dots. And what are the properties for this carbon quantum dots? These carbon quantum dots are highly stable in nature. Their conductivity is very good. They are low toxic in nature, and the most important thing is they are environmentally friendly. So it is easy to handle of these carbon nanomaterials. Now, before going to discuss about the nature of characterization part of this carbon nanomaterials, we should come to the spectroscopic part, because this this conference is basically based on the spectroscopy. But in previous lectures, we have learned a lot of knowledge actually from different parts of the spectroscopy. But here, I will talk about a material with different spectroscopic methods. Okay. Now here we see the Jablonski diagram, where there is if a material or molecule is in the ground state, it can absorb a particular amount of energy in form of light. then it can go to excited state. It can go to any excited state, and then if comes to the lowest excited state, then we say it is the internal conversion process. There is a vibrational cooling also, and from this singlet excited state to, if it comes to the triplet excited state, then we say it is intersystem processing. And if the energy is dissipated from the singlet excited state and it comes to ground state, then we say it is fluorescence. Otherwise, in other case, is from triplet to ground state, we say it is a phosphorescence. Here, for the nanomaterials, there is a beautiful spectroscopic studies for these nanomaterials. If we change the size in normal cases for any molecule, if we excite this molecule, it absorbs this molecule, it will absorb at a particular wavelength, and it will emit from from one particular wavelength. Okay. But if we change the excitation wavelength, there will be change in the intensity of the emission wavelength, but there will not be any shift from the emission wavelength. But for these nanomaterials, this is very exciting. For any type of nanomaterials, nanoparticles, if that nanoparticle is emissive in nature, if we change the excitation wavelength, there may be a shift in the emission wavelength. That depends on the size of the particles. Okay, if there is different size of particle is mixed in a solution, we can get a variation in the emission wavelength. For example, if we have a larger particle, for this one, for the first case, the band gap is very low. And if the particle size becomes smaller, then band gap is larger than the previous one. And if we have a very tiny particle, this band gap will be very large. Okay, so if it is large, if the band gap is very large, we will get emission from higher energy, or we can say from lower wavelength. And here is the one graph which is showing the band gap of PBSE, lead selenide, is actually decreasing with increasing radius of energy actually is decreasing with increasing radius. So here we have nanoparticle, any kind of nanoparticle. If we excite this one from ground state, it will go to excited state and then it will come here again, because this no material can stay in the excited state for longer time. Okay, it has to emit or it has to dissipate the energy by any form, and then it has to come back to the ground state. Okay, so here, if there is one particle that is absorbing, and then there may be several states, and we get the emission from several states. Okay, so we will come, what are these different states? We say these are the surface states. Now, for the synthesis of carbon dots, carbon quantum dots, there are several methods, several technology, or several resources are there for the synthesis of carbon nanodots. Okay, here one template synthesis is there, where one organic molecule, this gray colored sphere is the SiO2, and it is actually covered by some organic compounds. And then if we heat this one, it will polymerize, and with excess heating, it will pyrolysis, there will be pyrolysis, and these organic molecules actually decompose, and it will create some carbon chunk particles. So here you see carbon particles are on the surface of this SiO2. So it makes a composite kind of thing. After etching, this SiO2 will go and we will get carbon dot. After oxidation and passivation of these carbon dots, we will get fluorescent carbon quantum dots or carbon nanodots. So these carbon nanodots are very useful for different applications. Like here we have given one application for water splitting, and here it is for stimulated emission of radiation. And these are, you see, different applications. Like this blue dot, I have given some different colored dot. Here it is blue, green, yellow, red, and gray. Okay, so actually these carbon dots, if we change the size of the particles, we can get different colored emission from this carbon dot. And this is given by this image. Now, the synthetic process for these carbon dots, there are several technologies, several techniques for the synthesis of carbon dots, like electrochemical synthesis, combustion, thermal, hydrothermal, and acidic oxidation. Supported synthetic procedures, like we need some supported synthetic like SiO2, then microwave analysis, microwave synthesis, and some other chemical methods are also there, like plasma treatments and electrochemical analysis. For electrochemical analysis, if we have two graphite rods which is immersed under some water solvent, and then if we pass electricity between this graphite rod, we will get a black colored solution. Okay, this is the carbon solution. If we analyze this carbon solution, we will get this is a TEM image which shows the small particles of less than 5 nanometer in size. These are the carbon dots. This is another method for the combustion process, combustion of thermal, hydrothermal process. Here, this is acidic oxidation. Here, carbon nanotubes or graphene sheets or graphite sheets are there, which is digested by H2SO4, H1O3, and we get carbon carbon dots. Now, this is another procedure where like it is supported synthesis, like mesoporous silica is there. So it is a porous material, and if we keep this porous material in citric acid solution, then if we digest this one or if we heat this one, carbon material will be, carbon nanodots will be synthesized, will be prepared inside the core of the pores. Okay, so there is one advantage for this kind of synthesis. So these carbon materials, actually the size of the carbon materials we can control by controlling the porous size of this mesoporous silica. Okay, these carbon materials cannot be larger in size than the pore size of this material, and there will be sometimes this, if we prepare the carbon particles by different procedures, they can agglomerate or they can form aggregates. But here in this method, by supported synthesis, we will get discrete carbon particles. They will not be aggregated or agglomerated. Okay, now the microwave or ultrasonic synthesis. In microwave synthesis also, if we take glucose particles and if we keep on heating in microwave, with increasing microwave heating time, the carbon nanoparticles will slowly grow. So first, at the initial stage, this is the glucose particle, and now with increasing microwave heating time, a small nucleation is there, and then there is a growth of these carbon particles, and this is the larger carbon particles. So this is one synthetic process, and then the template synthesis. Template synthesis is nothing but formation of self assembly and using formation of micelles, and then etching the template to get the carbon nanoparticles. So these carbon nanoparticles have unique properties, fluorescence properties, emission properties. What happens? So this is the carbon particles generated from graphite or graphene sheets. So some functional groups are there. So when you heat one particle from any source of the materials, like any glucose or any kind of carbonaceous source, we will get carbon particles, but at the surface of the carbon particles, there will be some functional groups like amine or acid or hydroxyl groups. Okay, so these groups actually creates some defects inside the material. So these defects create some surface states just below the excited states of the excited state. And from this excited state, the emission can happen and we get lower emission intensity, lower energy emission. Now, if we passivate these surface states, what will happen? These surface states will no longer available for the emission. So whatever emission we will get from here only, from the lowest excited state, and there will be no change in the wavelength after excitation with different wavelength. So we will get the emission from the same wavelength. Now here, one synthetic procedure, for example, citric acid with urea. So this is a hydrothermal synthesis, and we get initially there is an aggregation and then carbonization process starts. So these are the carbon materials, and they have characterized these carbon materials by several techniques like TEM analysis. They have shown these particles are very tiny. It is less than 5 nanometer in size. Then surface functionalization groups are there, functional groups are there. They have done by IR studies. And here, this also, the XPS analysis also, that I'll come later for my own studies. Now from graphite or graphene nanoplatelets, if we have graphite or graphene sheet and we digest with sulfuric acid and sodium nitrate in presence of KNO, there is several steps, several procedures, steps I have to cover, and then after centrifugation we will get supernatant and precipitate. This supernatant liquid is actually fluorescent in color, and it is the carbon nanomaterials or carbon dots. And the larger particles are also carbon dot, but they are in the bulk, bigger in size. Now, graphite sheet, when we, this is the daylight image of the graphite sheet, which forms the carbon nanomaterials. And this is the 10 images of different carbon nanomaterials. Like from this characterized, they have characterized this one to get carbon dots or carbon particles. They have studied by TEM analysis. Here, this is the citric acid with urea. They have synthesized in different ways. Like first one is microwave analysis. They have done in microwave, they have heated in microwave, and it is normal pressure. They got a brownish melt. Here, if there is no evaporation, microwave synthesis at high pressure in sealed vessel, they got a brownish solution. So this solution after dialysis, they got a green color carbon particles. But here, with this brown solution after dialysis, they got blue colored solution. So we can tune the emission properties of these carbon materials just by changing the synthetic procedures, just by changing the workup procedures. So we can get different colored emission from the same carbon particles. Of course, there is some functional groups are also involved, which gives the defect states, and that will come later. Now here, the citric acid is the citric acid. Now, if they have used amine, some primary amines, here ethylene diamine, they have used citric acid with ethylene diamine, heated at 200 degrees centigrade for 5 hours, they got carbon dot along with some fluorophore. And here the fluorescence is very high fluorescence with 53% quantum yield. Now, when they have treated this citric acid with some caged compound with the same reaction condition, the fluorophore is quite different. And here they got very less emission, on quantum yield is only 17%. And if they have treated this citric acid with some tertiary amine, then with the same reaction condition, the emission quantum yield is very, very low. It is nearly 7% only. So just by treating with different ligands, they got different quantum yields, different emission intensity with same color. So we can tune the color, we can tune the intensity, whatever we want. We can. There is a variety of scopes actually with these carbon particles. Here they have used these carbon particles for as a fluorescent tint. This is just a cotton thread, and they dipped this cotton thread in carbon dot water solution. So this carbon dot is actually biocompatible. So it goes in water solution also, water also. Now, if we make a water solution with these carbon particles and we dip the cotton thread, we'll get emission of green color as well as from red color just by changing the excitation energy. And if there is they have dipped a seed in carbon dot solution, and there is a growth in the seed, that is proving that this carbon dot particle are actually biocompatible. It is not toxic at all. And for the security purpose also, this carbon dot can be useful. They can use this carbon dot as fluorescent tint. Now, if you take just milk and you just heat this milk at 180 degrees centigrade for 2 hours, you will get a fluorescent carbon particles from this milk. Okay, it is very synthetic procedure is very easy. You just heat it in a bomb reactor, in a autoclave. Here, this is another procedure from guava. You just take the pulp of guava and heat it. You will get the carbon particle. You take the red pepper, you heat it. Just hydrothermal synthesis. You just heat in butter solution, heat the water solution, extract in butter. You will get the carbon dot solution. Here it is just peas. You heat the water extract of the pea. Peas. You will get carbon dot solution. Here this is the spinach. So these are the references where they have clearly disclosed that carbon dots can be synthesized from guava, from red pepper, from peas, from spinach, and here it is for the mango pulp. So from this mango pulp, they can prepare different colored carbon dot solution. So in daylight, the color of the carbon dot solution is almost colorless or yellowish in color, but under UV light, it will give blue or red or green emission. So it can, if there is a RGB, blue, red, and green emission, we can cover all the colors actually just mixing different types of materials, different sizes of materials. Here, they have synthesized this carbon materials from orange juice. Take the orange juice, heat it at 120 degrees for 2 hours, you will get some particles, now carbon particles. Now, if you centrifuge this with the speed of 10,000 RPM, you will get smaller particles. If you centrifuge it with a speed of 3,000 RPM, you will get larger particles. Both the particles are actually fluorescent in nature, but the smaller particles will give high fluorescence under UV light, but this larger particle is less fluorescent in nature. If you heat the cyclodextrin, if you treat the cyclodextrin with HCl at 70 degrees centigrade for 4 hours, you will get carbon particles. So it is very informative actually. If we use cyclodextrin in any reactions and if you heat it, so we should be careful that some carbon particles can be generated, and that will give the fluorescence. So if we, for any chemical reaction, if we get the fluorescence, it may be confusing that this fluorescence is coming from these carbon particles or from something else. Now, there is two types of carbon particles. One is solid fluorescence carbon particles, another is hollow fluorescent carbon particles. Solid fluorescence carbon particles are generally synthesized by different techniques like arc discharge method, electrochemical synthesis, laser ablation method, and then hydrothermal synthesis, acid digestion. So we will get hollow fluorescent carbon particles. But for hollow fluorescent carbon particles, there is a specific method. Like if you have acetic acid, you mix it with water, you prepare one acetic acid solution and pour this acetic acid solution in P2O5. So what will happen? P2O5 actually is it gives very means exothermic reaction. So heat will be generated immediately. There is a sudden heat generation, and acetic acid decomposes, and since water is there, it forms small bubbles are generated. So carbon particles are at the surface of this small bubbles, and then it gives a hollow structures of the carbon particles. At the same time, polyphosphoric acid will be generated from P2O5, and this behaves like a catalyst for this reaction, and then this bubble actually gives a template for the hollow fluorescent carbon particles. Now we get hollow fluorescent carbon particles and then water. So it is a cyclic process actually. So if you mix acetic acid water in P2O5 solution, you will get hollow fluorescent carbon particles. So we have used this hollow fluorescent and solid fluorescent carbon particles for our study. Here, what we have taken Indian jamun. Okay, so at the beginning, actually, when I started my research work, independent research work in IIT Roorkee in 2014, I had nothing in my lab. So I thought that I will start, since my postdoc experience was on solar cells, I started thinking about some solar cell studies. So I took the jamun, I extracted the jamun, and I thought that I will do something on solar cells. But when I heated this jamun extract, and first initial state, I had to do the UV absorption and emission studies, and I see that emission studies actually it is giving emission because I heated this material. So I got some emission. So I told my students, you excite a different wavelength. See, he actually initially he did not get emission. So he excited different wavelength, and he got emission at different wavelength. Now, what happens? When this jamun extract, we poured in P2O5 solid, and then there is a you see the bubbles are coming, means fumes are coming, and after filtration we get a clear solution. If we keep this clear solution under UV light, we get very high fluorescent emission from this solution. So these actually the hollow fluorescent carbon particles are generated. Okay, so this is the absorption data, which shows two different types of fluorescent carbon particles, hollow fluorescent and solid fluorescent carbon particles. But this strong band is actually giving the excitonic band. So what is excitonic band? Now, when we excite a molecule, a particle, electron, actually there is a hole and electron separation. This hole and electron are in Coulombic interaction. When they are in Coulombic interaction, we say it is exciton. When they are far apart, we say free charge carriers. Okay, so here this strong band is actually indication of the exciton generation. And from the hollow fluorescent carbon particles and solid fluorescent carbon particle, if we excite at different wavelengths, we are getting emission from different wavelengths. So it gives a rough idea about the surface states, creation of surface states or presence of some defects. Here, from Mayer studies, we have shown that several functional groups are present at the surface of these carbon particles, like 1648 centimeter inverse. Sorry, here it will be centimeter inverse only. So 1648 centimeter inverse, we get a band for C double bond O, and here a broad band, it indicates the presence of OH group, OH functionality. Okay, now here, this is the Raman spectra. Here at 1385 and 1596, two bands are generated for solid fluorescence and for hollow fluorescence carbon particles. In both the cases, two bands are generated. One band at 1596 or 1595, we say it is a G band. One band at 1385 or 1395, we say it is D band. So G band is basically for the defect states for the SP2 SP2 defects, and D band is for defects for the SP3 defects. So these two actually IG by ID, but there is a ratio. We can calculate the ratio for the intensity ratio IG by ID, and from there we can say whether this material is crystalline in nature or not. From this, this is the time correlated single photon counting spectra, which gives average lifetime of 9 nanoseconds for the hollow frozen carbon particles and nearly 6 nanoseconds for the solid frozen carbon particles. This is average lifetime. There's some radiative decay kinetics are also involved. Non-radiative decay kinetics are also involved. Radiative decay kinetics gives the indicates that the emission is from the allowed transitions, from allowed states, and non-radiative decay kinetics actually gives the indication for the presence of some surface states or defect states, which actually quenches the emission very quickly. So the emission, if you see the rate constants, radiative rate constants and non-radiative rate constants, the non-radiative rate constants are faster. It is in the order of 10 to the power 8 per second, second inverse. So it is very fast, and it gives the presence of the surface states as a defect states. Here the XPS studies are actually basically the elemental analysis, and which shows the presence of oxygen, carbon, nitrogen for the hollow fluorescent and solid fluorescent carbon particles. So these all are the XPS analysis, deconvoluted spectra for the XPS. And this from here, if we deconvolute it, we will get different bands for the CC band, CO band, and C double bond O band. Okay, for TAME analysis, we have done hollow fluorescent carbon particles as well as for solid fluorescent carbon particles. From ACM scanning electron microscopic analysis, we don't find any interesting result because the particles are so tiny that from ACM analysis it's very hard to determine the particle size. But from TEM analysis, for the hollow fluorescent carbon particles, it is fairly evident. You see there is a hollow cavity is there for the hollow fluorescent carbon particles, and this is for solid fluorescent carbon particles. And next slide I will show the solid fluorescent carbon particles also. This is the particle size distribution. Here some fringes are there, which indicates that the particle size are actually crystalline in nature. This is the TAME image for the solid fluorescent carbon particles. Here, see in the previous slide, there is a void space is there for the for these carbon particles, but in this case there is no void space. Okay, so these are the solid fluorescent carbon particles, and the particle size distribution is almost is better size distribution is good for the solid fluorescent carbon particles. Now, what we have done with our material, we extracted the jamon, we heated this one, we got the solid fluorescent carbon particles. Now we tried to prepare some fluorescent ink from this jamon extract, and here we made this is a paper where we wrote IITR, and under UV light only it is visible, so it can be useful for security purpose also. Not only that, for biological studies also, we have taken some biological cells. Of course, it is in collaboration with our biotech department, and we have done some biological studies, and we see that the hollow fluorescent and solid fluorescent carbon particles are actually biocompatible. We can use these materials for the for cell fluorescence, and there must be some must be some concentration dependent. For example, for this study, this is the control, and when we add sample A, like solid fluorescent carbon particles, so this is the cell viability test, and most of the cell, almost 60% cells are alive. But in case of hollow fluorescent carbon particles, with increasing concentration of the carbon particles, there is a decrease, cells are dying. So it gives information that up to 15 microgram per liter per ml, it can be useful for the study. But for the solid fluorescent carbon particle, this is for the hollow fluorescent carbon particle, but for the solid fluorescent carbon particle, you see, in this case, for 15 microgram per ml, there is it is almost 100%. So there's all the cells are alive. And for 30, if we use 30 microgram per ml, still we can use this one for some living cells. So from this data, we can conclude that hollow fluorescent carbon particles are actually toxic in nature than solid fluorescent carbon particle. Why? During the synthesis of hollow fluorescent carbon particles, we have used P2O5, which reacts with water to give polyphosphoric acid. This polyphosphoric acid, we are not separating this polyphosphoric acid from the solution. So this polyphosphoric acid is actually present in the solution, which gives the toxicity for the cell viability test. Not only that, we have found some application of this carbon particle for ion sensing. We have actually used several cations, cationic solution. We have added some metal ions in carbon solution, carbon nanoparticle solution, and we see in only 1 or 2 cases, like here, only iron 2 or iron 3, in both the cases, we see there is a quenching in the fluorescence of the carbon particles. And we have done the titration studies also. From Stern-Volmer equation, it does not give the information whether this is a static quenching or dynamic quenching, but if it is a static and dynamics mixed together, then only we will get a curved structure. Otherwise, for the static and dynamic in both the quenching, we'll get a linear curve. So not only so this is the ionic studies for the solid fluorescent carbon particle, and that was the ionic studies for the hollow fluorescent carbon particles. In both the cases, we see that with the iron solution, iron Fe2 plus or Fe3 plus, in both the cases, actually the emission is quenched. So this is the final data for hollow fluorescent carbon particle and solid fluorescent carbon particles with anions. And we found that for some anion like fluoride ion, it senses. For ammonium ion also, with ammonia also, there is a change in the intensity. So it is for both the studies, for hollow fluorescent and for solid fluorescent carbon particles. Now, here, what we have done at the beginning, we synthesize these carbon particles and we excite it at 95 nanometer. We get the emission at 435 nanometer. Now, if we add iron solution in this carbon dot solution, there is a quenching. Now, if we add ammonia, again we are getting fluorescence from that. Or if we add fluoride ion, we'll get the emission from there. So we propose that there may be a strong complex formation with ammonia and iron. So iron is actually coming out from the solution, and we are getting the fluorescence emission from these carbon particles. Here with fluoride also the same thing is happening. Iron is forming fluoride complex, and these carbon particles are actually free, and these particles are giving emission. So these are the spectrum studies for hollow fluorescent and solid fluorescent carbon particles. Now, using this concept, we prepared fluorescence on-off on switch. So this is a kind of molecular switch device kind of thing. So switch means once we switch it on, we will get the emission. If we want to switch it off, if we off it, we will not get emission. Here is the same thing. Here we got this anthocyanin dyes are there. So in jamun extract, 5 different types of anthocyanin dyes are there. So all are mixed together. So it is very hard to separate all these anthocyanin dye from jamun extract. So we have tried to separate this by HPLC, but it is in vain. Okay, we could not able to separate the different types of different anthocyanin dye from jamun extract. So what we did, we heated this one and we got frozen carbon particles. So these are the solid frozen carbon particles, and this is the characterization process where we got the same studies. But here, this image, it shows the fluorescence image of the solid frozen carbon particle without adding any amine. Okay, but if we add a primary amine in the same solution, what will happen? Here you see, if we change the excitation wavelength, we are getting emission from different wavelength. But here, after addition of amine, if we change the excitation wavelength, we are getting the emission from the same wavelength, but the intensity is different. Okay, so that means the surface state here, the surface states or defect states are passivated. Now this is the TAME image for that one. This is the hollow fluorescent carbon particles, which shows the crystalline properties. And here the polycrystalline properties, actually the ring structure gives the polycrystalline nature. And in biological cell also we have done, and we see these fluorescent carbon particles from anthocyanin dye are cell viability test. It is showing that these materials are actually biocompatible in nature. We can use this material for any therapeutic drug delivery system. Here, from this anthocyanin dye, whatever carbon particles we have synthesized, these materials are actually sensing iron. It is iron 2 or iron 3. It is sensing both. So using this concept, we prepared, so this is the characterization techniques with iron. And then using this concept, we actually tried to prepare some hemoglobin sensor, because iron is present in hemoglobin. So what we did, we took, we actually purchased one hemoglobin, and in iron's carbon dot solution, we added that hemoglobin directly, and we see there is a quenching. So now we have to prove that the quenching is actually happening from iron, because in hemoglobin, a lot of different entities are there. So first we took one protein, one globular protein, because the in hemoglobin, the protein is globular protein. So we took another globular protein, and we see there is no quenching of this carbon dot solution. So now we took porphyrin, one porphyrin without any metal ion, only simple porphyrin, and we see there also there is no quenching. So we proved that indirectly that quenching is actually happening because of the presence of iron in the solution. And here is some chemical reaction that I have proposed. Here is a hemoglobin is okay. So this, once it is quenched, if we add H2O2 in excess quantity, this fluorescence is coming back. So what is the reaction? So in ppm level, a ppm to ppb level, if we use H2O2, it reacts with hemoglobin. It is a Fenton's reaction. So OH radical is actually generated. This OH radical, which is present in the solution, it quenches the fluorescence. Now, if we use slight excess of H2O2, now hemoglobin reacts with H2O2, and then it gives that ferryl hemoglobin cation and ferrous ion. This H2O2 again reacts with this ferryl hemoglobin cation to form these superoxides and OH radicals. This superoxide actually reacts and then gives the OH radical. This OH radical actually quenches the emission from this carbon dot solution. Now, we have studied with excess amount of H2O2. Here, hemoglobin reacts with H2O2 to form OH radical. This OH radical is consumed by H2O2 and Fe. So this is the reaction. H2O2 reacts with this OH radical to form HO2 radical, and then iron 2 plus reacts with this OH radical to form iron 3+. Now, this OH radical is actually consumed. So there is no OH radical present in the solution. So we get the emission intensity from this carbon dot solution. So there is no OH radical present in the solution which can quench the emission from carbon dot solution. And finally, here we made some logic gate device using this same concept. So here a threshold, we put a threshold value below which it is off and above which it is on. So in that case, if we consider hemoglobin as input 1 and H2O2 as input 2, then if there is no input, we get high fluorescence from the solution. If hemoglobin is present in the solution, there is no fluorescence. If only H2O2 is present in the solution, H2O2 does not quench the emission from carbon dots. So it is fluorescent. Now, if we add H2O2 and hemoglobin, there is a fluorescence. So we prepare empirical logic gate. So this is one kind of device making. So finally, I conclude that we prepare some carbon dot solutions, and if we excite this carbon dot solution at 335 nanometer, we get emission from 421 nanometer. If we use this carbon dot solution with hemoglobin, there is a quenching, and if we add H2O2 in that solution, same solution, then we get the fluorescence on. So using this concept, we prepare a fluorescence on device. So this is my group in IIT Roorkee. Gaurav, Neem, Abha Jha, Sukarna Ghosh, Harishankar, and Sumit, and one more student actually supposed to join. Actually, he joined, but due to this COVID, he cannot come to IIT Roorkee, but he has already registered. So this is my group, but the thing is that no one is working on the carbon dot research. So everybody is now involved in the perovskite research, perovskite nanocrystals. Anyway, thank you all. If there is any question.
Yeah, thanks, Dr. Kar. It was a very informative lecture. As far as I think the students must have really learned the difference about the quantum dots and other nanomaterials, which is kind of quite a hot topic these days. And there are a few questions in the chat which I will ask, and I will also ask the participants if they have a question. They can also ask you directly in the Zoom. And so one question is that, can we call carbon nanotubes as carbon nanoparticles?
Yes, definitely we can call carbon nanotube as carbon, but the size has to be size of the carbon nanotube should be in that range, because for the carbon nanotubes, it is actually one-dimensional in nature. Okay, so it is a tubular like kind of thing. So, but carbon dots are actually dot particles. Okay, it is spherical. It is just like a points. So in that case, carbon nanotubes has a one-dimensional structure. So there is the difference. Okay, so it is one-dimensional and carbon dots are zero-dimensional.
Yeah. Another question is, what is the reason for increase in band gap with decreasing size of nanoparticles?
No, band gap actually decreases with increasing the size of the particle. Okay.
Yeah, so, I think he has the wrong question. Yeah.
Yeah. So if we increase, if we decrease the particle size, so the energy levels, the different energy levels are actually involved to create the band gaps. They are separated. Okay. So if we decrease the size further, this will separate it out. And sometimes there is a long gap, there is a discrete energy levels. So we will, means instead of band structure, there will be electron transfer. Means in band, if there is a single band, it will be conductive in nature. but for the semiconductors we get discrete energy levels, because this, if we say, change the particle size, energy gap, there will be energy gap.
Okay. And I mean, one thing I found very interesting is that you can create these quantum dots from various fruits and extracts. So, I mean, how different are these? Like you obtain it from orange juice or from the pea?
Yes, yes. Actually, source may be any kind of carbonaceous material. Whether it is glucose, sucrose, or citric acid, or graphite, or carbon nanotube, whatever. So that source material, the initial material, the reagent should be carbonaceous in nature. Means a lot of carbon atoms should be there. After the decomposition process, that will create actually a chunk of carbon particles.
Okay. But they will not be. I mean, would there be any difference in the properties?
Yes, yes, yes. Actually, that depends on the functional groups.
Okay.
Okay, so if we use some carbon particles which has a lot of OH radicals, means OH functionality at the surface, so we will get carbon particles with OH functionality at the surface. If we have some particle, means resource where NH2 groups are there or carboxylic groups are there, so we will get carbon particles with at the surface, where at the surface lot of carboxylic groups are there. Okay, so that will make the difference.
Okay, okay, that's interesting. So I request the audience, if they have another question, they can ask Dr. Kar. Yeah, so I don't think so there are any more questions. So I guess, yeah. So we'll like to thank Dr. Kar for giving this excellent lecture, and I hope everybody enjoyed it. And thanks once again, sir, for coming. And
thank you very much. Hope we'll meet you in future.
Yep, definitely. I'm looking forward to that. All right, see you guys.
Okay, see you.
So the next speaker is an audience now, Venus.
Okay, okay, that's fantastic. So our next speaker is Ramanathan, so who will be with us to talk about probing disulfide bond by surface enhanced Raman spectroscopy. So I will give a brief description of Ramanathan. He is a Fulbright Fellow and Fellow of Indian National Young Academy of Science, INSA, and he is currently working as an assistant professor in the Department of Chemistry at BHU, and his research interests are in making label-free imaging of cells and tissues using Raman microspectroscopy, and gas phase spectroscopy, ab initio quantum mechanical calculations, and characterization of drugs from traditional Indian repertoire. And he has done his doctorate in physical chemistry from Department of Chemistry, IIT Kanpur, and he has done his master's from Sri Sathya Sai Institute of Higher Learning and from Andhra Pradesh. And he has done several postdoc stints in various countries from 2008 to 2012. After that, he joined as a faculty in India. He has been awarded with several honors and awards. There is a long list of that. I would not be talking about all of them. And yeah, so he has a lot of teaching experience and awarded with many funding projects and everything. And I would now invite Dr. Ramanathan to please begin your lecture. Dr. Ramanathan, are you with us?
Thank you, Dr. Venus. Yeah, I'm here. Thank you for your kind introduction. I just would like to share my screen.
Sure.
Professor, if we can have your videos on, that would
that would be really
possible. Yeah.
If you can switch on.
Just give me 1 minute. Are you able to see my slides?
Yes, we are able to see your slides and you. Yes.
Okay, fine. So thank you very much for that kind introduction and giving me this opportunity to talk about a part of my work and also give a basic introduction to this topic. I believe the first speaker, Dr. Sukumar, would already dealt with the basics of Raman spectroscopy. So I do not know how it got placed. The conference began with Raman spectroscopy and kind of also ending with Raman spectroscopy. So it's like a coincidence perhaps. So anyway, let me, so this is just my overview. I'll be also briefly introducing the concept of Raman spectroscopy, but not of course as detailed as what Dr. Sukumar had done. Then I'll be very briefly giving a bird's eye view of what is surface enhanced Raman scattering. And then I'll be showing you the results of a few of the molecules that we have studied using a novel substrate employed in surface enhanced Raman scattering. So the molecules which contain predominantly the sulfur bond or the disulfide bond. So PATP is para-amino-thiophenol, methyl benzoic acid. GSH is glutathione, and cysteine is a dimeric form of the amino acid. So the results of that I'll be showing it to you. So Raman spectroscopy, as you all might be aware, it's perhaps till date the only scientific experiment that has got us the Nobel Prize. It was discovered by Sir C.V. Raman way back in 1928. And February 28, that's what we celebrate as National Science Day every year. And he was so confident that he'll be getting the Nobel Prize the next year, but he didn't get. So, of course, he got the Nobel Prize in the year 1930. And we have been waiting till then. It's been 90 years for any further Nobel breakthrough. Because this is October month where we have had all Nobel announcements. So, to tell it in a very nutshell, Raman scattering, I mean, historically, if one looks at how Raman himself got the idea of venturing into this area of research, is after the Compton effect had got the Nobel Prize. Compton effect is nothing but the nonlinear scattering of X-ray upon interacting with the crystals. So what he felt was that what is possible in the X-ray must also be possible in other regions of the electromagnetic spectrum. So he ventured with the visible range of the electromagnetic spectrum. And initially they did have a success way back as back as in 1921 or 22, where the student did observe the nonlinearly scattered light from liquid benzene, but they termed it as a weak fluorescence. They suspected that there is some impurity in the liquid benzene, so they did not take it seriously. Yet they were pursuing it. Raman and a group of his students were pursuing it, and it was in 1924 or 25 that Raman took it up very seriously, put Krishnan, K.S. Krishnan also into it. So there is, the people who have written the biography, they go on to say that it is not just Raman effect, but also Raman and Krishnan effect. I mean, I'm interested in history, that's why I'm bothering you about a little bit about tidbits from the history. Of course, there are a lot of interesting facets when you have to look into the development of, or the evolution of the Raman effect, the way it was discovered. But at the same time, Russians were also, they had come up with a theoretical framework. So to this day, they do not refer to this effect as Raman effect. They have the Russian scientist's name associated with it in their country. That's how they address this effect. So in a nutshell, it is like, as I said, it's the nonlinear scattering of light, especially the electromagnetic region, upon its interaction with the with any molecule. In fact, one more tidbit before I get into the technicality. It's in the written
while it's the return voyage from Britain that Raman embarked upon, because one of the role models of Raman was Rayleigh. And while and Rayleigh is one of the most iconic explanations was why the sky is blue. So while pondering deep over it, and when Raman was returning from UK to India by the Mediterranean ship route, what got excited Raman was the blue color of the sea. Why is the water in the sea blue? So that question bothered him, and I'm saying this because this might enthuse the students, because even a trivial thing that that comes to our observation, if we are persistent over it, and if we go deep into it to find its logical end, to get the answer, perfect answer to our satisfaction, it may lead to breakthroughs, and that's what happened in the case of Raman. And it's not just the case of why water is blue. I mean, wherever he went, it said that when he was in the Whispering Gallery, he had studied the acoustics so well that within one visit of the Whispering Gallery, he wrote a paper about it. So that was the brain of Raman that we are dealing with. So it's a nonlinear scattering. So, I mean, whenever light falls on any medium, it has got, broadly we can classify the consequences into three, namely the radiation can get reflected as is, or it can get transmitted through, or it can get scattered. And in that scattering also, there are two different possibilities, as I said, elastic and inelastic. And it's the Rayleigh scattering comes under the domain of elastic scattering. The equations that I've used here are from the classical model, or for that matter, the semi-classical model, where the matter, that is the vibrating medium, is treated in a classical sense. So here you can see how the vibrating bond is modeled in the form of a mass on a spring, and that's how the Hooke's law's equation is being applied here. F is equal to minus kx. In the place of F, it is the ma, mass into acceleration. And if you substitute, of course, we are not taking individual mass, it is the reduced mass, because two masses are employed here. And acceleration of each of this individual particle mass is what is being written here. And x1 and x2 representing the displacement of individual mass from their mean resting position. Now, if we look at the incoming radiation having a sinusoidal component, so that sinusoidal component is going to interact with this vibrating bond. And furthermore, this vibrating bond can be written, can be expanded as multipole. And in the case of Raman, since the change of quadrupole moment is what is giving rise to the so-called spectroscopic transition, so the quadrupole moment is what is being employed here. And when that quadrupole moment gets to interact with the incoming radiation, which is having, say, a frequency of nu zero, oscillating in the frequency of nu zero, as a result of interaction, finally what we get here, the last equation, is we have a term where you have nu zero minus nu m plus cos 2 pi nu zero plus nu m. So these are respectively the Stokes and the anti-Stokes shift that the electromagnetic radiation experiences upon interacting with this oscillating dipole from the vibrating molecule. Now, I mean, I'm sure Professor Sukumar would have gone into the detail why not the dipole moment, why the quadrupole moment here. I mean, it's not it's a standard textbook case problem. But to cut the long story short, the selection criteria or the selection rule for the case of Raman transition is, as I said, the change in the dipole moment. And that's why the term alpha is what is being employed here and not the term the mu. So here the nu zero minus nu m and nu zero plus nu m, these are the the Raman shift per se, which are nothing but the Stokes and the anti-Stokes radiation. To describe it in a very pictorial, in a very cartoon or in a very graphical way, you can think of the vibrating bond as this vibrating membrane here. And as you can see, it is having the motion of the vibration. And the blue dot, you can take it up as the incoming radiation, either wave or the photon. For this cartoon, it doesn't really matter. So it interacts, and as it interacts, you can think of this blue dot interacting with the membrane when the membrane is having the maxima, or when the membrane is having the minima, or when the membrane is in the stationary or in the equilibrium state, a non-displaced state. So as a consequence, when the incoming radiation, or this, say photon, or in this case the blue dot, when it interacts, say with the membrane, when it is in the non-displaced state, or in the state where it is having no vibration, then obviously there is no exchange of energy happening. So whatever energy the blue dot comes in, it exits with the same energy after the interaction. And that's what we classify as a Rayleigh scattering, shown as the red and the blue arrow in this card, in the energy diagram below. On the other hand, when this blue dot or the incoming radiation of the photon interacts with the membrane, when the membrane is stretched to, say, its positive maxima, so it has a tendency to gain the energy from that membrane, whereby after the interaction, the blue dot, when it exits, it gains, its energy gets added. And that's what you see in the last purple, blue and the purple arrow, where you can see that, of course, this energy is increasing the y-axis. Y-axis is inherent, it's not explicit in this energy diagram. So you can see that the length of the blue arrow is smaller than the length of the purple arrow, which indicates that the energy has increased after the interaction. And the last possibility, when the incoming radiation, or in this case the blue dot, interacts with the vibration, the blue dot can transfer its energy to the vibrating membrane, whereby after interacting, the blue dot will lose some of its energy. And that's what you see here in the form of a green arrow, where the length of the green arrow is shorter than the length of the blue arrow, indicating that the energy has reduced when the photon or the incoming radiation has lost its energy to the vibrating medium, in this case the membrane. Now again, it's a matter of fundamental statistical thermodynamics, whereby you can see that at room temperature, what the Maxwell-Boltzmann distribution is what is the closest to describe the distribution of any system. So it's very obvious that the Stokes scattering would be more dominating than the anti-Stokes Raman scattering, because given the Boltzmann distribution, the population would decrease as the energy levels increases from 0 to 4 in the ground state. So it is the intensity, of course, the intensity is proportional to the transmission coefficient, which in turn is dependent on the population. So given in this case, the population of the higher states are much lower than the lower states, the anti-Stokes radiation is of much smaller intensity compared to the Stokes Raman scattering. So what the day in the normal lab, in the ambient condition, what normally we observe is the Stokes Raman scattering, where the energy of the photon or the light wave, after interacting with the molecule, is losing its energy. Now, just as a matter of tidbit, if we were to perform, say, candle light or the fire as our sample, there, because the temperature has increased, the population of the higher levels also will be more. We can expect the anti-Stokes radiation, anti-Stokes Raman scattering to dominate. And that's what has been exploited in one avatar of Raman scattering called coherent anti-Stokes Raman scattering. But I will not get into the details of that. But this is just as a matter of information that if by temperature, if we are able to populate the higher vibrational states, then we can expect the anti-Stokes Raman scattering to be either equally intense or in fact more intense than the Stokes Raman scattering. The caveat or the major drawback with respect to Raman scattering is that only 1 in a million photon gets Raman scattered. What I mean by that is, if say 1 million photons are falling on the membrane, it's only one of them is going to either get Stokes shifted or gets anti-Stokes shifted. And you can also infer this from the fact that even though it was 1930, Nobel Prize was awarded to C.V. Raman for his discovery of this effect, it was until 1960. If you look at the number of papers that were published, and if you compare the papers that were published between 1960 and 70, the number of papers would at least be 10 times more than what was published between 1930 and 60. The reason is something remarkable happened in the year 1960, where we have the discovery of lasers coming in. First the solid state, the ruby laser, and then of course the gas laser. Within a very short span of time, these two discoveries, they revolutionized the whole field of spectroscopy. We have very intense light source. So instead of, but still this is not, this ratio is intrinsic. 1 in 1 million is intrinsic. But what happens is now we can have larger photon cross section falling into the medium of investigation, whereby the Raman scattered photon, that cross section can be increased. The Raman photon intensity can be increased, and that's what, as I said, it revolutionized the whole of spectroscopy, and particularly with respect in the field of Raman spectroscopy, it had a very huge effect. The invention of laser. For most of our studies, we had used this system, handheld Raman system with a 532 nanometer continuous wave. It was like a tabletop spectrophotometer, which also has a handheld adapter to it. So it's a fiber coupled system, and it has the grating. The spectrometer inside has a grating groove density of 2,400 grooves per millimeter, and it uses a CCD based detector. And the spectral processing procedure involved denoising using FFT algorithm. By and large FFT, but wherever needed, we change the algorithm to suit in order to remove the noise appropriately, and the baseline correction. So these two minimal analysis of the pre-analysis of the data was done to the raw data. Before I move on, if laser was the invention of laser was a boon for the domain of Raman spectroscopy. At the same period, in the 1960s, there was another major discovery, I would say, or great observation by Fleischmann, who saw that when an analyte, or say whatever Raman probe that we need to measure the spectrum of, if that probe is adsorbed on a metal surface, metal meaning the coinage metal, which readily gives plasmon upon interacting with, say, electromagnetic radiation in the visible to near IR region. So, any problem? Am I audible?
Yes, sir, you are audible.
Okay, fine. So when so Fleischmann observed that when the molecules are adsorbed on a metal, and when the laser was shone on such metals, coinage metals, the plasmons which are produced on the surface of the metal couples with the molecular vibration, and this coupling enhances the Raman cross-section. The Raman scattering efficiency gets enhanced by orders of magnitude. So much so that at least 10 to the power 4 to 10 to the power 8 orders of magnitude enhancement was seen in molecules that were adsorbed on the metal surface and onto them when the laser light was shone. Of course, there are two different, and this is what is referred to as the surface enhanced Raman scattering. There are two different theories to explain this surface enhancement. What I just now explained was the electronic theory involving the plasmon coupling. What we have is also chemical theory, where if the plasmon theory assumes a physisorption, the chemical theory to explain the surface enhancement effect involves a chemisorption. And so fundamentally, these are the two theories which exist to explain the effect of surface enhancement. And what is more important to note here is that we observe at least 10 to the power 4 factor order of magnitude enhancement in the regular Raman signal. And that's what will be also evident from the data that I'm going to show to you in a couple of minutes from now. So just give you an impression. If you look at the spectra that I'm showing at A, this is a regular Raman spectrum of ethanol, where you can clearly see the CH bond and the CH stretch, CH bend, CO bend, so on and so forth. That is in the bottommost A spectra. The B spectra, which is the red spectra, is the Raman spectrum of 100 millimolars of ethanol. What was A was a neat ethanol, and when the same neat ethanol is diluted using water to the concentration of 10 to 100 millimolar, we see that there is absolutely no Raman response seen or discernible for ethanol molecule. In the red spectra, what you see is only water response. The broad peak that you see after 3000 centimeter inverse is that corresponding to the OH stretch. That could be also from the water as well as the ethanol. But the neat ethanol, you see, the CH cross section is much more compared to the OH, and the number of CH bonds is also much more than the OH. So obviously in the neat, you do not have the OH concentration, even though it is there, very minimal, but then the CH stretch dominates OH stretch. So clearly the red spectrum, what you see here is the response only coming from water and not from the ethanol. But the blue spectrum, if you see, we have, this is a spectrum of 1 picomolar, that is 10 to the power minus 12 molar of ethanol on silver bulk. What I mean by silver bulk here is, we did this experiment by taking a silver rod and just dipping that silver rod on 1 picomolar solution of ethanol, and then we recorded the spectrum. That's what I call it as AG bulk. But the same experiment when repeated was, this was on silver nanoparticles. So we prepared the silver nanoparticle, and at one stage of preparation of silver nanoparticle, we added ethanol to it, and we can see that the ethanol adsorbed on the silver nanoparticle spectra more or less closely matches with the 1 picomolar spectra of ethanol on silver bulk. Clearly the peaks compared to the neat ethanol are shifted, but they are identifiable, and they are matching with the literature, the peak values reported in the literature. So this was kind of a proof of principle which was seen for using our tabletop spectrophotometer. Now we had a collaborator, Dr. P. Suresh, who is basically an electrochemist. He does a lot of electrochemistry, basically splitting water using different kind of electrodes. But then we discussed and the collaboration began. What he does is he takes just a pencil graphite that normally we use it for our pencil, the pencil nibs that we get. We would take the pencil graphite and he coats different metals on them, copper, silver, palladium, platinum, so on and so forth. So he coats the pencil graphite with these metals and he does the electrochemistry experiment. But then in our collaboration, I borrowed those metal coated pencil graphites and wanted to see if those metal coated pencil graphites could act as a novel SERS substrate. Because in SERS, you can see that we need a metal substrate. And through the previous slide, I showed that with our instrument, we are able to see SERS effect with silver bulk, silver nanoparticle. So we wanted to test this copper coated on a pencil graphite, whether it would also serve as a novel surface enhanced Raman spectroscopy substrate or not. So this is the procedure that is followed in their lab, my collaborator's lab, to prepare metal coated pencil graphites. I won't get into the detail, but as I said, our motivation was, can this be good? Can this be a good SERS substrate or not? So here the abbreviation CuPg, PG represents pencil graphite. CuPg means copper coated on pencil graphite. CuAgPg, it's like a core shell coating on pencil graphite where you have copper and silver coated on pencil graphite subsequently. So using these two metal core shell metal coated on pencil graphites, we wanted to show for the proof of principle with a very standard sulfur containing molecule called para-aminothiophenol and 4-mercaptobenzoic acid. That is 4-PATP and 4-MBA. And we also wanted to see if we can quantify these through SERS studies or not. What was reported earlier by Huang et al. In JACS in 2010 and subsequently is also in 2012 was that when PATP was adsorbed on silver surface, it had the tendency to undergo dimerization. So that is what is seen here. So the peaks in the more or less green color are from the PATP, and the ones that are from the red are the dimeric PATP. We wanted to kind of replicate this using our new setup. So this was the procedure, sample preparation. The monolayer formation is a procedure that was adopted by my collaborators lab, single atomic layer, single atom monolayer, that's what they call SAM, that's the sample preparation, where on the copper which is coated on a pencil graphite, we make the analyte adsorb. And that is, we verify whether that is single atomic layer or not using cyclic voltammetry. And then that was followed by the SERS measurements. So this is the cyclic voltammogram of PATP on, as for standard, we also compared it with copper bulk. So here, copper bulk was taken for a standard as a reference here, where we just took a simple copper rod, kind of removed the oxide layer, and very quickly dipped it into the solution of PATP of varying concentrations. And then we had measured for each of these PATP coated copper rods as well as PATP coated copper PG. We had done this characterization of the monolayer formation. And clearly we can see that the black is cyclic voltammogram before the monolayer formation, that is the bare pencil graphite coated with copper, or the bare, and red is the after the PATP getting adsorbed on it, And the blue spectra is also, blue voltammogram is, see, PATP modified copper wire, that's copper on bulk. So this confirms that we have our analyte adsorbed as a single layer, monolayer on our substrate, namely copper on pencil graphite and bulk copper. So this is the Raman spectrum of solid PATP, just for the comparison's sake, where you see the different characteristic peaks, the NH and the CH peaks convoluted in the 3000, slightly above 3000 centimeter inverse. Then you have this CC bend. Then the characteristic peaks of the CS, the CH, the bending peaks of this molecule. This is, as I said, this is for our reference to see what happens to spectrum of this when it is adsorbed on either copper bulk or on the copper that is with the pencil graphite. So this is the spectra of PATP, that is para-aminothiophenol, on copper PG. And if you compare it with the Huang et al.'s work, we also see that the dimerization is indeed happening, which means that, two things are answered here. The copper coated on pencil graphite is indeed acting like a novel SERS substrate, that is one. Second, it is also acting like a good substrate for a photocatalytic reaction, where the monomeric PATP is getting converted to the dimeric form, where the NN, the azo bond gets formed, which is confirmed by these peaks 1388, 1438, and 1140, which is observed, which was also observed by Huang et al. So for comparison, you see that the red spectrum is of Raman spectrum of 100 millimolar of PATP in ethanol. And if you can see, the red and the blue and the black spectrum are nearly identical, meaning that the neat ethanol and 100 millimolar of para-thiophenol in ethanol, normal Raman spectrum is not able to detect the presence of 100 concentration as high as also 100 millimolar of PATP in ethanol. This is the comparison here reveals that fact. But the blue spectrum is from 1 micromolar. So there is clearly 10 to the power 5 orders of magnitude change, at least here, because here we are able to see we are able to detect the presence of para-aminothiophenol clearly, and which is telling us that there is a factor of enhancement at least 10 to the power 5. This was on copper PG, that is copper coated on pencil graphite. I mean, these are the spectroscopic vibrational assignments to confirm it. So now this is something to detect how low can we go with respect to the detection limit. We cannot rigorously call it as the LOD, or the lowest observable concentration, or lowest detectable limit of detection. We cannot rigorously call it that way for reasons because of the reproducibility factor here. So of course we have, what I mean by reproducibility factor here is that if we record the spectrum on one spot of a coated pencil graphite, we'll have to change a different, we'll have to go to a different spot. Now our cyclic voltammogram says that it is a mono layer. So in a way that the repeatability within one sample is there, but when we shift the samples, we'll have to do the cyclic voltammogram first and then come to the Raman measurement in order to confirm, ascertain the reproducibility part. So assuming that, so the lowest that we could go for para-aminothiophenol on copper adsorbed on bulk, para-aminothiophenol adsorbed on bulk copper is 1 micromolar, whereas with para-aminothiophenol on copper on pencil graphite, we could go to concentrations as low as 1 nanomolar of PATP in ethanol. So we can clearly see that there is at least 10 to the power 5 to 10 to the power 8 factor of enhancement. This 10 to the power 3 enhancement comes because of the nano effect. Because from the bulk copper to copper on PG, the surface area obviously increases, so the plasmonic coupling efficiency also gets enhanced. So this is about 4-mercaptobenzoic acid, where again it is from the proof of the principle. So this is the spectrum of so Raman spectrum, the solid sample for our comparison's sake, how the peaks shift. And this is for showing how the 4-MBA, when it is adsorbed on copper bulk or on copper PG, how the spectra varies. So here the black spectrum is that of ethanol, and the red spectrum here is Raman spectrum of 10 millimolar of 4-MBA in ethanol. And as you can see, the two spectra are again identical. Clearly, the inference drawn from here is that even a concentration of 10 millimolar of 4-mercaptobenzoic acid in ethanol is not sufficient to be detected by regular Raman spectroscopy. Whereas, if you look at the spectra that are shown on this panel, these are CRS spectra of 1 millimolar of 4-MBA on copper, bulk copper, and 4-MBA on copper PG. So this also once again shows that the copper on bulk, the bulk copper as well as the copper on pencil graphite are indeed acting as a good source substrate. So this is the another molecule containing a disulfide bond, which is a cysteine, dimer of the amino acid cysteine, where if there is a cleavage here, this gets an SH and this gets an SH, and you have that as an amino acid, which is your cysteine. The dimeric form is cysteine, and this is the neat spectrum or the Raman spectrum of the solid cysteine. And these are the results when it is adsorbed. So this is the Raman spectrum of 400 micromolar of cysteine in water, where you can clearly see that it's only the water response and there is no Raman response of the analyte. Whereas the same concentration, 400 micromolar of this analyte on copper and on copper PG are shown in the spectra of red and blue. One conspicuous difference that we can see here is that the spectra of red and blue is very different. Even though the analyte is the same, the difference is this is copper bulk and this is on copper coated on pencil graphite. So if we compare the spectrum, the blue spectra, that is cysteine on copper on pencil graphite with the solid cysteine for reference, we can clearly see there is a slightly shift that is happening to the 625 centimeter inverse. So there is this peak here, there's a 499 peak here. And then there's a peak at 615, 615. So it is the 615, which is nothing but the CS stretch. That is what is seen here. And you can also see that this sharp peak, which is the 499 peak in cysteine, which corresponds to the sulfur-sulfur stretch, that gets completely vanished in the blue spectrum. Of course, what you see here is a very small elevated from the baseline. This is as good as having no, it's in comparison with the noise level. So you can say that 499, there is absolutely no peak, or there is very small trace of that disulfide intact peak. So two messages we get. the adsorption, so when the when the cysteine is adsorbing on copper Pg, the adsorption orientation we are clearly able to see, it is able to adsorb through the sulfur functional group, so much so that the sulfur-sulfur bond is getting cleaved. Whereas, if you look at the spectra of cysteine on bulk copper, we see that still there is a 499 peak is quite intact, which means that when cysteine is adsorbing on bulk copper, the disulfide bond is not completely getting cleaved. So that is a take-home message here. There is also a peak that is, this peak comes from the SH stretch, which is seen in the, which is seen only in the red spectrum and not also in the blue spectrum. In the blue spectrum, it's completely not there. So the binding motif is coming out very evidently from these results. And the fact that the disulfide is partially intact, partially broken, is also getting revealed from the red spectrum. So two things here. There is a shift in this CS stretch when cysteine is adsorbed on copper on pencil graphite, and the disulfide bond is completely getting cleaved. Whereas when the cysteine is on copper bulk, the SS double bond is partly intact and partly getting cleaved. So this we further tested for applying it on some real-life application-oriented molecule, because till now what we saw was either proof of principle or very preliminary application in the sense of this amino acid here. This is glutathione, which is of a free radical scavenger, something very important for early detection of cancer, because whenever there's a free radical generated, our body releases this glutathione, and GSH, it gets the electron and forms a dimer, GSSG, it forms a dimer, and that's how the free radical gets scavenged. So that's the interest here. So wherever there is a large concentration of GSH being released, that can be a very good target area for very early detection of some tumorous activity. So, I mean, that's a motivation there, but then you can, as far as the result is concerned, you can see here, the red spectra is the source of 10 millimolar of glutathione in water, and the black spectrum is that of neat powder glutathione. So this 2532 centimeter inverse is that of this free SH stretch. The SH bond stretch frequency appears at this wave number, and you can see that that is completely missing in the red spectrum, meaning again that the bonding motif of GSH on, say, the silver nanoparticle, or in this case what was used was silver nanoparticle, it was not copper. In this case it was silver nanoparticle. So this moiety is binding through its SH bond to the silver nanoparticle. And this is again for the quantification stage, where we can see that as low as 100 nanomolar of glutathione can be detected using this silver nanoparticle and using surface enhanced Raman scattering. This is what is pictorially shown here, the adsorption process happening. So the detail, this is very standard way of preparing the silver nanoparticle. And that same spectra shown in a more detailed way, how the bonding motif is seen here. So to overall summarize the results, we see that the copper on pencil graphite acted as a good novel surface enhanced Raman spectroscopy substrate, which we showed that this photodimerization is indeed happening when that was used as a substrate. Similarly, we tested it also on 4-mercaptobenzoic acid. There is a result which I didn't discuss, but it is also shown that we also did with palladium, and that also shows as a good search substrate. So the take-home message that I would like to say here is that this simple electrode prepared by my collaborator, where he takes a pencil graphite and coats different metals on it, can also be used in surface-enhanced Raman scattering, and I've shown it using ample proof of principle molecules. That was previously was a paraminothiophenol. This is using cysteine, where you can see that the cysteine, when it is interacting with nanocopper, where that is copper on pencil graphite, the disulfide bond is completely getting cleaved, whereas when it is interacting with the bulk copper, the bond is still partially intact. So that's all I have to share. I hope I have impressed upon you the fact that metals that are adsorbed on pencil graphite can also act as a good surface enhanced Raman scattering substrate with which we can do wonderful experiments. If you have any questions, I'll be happy to answer them. Thank you.
Yeah, thanks a lot, Dr. Ramanathan, for sharing this. And yeah, this mic is. So I request the audience, if they have some questions for Dr. Ramanathan, to please you can raise your hand or you can ask your question here. And yeah.
If I'm able to answer, I'll be happy. Otherwise, I can get back to them by email.
Sure. Yeah. Okay, I don't think so there are any questions even in the chat session.
No problem. Yeah.
But thanks a lot for giving this informative lecture. I'm pretty sure the students have got a gist of everything they need to know about Raman spectroscopy and the applications it has. And once again, I thank you on behalf of the organizers for finding time from your precious schedule to deliver a lecture. Thanks a lot.
Thank you very much for this opportunity. Yeah. Bye.
I think we'll take a short break here before the next talk, which will start at 5. So I request you all to rejoin at 5 o'clock. Or maybe you can stay here with us, but we'll take a half an hour break. So, hi Priyal, I think it is time, but let us wait for another 2 minutes for the speaker to join and then we can start.
नानक नाम दा ताज इलाही सीस सजावण वाला जिस दी होंद च शब्द गुरु दा जगे पुनीत उजाला सदा सदा पुरनूर रहे सदा सदा पुरनूर रहे गुरु
Hi Priyal, I see the first speaker is here.
Yes, ma'am.
Okay. So I think we can start. Welcome, Professor. Yes, welcome, Professor Das.
Am I late or not?
That's okay, man. Just 1 minute. I think there was some
I forgot. I couldn't get the link properly. Yeah, now I do. Yeah, just late by 2 minutes. Yeah, it was somewhere in my email.
That's okay.
Okay.
Yeah, sure, no problem. So I think we can get started. Do you want some time to start, or we can start right away?
I am reasonably ready. Yeah, whatever you say.
Okay. So I think
you can hear me, I suppose.
Everybody
Yes?
in the audience. Yeah, we can hear you, but your videos are off.
How do I switch up?
Yeah.
Oh, start camera. Now?
Now I see you.
Okay, right.
Yeah. But if you can shift your webcam a little bit down, because yes, now this is perfect. This is perfect. So I think everybody in the audience already, they know you. Most of them have already attended your first lecture.
One second.
So I would just like to say that Professor Das, those who were not present for his first lecture with us, we should know that Professor Das is working at TIFR in the Department of Chemical Sciences, and he's going to continue with his second lecture on electron paramagnetic resonance spectroscopy principles and applications. So please go ahead, Professor Das.
So I start now by sharing the screen. Yes?
Yes, yes.
Share. Share.
Yes, we can see your slides.
Can you see the slide now?
Yes, it's
okay,
on angular momentum.
Yeah. Let's go to the beginning of this. Okay. And here, hide this thing. How do I stop this screen? Is the slide appearing properly or anything?
Yes, it's perfect. No,
okay.
Everything is fine. Yeah.
Okay. Yeah. Okay. So this is the continuation of the last lecture. So in the last lecture, to a large extent, I discussed the principles and also gave examples of application of this electron parametric resonance spectroscopy to organic free radicals. So now we'll continue to see more applications in other branches of chemistry and physics. So this is just a recapitulation of what we did last time. That is that angular momentum and magnetic moment are related. In particular, electron may have a spin angular momentum S that will give rise to a magnetic moment mu due to the spin angular momentum. Similarly, it can have an orbital angular momentum L, and that will give rise to a magnetic moment due to orbital motion. Both are essentially very identical in their appearance of the equation. So G factor is a proportionality constant. Beta is Bohr magneton. So in case of spin angular momentum, G happens to be for a free electron approximately equal to 2.00 something. And for an orbital motion, G is equal to precisely 1. So even though the equations are same, it is the proportionality constant which is different. But point to notice here is that in these two relations, G is a pure number. Beta is of course a constant because it is the unit of magnetic moment. So you see the vector S, angular momentum vector, will be parallel to the magnetic moment vector in case of spin angular momentum. Similarly, in case of orbital angular momentum also, the orbital angular momentum vector L is parallel to the magnetic moment due to L because G and beta are pure number. So far there is no complication. But if the electron has both orbital angular momentum and spin angular momentum, then because of these G's are different, the effective angular momentum one can define this way: J is equal to L plus S, and this addition is not an algebraic addition. This addition is done in terms of the vectorial addition because L is a vector, S is a vector. So this have to follow the rules of addition of vectors using quantum mechanical rules. So then what happens? The effective J will have a direction, but magnetic moment will not be parallel to that direction. So that is the complication that comes when the species has both orbital angular momentum and spin angular momentum. Then without getting into detail, it is enough for us to know that since the effective angular momentum J and effective magnetic moment mu are not parallel, this sort of simple equation won't work. You have to put something here which will make a vector J in one direction and magnetic moment mu in some other direction. That is possible by making G a matrix. So it is not a pure number. If you make a 3 by 3 matrix, now for some reason this is called tensor quantity, but we don't need to get into that technical detail. It is, on the other hand, it is easy to visualize that if I have a vector S which is parallel to mu, it is enough to say this number is a pure number. But if S happens to be a direction which is different from the mu, then a pure number G will not equate this equation. So if you, on the other, if you put a matrix 3 by 3 matrix here, then a vector here, then you multiply this dot product, then it will produce another vector whose direction will be different from that. So that is basically the essence of this, that a species which has got L and S that can have a G which is a matrix. So with that we will proceed further now. So just the L and S can be combined to produce an effective magnetic moment, and that in the magnetic field will produce an interaction. So S becomes an, if you write this whole thing to be an effective S, then G becomes a tensor quantity in a sense, or it is a 3 by 3 matrix quantity. This will continue. Now it so happened that even though G is a 3 by 3 matrix, there are 3 special directions in the molecule, let's say called X, Y, and Z. And because it is 3 by 3 matrix, one usually writes using 2 suffixes X, X, Y, Y, Z, Z. Then in each of the specific direction, the magnetic moment component S is parallel to the magnetic moment component mu X is parallel to the spin component Sx. So this behaves like very similar to the usual relation of angular momentum and its magnetic moment. So these are the 3 specific directions of the molecule where this G has 3 special values where the magnetic moment and angular momentum are parallel. These 3 specific values are called the principal values of the G matrix, and they are designated as GXX, GYY, GZZ. That is one part. Second part is about the electron nuclear dipolar interaction. This we discussed last time. The electron has a magnetic moment, and many nuclei also have magnetic moment. Proton, for example, that they can interact and produce an potential energy, but this interaction depends on the directions. I also mentioned that this, when the molecule tumbles in a liquid solution, this average value becomes 0, and so it doesn't contribute. But if the tumbling is not sufficiently fast, or if the sample is crystal or frozen solution, then that will not be averaged. So that will contribute. Also, we also mentioned there is some isotropic spreading constant, although we said that is the interaction where the electron magnetic moment is sitting on the nuclear magnetic moment. This is called the Fermi contact interaction. This gives rise to the hyperfine splittings. This we saw last time. And we usually write this whole thing as a parameter A, which is called hyperfine splitting constant. So we have got now, if this dipolar interaction, which is excuse me, interaction of electron dipole with a nuclear dipole, combined with this type of special type of interaction of electron dipole and nuclear dipole, then we can write even the hyperfine interaction also can be written in form of a matrix of A, 3 by 3 matrix here. So S is the effective electron spin, this is the nuclear spin, they are interacting through a 3 by 3 matrix. So again, this will have 3 special directions in the molecule where this will behave like isotropic splitting, AX, AY, SZ, 3 principal values of the A matrix. This is sort of recapitulation of last time and what complication we are trying to introduce here if the tumbling is not sufficiently fast. Now, this is immediately seen in case of EPR of spectra of transition metal complexes. There, you see often transition metal complexes have d orbitals. So d orbitals have angular momentum L equal to 2, SPD, yes. And of course, it is generally expected that the angular momentum is quenched. Usually all electronic chemistry textbook says that. But quenching is never 100%. Some residual angular momentum, that's orbital angular momentum, stays there. So that couples with the spin angular momentum to produce all these complications. So what happens, therefore, the G doesn't remain a pure number. It becomes a matrix, and that is, the interaction becomes directional dependent. We call it anisotropic G value. Similarly, the hyperbolic coupling constant A is large for these transition complexes, and also it becomes anisotropic. It becomes directional dependent. So tumbling in solution, if they are not very fast, they do not average this out. But what happens in case of organic radical, these interactions are very small. So usual tumbling in a moderately viscous solvent is enough to average out these small anisotropies. Because in transition metal complexes, these are sufficiently large so that one sees this effect even in solution. So this is the example of this copper spectra of this particular complex. I showed it last time as an example. See, copper, now we know that this natural copper has two isotopes, 63 and 65, and both have nuclear speed of 3/2. So this will produce 4 lines. Excuse me. And how to, indeed there are 4 lines, but it is not very obvious. So if you purify it to have only one nucleus, it's copper only 63, excuse me, then it gives these 4 lines. The gap from here to here is same as from here to there and from there to here. That means they are actually coming from as one nucleus, and that is copper 63. Important, but so that is fine. 3/2 produces 4 lines. But what is not so fine is why the intensities are so different. Now here we have to really be careful about what we mean by the intensity. So here the EPR lines are in the form of a derivative. So 2 parameters decide the intensity. One is the width, from peak to peak, this top to this one, this is called delta B, peak to peak, and height of this to this, that is IPP. This together decides the intensity of the transition or spec line. So because it is first derivative, one can show that effectively the area of the absorption curve of this will be this I peak to peak height times this width square of that. So this together one can actually, both the values have to be considered to decide the intensity of a particular line. Height times the width square. Now if you want to do that, if you want to do that, then you calculate the width of this. It's a broader. This is narrower. Because the width is broader, height has gone down. So if you calculate this height times width, it actually transfers that all of them have the same intensity. They're 1:1:1. And that agrees with this copper nuclear spin with 3/2. It gives 4 lines with equal intensity. Now comes the reason why the widths are different. They're all related to anisotropic value of A and anisotropic value of G. And they interact such a way that they produce this sort of line width, which is dependent on different for different line. So the anisotropic interaction in copper complex is actually present, is shown by these different line widths. Now the one we started with is that we have got copper natural abundance. It has got 63, 65. So one can actually see that from this little hump here to something here, and this other one here, these 4 lines corresponds to copper 65, and copper 63 is this, we see little hump here, and they are actually almost overlapping here and here, and the 4th one is here. So one can see that 4 are there, but because of this partial overlap, they give rise to this strange looking line shape. At the same time, the percentage of 65 and 63 in this naturally abundant is some 69 to 31%. That will also contribute to the relative intensity. So that way we understand why it is so. So in particular, this shows that hyperfine interaction and anisotropic interactions of G both are present here, and one can actually determine these values of this anisotropic G and A from this trying to explain this line shape. That information is actually contained here. So in the similar vein, here is another example. This is the di-vanadilyl complex. Now vanadium has 51 has nuclear spin 7/2. So one nucleus will give 8 equal lines. Now since there are 2 of them, it produces actually 15 lines. And you see how the line widths are changing. The way you are changing again, it is a different. It is here the width becomes narrower from narrower to broader from right to left. Here it changes in some other pattern, in other manner. Here both extreme end the lines are broad and the middle lines are narrower. Now why this is so? That's again the simplest answer is that the anisotropic interactions are present here. They are contributing in such a way that different lines have different widths. So one can actually find out the anisotropic values from this spectrum. Now we'll not do any more on this transmetal complexes. It's a vast subject. For example, one can look at the spectrum in single crystal. One can look at the spectrum by freezing the sample. Those are, each of them is a way of finding out the interactions that is present there, and particularly the anisotropic G or anisotropic A values can be obtained from those experiments also. But let's get into a different territory now. This example I showed last time is the very stable organic free radical. This is called tempol free radical. This hydroxyl group is giving us to the OL here. This is a tetramethyl piperidine N-oxyl. This is the total name of this one. But since this is very large name, it is called tempol. Okay. Now these three lines we know they come from this nitrogen nucleus whose spin is 1. So this gives us to 3 equally spaced lines. And this is the experiment done at room temperature and in solvent N-hexane. Now it so happened that this itself has anisotropic interactions which is not visible here. In the spectrum looks very much like any other organic free radical. So let's see if we change the temperature of the spectrum and see what happens. Here is the experiment at different temperature. So this is the solvent is this diisononyl phthalate, somewhat more viscous than N-hexane. N-hexane has got very small viscosity. The first thing you see that 3 lines are there, but you see that these are well resolved and these extra lines are here, which is not seen. And those lines are actually coming from these methyl groups, protons here. So the unpaired electron goes all the way there to produce the splitting. That is the minor point here for this discussion. Now you lower the temperature. This is 343 is higher than room temperature. They go to near room temperature. See how this line has become smaller in intensity and than this one. So intensity is not small, but it has become broader than the signal here. So it is showing this behavior means we already know now that anisotropic interactions are appearing even in the liquid solution at this temperature. So you go to still lower temperature here. This is 250 or something. I can't see this thing. Something is overlapping here. But you see how strange looking lines have come here. This line has become very, very broad. And middle line is not so broad, but the other left hand side line is also become broad. So this also is due to the anisotropic G interaction, anisotropic hyperfine interaction. So finally, if you freeze the sample, it changes to something like this. So you see, information is same in all the cases, but the appearance is different. So in all our cases, the anisotropic interactions are showing their presence by changing the line shape. Now, see the interesting behavior that going from slightly higher than room temperature to very low temperature, how the line set changes. What is happening here? Only there is no chemical change to the radical. There is no chemical change in the solvent. What has changed is temperature. Now, how does the temperature affect the solvent? It changes the viscosity. So it becomes more viscous here. Now, how does that affect the EPR spectrum? As I said again and again, how much of that anisotropic interactions are getting averaged out. So that averaging is not very effective at lower temperature or in higher viscosity. So now turning it around this behavior now, that this molecule, which is very stable, you can buy from a chemical supplier and they will stay there for months. So this has become a very sensitive probe to measure viscosity of a solvent. Or solvent is of course very common to measure, but some biological system like cell or peptides or I don't know, some sort of lipids membrane. So this can be used as a probe. So I've given the values of the G's of this temple. See, they are not same for all the 3 directions, slightly different there. But this slightly different actually is a large difference can be seen in the experiment. Similarly, the hyperfine interaction in the 3 directions, they're quite different. So such large anisotropies make it spectra sensitive to the viscosity of the environment. So let's see how that is used now. These are all different types of this stable organic free radical, and these are called spin levels. Some leveling technique, that is, you can level your whatever species, whatever region you're looking at, that region one can keep this molecule, or you can bind through this functional group, and then look at the viscosity. So since slow tumbling doesn't average the anisotropic interactions, this can be a good probe for knowing the viscosity at a place of interest. So here is an example, experimental data. This is DPPC is some sort of what is it called? Vesicle. So what is the viscosity in a vesicle? The tempo is put in that vesicle at this is room temperature. So what happens if you see the spectrum? This is the low field line. Then this one, this looks like two lines appearing here. So that's very different from again this. This is the normal viscosity. One gets this one. That same molecule bigger. So spectra of this kind. So this has been identified to be coming from two different tempo radical. The tempo radical is same, but from two different environments. One is at low viscosity, and the other is the lipid phase in high viscosity. So the high viscosity gives this broad little line here, and this narrow line comes from the low viscosity. So this simulation actually is showing that one can simulate this line here and also simulate separately the line here, and combination of this will give rise to the overall spectrum here. So that way one can find out the viscosity of this DPPC vesicle. Now, if we this is done at the 9 gigahertz experiment, EPR spectrometer expand. Now, if you change the spectrometer frequency, the G value decides the line position. Now, this anisotropic G being different in different direction at higher frequency, 94.3 gigahertz, the line should split further. So what we saw there at the same experiment, but at different temperature, you see how these other lines which are coming from the high viscosity, they have spread out, separated from this narrow line which is coming from the low viscosity. Let's compare quickly here. You could not see this here. Only this line was seen here. But if you go to higher magnetic field and higher frequency, the spectrum shifts, and then this appears separately. So this is much more convenient to identify and interpret. Now here another one, some spin level here. That at putting it a cytochrome, cytochrome thing, that gives us a spectrum of this kind. Again, it can therefore give information about the viscosity or fluidity of the site. That is one important application. How are you doing with the time? 70. We should stop at 5:40, 50, right?
Yeah, let me check the schedule.
Yeah. So next application is photochemistry and EPR spectrum. EPR. Photochemistry means, of course, that chemistry in the presence of light. So often when the molecule is excited by light, molecule absorbs light and goes to, see, most of the molecules are in the singlet ground state, most of the molecules. So by absorbing light, go to S1 excited state. Then sometimes they also go to triplet state by intersystem crossing. Now here there are two unpaired electrons. So therefore this becomes a paramagnetic species, and that can give rise to EPR spectrum. That's one aspect of application of EPR in photochemistry. But this is no chemistry, but molecule goes to triplet state. Or excited molecule can undergo a chemical reaction. Now, this chemical reaction can sometimes produce free radical, and free radicals are paramagnetic, and they can be detected by EPR spectroscopy. But trouble is that free radicals are usually very reactive. Excuse me. So it is usually difficult to record their EPR spectra. But if you can detect them, then they actually give very unambiguous evidence of the presence of the radical, and based on that, one can formulate the reaction mechanism. So let's look at the triplet state now first. So triplet state, as the name implies, that there are two electrons which are unpaired. So effective electron spin becomes 1. So its component will be 1, 0, minus 1. 3 components. So in the magnetic field, this 3 magnetic moment will interact this way, that one will be 0 corresponds to no effect on the magnetic field, and plus 1 increases with energy, and minus 1 decreases with energy. So this is again a Zeeman splitting. In case of one electron, which is spin is half, it was split into 2 lines. Now, the triplet state energies are splitting into 3 lines. So you can think of a similar EPR experiment here. And a given micro frequency, one can scan the magnetic field and see the transition. But you see, for a given magnetic field, this gap from -1 to 0 is same as 0 to 1. So there will be 2 transitions, but they will take place at the same magnetic field, because this gap is same from here to -1 to 0 is same as 0 to +1. So you should therefore see 2 degenerate EPR transitions. By degenerate, I mean they're appearing at the same magnetic field. That's the way this picture looks like. But in reality, the situation is not that simple. There are a lot more complications there. Complication is something, of course, good in science, because you learn something more about the system. It is not that simplistic. So let's look at the thing. First, look at the EPR spectrum of a triplet molecule, which is naphthalene. Now you see how many lines are appearing here. This is, of course, an artifact. It is some free radical formed when the light was falling on the sample. So ignore that. Other than that, you see that there are 6 lines of this strange looking shape. And what we expected here, this will give you only 1 line. Naturally, a lot more interactions are there, which one can find out by looking at the triplet state of the naphthalene triplet. Now, we will not get into detail of this, but try to understand at least qualitatively what are the interactions which can give rise to such extra lines. These are not hyper-one lines. These are again the transition right here, but it is not obvious why so many lines should come. So again, let's go back to triplet state interaction. Now we have got dipole-dipole interaction between 2 electrons. Electron number 1, spin half. It has got a magnetic moment μ1. Electron number 2, again it is spin half. It is magnetic moment 2. Now, depending upon this orientation, this energy will change the dipole-dipole interaction. So, 2 electrons are influencing each other to produce some energy of interaction, and that depends on the direction. So, we will not get into this interaction, actual expression of the interaction. Effectively what happens is that if this dipole-dipole interaction is absent, then suppose this is the energy. And this interaction actually produces 3 energy levels, these sort of things. Let's call dxx, dy, dz, for whatever reason. Let's say x, y, and z. So this splitting is the splitting of the 2 electron energies because of the mutual dipole-dipole interaction. This is not yet because of the magnetic field. We'll apply magnetic field over and above this splitting which has already taken place. Oh, sorry. This splitting, which is now inherent in the molecule of the triplet state because of the interaction of 2 electrons, this is called zero field splitting of triplet state. Zero field splitting means splitting even in the absence of external magnetic field. So how strongly these 2 electrons interact, that will decide the magnitude of the splitting. So this is the property of the molecule now in the triplet state. And experimentally, if one can measure this one, that gives you the idea about the dipole-dipole interaction that is taking place in the molecule. So now we apply magnetic field. This magnetic field applied here. So these are the 3 levels, Tx, Ty, Tz, in the zero magnetic field. They are already split now. Now, depending upon the direction of the magnetic field, as I said, the dipole-dipole interaction is direction dependent. If it is applied along the x direction of the magnet of the molecule, where these 3 levels are designated according to this direction of the molecule, this becomes independent of the magnetic field, but these 2 changes this way, the way the Zeeman splitting is. Now here, if you do the EPR experiment for this much micro frequency, they will take place at different magnetic field. -1 to 0, one transition here, and 0 to +1, another transition here. So you get 2 lines at 2 different magnetic fields. Similarly, if the magnetic field is parallel to the y-axis of the molecule, again there will be 2 transitions, but at 2 different magnetic fields, here and here. So you get 2 lines of this type. Finally, if the magnetic field is parallel to the the other axis, x, or whatever the other axis, third axis, then you get two other lines here. So effectively, therefore, B parallel to Z gives two lines here. This is the value of the one of the parameters of this zero field splitting. B parallel to Y gives this two line. B parallel to X gives two other lines. So the absorption spectrum actually goes all the way from this to this. Everywhere the molecule is absorbing. So that is the absorption profile. And wherever there is this kink here, that corresponds to one of this transition here, this place here. So the EPR spectrum doesn't appear in the form of absorption, it appears in the form of a derivative. If you take the derivative of this thing, this actually gives rise to this pattern, which is exactly what you saw in case of naphthalene, triplet. This one, exactly the shape we got here. So the information about how much this splitting is, this splitting here, these are the splitting now can be very accurately measured from this experiment. That is the information one can get from triple state. Next is that photoelectrically generated free radical. What sort of information we can get? But how to do the experiment? See, for the free radicals are short-lived. They don't live for a very long time. They're very reactive. So it is not very probably meaningful to do photolysis in one lab and carry the solution to the EPR spectrometer in another lab and hoping that some radical will still survive and give you the spectrum. That will rarely happen. Most of the radical will disappear by then through secondary reaction. So one has to do is to photolyze the sample right inside the cavity of the spectrometer and have the light on all the time when you are recording the spectrum. This is called continuous photolysis and obtain a steady state concentration of the radical inside the spectrometer cavity. And that hopefully can give rise to sufficiently high concentration so that the spectrum can be recorded. And there are two other techniques we will see in course of time. So let's first look at the continuous photolysis, how that is done. So here, I try to explain the experiment. This is my cavity here. If you remember, this is a cavity. This is a screw which adjusts the microwave coupling. So here we put the tube here and have a pump. Where is the pump here? There is a pump here which takes this reaction mixture, pump it through, maybe if you want to lower the temperature, some low temperature bath and push it through this tube here and take it out and put it back here. You can keep on doing it continuously and same time have a small opening in the cavity and shine light through this. The light falls here all the time. So this is the steady state photolysis. This thermocouple is kept, which is to measure the temperature if you are doing a variable temperature experiment. So that way the experiment is not technically very difficult to do. So what you do is therefore have continuous light irradiation and look at the spectrum as the photolysis is going on. This is one example here. So here, this is the parabenzoquinone put in this isopropanol and shine light, and we get a radical of this kind, the spectrum of this kind. Now we know how to interpret this, and looking at the hyperfine pattern and the number of them, one can say this is actually coming from this radical here, which is semiquinone radical. And this is the absorption spectrum of this, which of course the spectrometer doesn't detect. The spectrometer detects in this form, but nevertheless, this is an absorption spectrum which looks like this. So we know for sure this radical is forming. We still do not know what happened to the what is the reaction mechanism for that one. It only says that the radical is forming, so one has to think of a reaction mechanism for that, and that will be the chemistry part. Now here this same experiment is done in ethanol. See, previous one was done in isopropanol. Now here what happens now? It seems you see you can identify the similar radical, similar lines are present here. This bunch here, similar to what we have here. In addition, there is some extra line. You see one here, one there, another one here. Okay, this extra line here. So that means that previous radical is forming, no doubt, but some other radical is also forming, and one can carefully find out the coupling constant and the intensities. And the simulation shows that this blue is the one radical which is same as this radical here, and Red is the other radical which matches with this. That has got 1, 4, 6, 4, 1. This is the radical of parabenzoquinone anion radical. So that way one can see that both the radicals forming here. This PBQ with a hydrogen atom here, and this is the anion form of that. Another experiment now. Here acetone in isopropanol. It gives rise to this spectrum. Now here, when this experiment is done in the presence of UV light. Now here, acetone absorbs UV light and goes to excited state and does some chemical reaction to produce this spectrum. Now here, there are actually 7 lines. The intensity pattern follows this, and one can definitely say from this number that this radical must be this. There are 6 equivalent protons are present there, producing these 7 lines with equal spacing. And so this is the radical which is forming here. So the reaction mechanism will be something that this hydrogen atom from here comes to the other one, so producing this radical CH3 C dot OH. So that's the way the one can shine light continuously and look at the spectrum of a radical which is reasonably stable, in a sense that this gives sufficiently high steady state concentration to give the, so that the spectrum can be recorded. But most of the radicals are not that stable. So this is the another way of trying to get EPR spectrum of radical which is not so stable. This technique is called spin trapping technique. You see, the name implies that you are trying to trap the spin. What does it mean? Suppose there is a reaction which produces a radical R dot, and it's very reactive. It doesn't stay for a long time. So allow it to react with some other neutral molecule T, I call trapping agent, and it produces a radical RT dot. And it may so happen that RT dot is a reasonably long-lived. It is not very reactive. Then that reasonably long-lived radical can be detected in the usual manner. So you trap the short-lived radical by trapping agent to produce a reasonably stable radical. So that is the idea of the spin trapping experiment. So conceptually, it is not very difficult. So let's see how it is done in practice now. So here, this common trapping agent is of this kind, NO type of thing, nitroso compounds. This is one of them. So when R dot comes here, it attacks this place to form a bond of this kind. Now you already know the nitroxyl group which you are already talking about, the tempo, for example. These are reasonably stable. So if this R dot and R are bulky group, then this molecule doesn't really react with other radical because of the steric hindrance. This becomes a reasonably stable radical. Similarly, another one. R dot comes here and it attacks where? This carbon to produce a radical here. These are the common trapping agent. So this will be a reasonably stable radical which can be detected in the EPR experiment. Another one is this nitrone compound. That was nitroso compound, the nitrone compound, NO of this kind. So here, for example, you take this ethyl radical, which is extremely difficult to detect in EPR spectroscopy. So this can attack here, this place. And then this N plus nitrone becomes NO nitroxyl group again. So this becomes a relatively stable radical. So the spectrum of this will be triplet splitting due to the nitrogen 14. And then there are other nucleus which are very far, but nearest to this is this proton is here, 1 proton. So that will give us a doublet. The spectrum will look like this. So effectively, your radical which is trapped here is quite far away from this radical center. So all the spectrum looks very similar, no matter what radical is trapped. So this is one of the, of course, weaknesses of this technique, is that you may not be able to say very definitively what radical is trapped. All you can see is that my reaction has produced a radical which has been trapped here. So one has to measure the G value, for example, very, very accurately. Then one may get some idea that if the radical is different, one can get slightly different value of G. Or the splitting may also be slightly different. So by careful measurement, one may be able to say something about the identity of this radical. Now, this is another spin trap. This is a pyrrolidine compound. The 5-member ring here. Again, it is nitrone, but when some radical here attacks this place here. Then it gives rise to again a nitroxyl radical, and these are the other bulky groups here. Now here what happens here? They again nitrogen will give rise to splitting of 1:1:1, and this proton will give rise to another splitting. But for this molecule, the hypermobile splitting due to this proton is quite sensitive to the nature of the radical here. That way, it is much more informative in telling you what sort of radical that has been trapped there. This is 17:44. When do we stop? When do I stop?
We still have 10 minutes, but I see, Professor Das, there's a flood of questions for you in YouTube. So, if you can...
I'll skip this example. These are real examples. Okay. You got the idea of spin trapping. It is basically this. So let's not worry about the examples. These are real examples. Now, the problem of spin trapping is, of course, it's a useful technique, but you trap a radical, but since the information is very little in the spectrum, it may not be a radical you have in mind in your reaction mechanism. Sometimes the trapping agent itself produces a radical in the presence of light. So one has to have a lot of control experiment to make sure that the radical that you are seeing is indeed coming from the reaction that you have in mind. Now, a trapped radical of your interest doesn't necessarily mean that your mechanism is certain. That is creating this one. Because there could be a radical formation from an alternative method, which you may not have thought about. And finally, you may not see any radical in the spin trap experiment. But that doesn't mean that radical didn't form. It may have so happened that that was very reactive radical. It just didn't get trapped sufficiently high concentration to give rise to the stable radical. So if you don't see any radical and start writing a mechanism where radical is not involved, that may be not quite right. Okay, this is the final part of this thing that, see, these are all radicals which can be trapped and hopefully they can live for a long time. But by and large, radicals are very short-lived. How can you detect those radicals? This is a very, very different technique now, which is called time-resolved EPR spectrum, where we look at the signal as a function of time, as and when the radicals are generated. So I'll give a very brief idea about this for these people who are quite new in this field, and we hope you might like that such a thing is possible, because these are usually not taught in textbooks. So radical can be generated in light, pulse light in this particular case, or electron beam, which is called radiolysis. So idea is that capture the radicals right at the moment they are generated. Now for that one needs an EPR spectrometer which is very fast, which can record radical or EPR signal very quickly. For that, this modulation that I mentioned yesterday, which produces the derivative signal, that makes the spectrometer slow. It doesn't respond very fast to the change of the EPR signal. So you don't need that one. Remove this altogether and directly look at the absorption signal. This is the spectrometer with direct detection. So what we'll get is the signal directly in the absorption mode. So there, what is done here is that usually the light source could be pulse source, laser light. This comes here periodically. This laser light comes here, and it keeps on repeating. And then when the laser light hits in the cavity and reaction takes place, it gives rise to some microwave signals due to the generation of the radical. We try to capture this signal in a microsecond time resolution. That is possible now. And then plot that signal as a function of time. As a function of magnetic field. Capture a part of the signal at a given time and plot as a function of magnetic field. So here is an example how it looks like. This is a duroquinone, and it is excited by light, and it takes a hydrogen electron from this amine here, and it becomes an anion radical, and it gives rise to this absorption spectrum. But actually, it is not absorption spectrum. With the spectrometer is set up, absorption spectrum should give the signal which goes up, so it goes down. That means it gives an emissive spectrum, which is quite strange. That why should it give an emissive spectrum? But the fact that it does means it is telling you something quite a novel information, or not novel, unique information about the reaction mechanism. And the signal that you've seen here, it first starts from zero signal. The laser comes here. Immediately the EPR signal becomes negative, and then slowly means time is microsecond. If you record a longer time, that's 100 microseconds, it goes to emission to absorption and then goes to chemical decay here. So that EPR spectrum actually changes its sign from emissive to absorptive signal. We will not get into the understanding the reason for this one, but at least it gives you that very interesting information, that something extraordinary detailed information one can find out about the production of radical and how the electron spins are evolving. That information is right here. So one can record this spectrum as a function of, let's say, magnetic field direction domain here and the time domain here, and you can get this sort of two-dimensional EPR spectrum. And this gives the complete characterization of the EPR signal as a function of both time and field. Let's not get into that one. But similar thing actually one can get an NMR signal also. This is an experiment where some thermolysis is done. This molecule, peroxide, is heated by increased temperature, and look at the NMR signal of this reaction product. And you see here, this NMR signal which normally shows absorption, this. But some of them comes in the opposite direction. This is the emissive signal. So something strange is happening here also. So what is the common thing between this and the EPR is that we are looking at the NMR or EPR signal right at the time they are generated. Another example of similar NMR, where this is the CH3CH2Cl. This is very ordinary molecule whose NMR signal should look like this, quartet and triplet. What the spectrum that looks like when you record it, when the reaction is going on, the two lines are absorptive, other two are emissive. Here first line is absorptive, middle line is gone, and third line is emissive again. So that means that there is something interesting reaction mechanism which are giving rise to this sort of electron spin dependent signal, which is dependent on the population, and population is not following the Boltzmann population. They are deviating from the Boltzmann distribution. So this is a new phenomenon that was discovered from 1960s, and it has become very, very popular after that. It is called chemically induced dynamic electron polarization. When you see the thing in EPR and NMR, similar thing is called chemically induced dynamic nuclear polarization. This polarization means the population distribution do not follow the Boltzmann distribution. They are polarized in a way that either the alpha spin is more populated or beta spin is more populated. Accordingly, the signal becomes absorptive or emissive. A general term for this is chemically induced magnetic polarization. So this interaction, which can show this sort of feature, can be seen only in NMR or EPR experiment. Optically, they cannot be seen because this interaction energy is so small. Optical spectrum has no information of this kind. So this is a very, very powerful technique to give or obtain a very detailed microscopic and molecular level mechanism which involves the spin of the electron to produce spin selective interactions, and that information is seen in the spectrum. So what are we different now? See, this same experiment we saw that acetone in isopropanol gives us the steady spectrum of this kind. Now, if I do the same experiment in this time resolved mode, the steady spectrum shows absorption of this kind, but in time resolved mode, the lines are placed at the same position, but this low field 3 lines are in the opposite phase and compared to the high field lines. So you see, these becomes emissive line and this becomes absorptive line. So here the electron spins are polarized such a way that different hypercon lines have different type of electron spin distribution. So that could not be obtained from the steady state EPR spectrum, but this time resolved spectrum, which is recorded at 0.5 microsecond after the result pulse, one could see such a spectrum. Means we can learn a lot more about the generation of the radical. Similarly, this quinone in alcohol gives rise to this spectrum in the steady state mode, but if you look at the time resolved mode, these quinone lines are appearing here in the emissive, and the solvent from the alcohol, they are also seen here, this cross here. They are from the solvent. This radical is the solvent radical, which can see here, which could not be seen in the steady state. I think with this, we have more or less given rise to the idea. These are various examples of this kind. So tempo, a stable radical, and suppose tempo is not chemically reacting to a triplet state of naphthalene, but quenching the excited state. So then what happens? The EPR signal of the tempo, normally we see the 3 absorption line. And what it shows here is that all the 3 lines have become emissive. Or it is stable radical tempo, no chemical reaction, but the quenching process is such a spin selective information or interaction is such a spin selective manner that the 3 lines become emissive and not to the same extent. This shows also a window to find detailed information about the quenching process. See, the molecule is, instead of naphthalene, it is a coronium temple, then same quenching process changes to the polarization of the tempo to absorptive phase. So why it is so? That is of course detailed. But at least information content wise, this has got a rich information of a very, very detailed electron spin dependent interactions, which are otherwise almost impossible to identify from any optical experiments. This is the power of the time zero EPR experiment. So the power of this experiment is that it can identify the radicals that live longer than just a few nanoseconds. And most importantly, it reveals a detailed picture of the spin evolution of the radical. And that is called spin dynamics. Now, this summary of what we have learned today. That we have learned the EPR spectra of transcendental complexes, a very, very rudimentary knowledge. Then use of stable radicals at spin level to prove the fluidity of biological systems, and the characteristics of triplet state EPR, a spin trapping technique for short-lived radicals, and time resolved EPR technique for direct detection of photochemical and photophysical processes. Photophysical process is the quenching process here. There is no chemical reaction, it's just quenching. And the spin selective interactions revealed through the electron spin polarization is unique capability of time resolved EPR techniques. Now, we have really gone through very vast areas in a quick manner, in a qualitative fashion, but all these are described in detail in my suite of lectures, the 25 lectures. If you are interested, go to this website or this one. They're described in detail. Each of them have been described in detail. So here, I think we are end of my presentation. I hope I have not exceeded my time by too much. That's all from my side. Thank you very much.
Thank you, Professor Das. That was something which usually we don't get in textbooks. That's
yes, yeah. I hope you find it interesting to know that such things are possible.
Yes, I mean there are a flood of questions in YouTube chat window, which definitely shows how much kids were fascinated by the concepts which you just shared with us. So I'll share these questions since we have felicitation program in a couple of minutes. We can try to answer as many as possible. There is a question from Priyal Sharma.
Yes.
What is residual angular momentum? Where does it appear from?
Orbital angular momentum. Which is
residual.
Yeah, residual with normally electron in a d orbital should have L equal to 2, right? SPD, S0, L equal to 1, P, S equal to 0, P equal to D equal to 2. L should be equal to 2. So electron d orbital should have angular momentum equal to 2 units. But it is really not 2. It becomes very, very small. But nevertheless, it is never 0. That is called residual orbital angular momentum. That will add to the spin angular momentum and produce the complicated total angular momentum.
Okay, thank you. Parul Sharma, she has 2 questions. What are G values in ESR spectroscopy? That's the first question. And the second is, what is zero field splitting in ESR?
G value is, I mentioned, as simplistically speaking, it is as a probabilistic constant between an angular momentum and magnetic moment. So magnetic moment of electron comes from the angular momentum. It is a proportionally constant if you look at it that way. That is correct and simplest thing to understand. One angular momentum, other angular momentum, they are parallel to each other, they are proportionally constant. But it's so often that it is not quite a proportionally constant when both orbital momentum and spin angular momentum present there. Then it becomes somewhat complicated. But let's go to the very beginning. This proportionality constant is the best way to understand that. Here. See, this is the spin angular momentum. For electron, speed is half. This is the magnetic moment of the electron spin. This is the proportionality constant. That's all, pure number. Bohr magnetic is the unit of angular momentum. Similarly, for orbital angular momentum also, L is the orbital angular momentum. This is the magnetic moment due to the orbital motion. This is the proportional constant G. That's it. Nothing more to it. There's no magic about it. Magic is that only when both are present there, then it is not quite correct. Total angular moment can be added this way. But this magnetic moment will not be parallel to this one. So you can't write as a pure number here. Then it becomes a matrix. That way things become complicated. About the next question was about the residual. This is the splitting. Yeah, here. This dipole-dipole interaction of two electrons, when they're present there, they split the energy level even in the absence of magnetic field. Here, these two electron magnet, one electron spin off, other electron spin off. So they will like bring it to magnet nearby. What is the energy of that? They will split the energy in this way. When there are no interaction, this is one level. Now they will split into three. These are the splitting, because the two magnets are influencing each other. This is the zero field splitting. Zero field simply means that splitting in the absence of external magnetic field. That's all. So if you have brought two magnets closer, you can bring it this way. They will try to attract one way. Other way, north-north will try to repel, right? So that way, two extreme places. In between, this microscopic magnet will behave such a way that two such magnets will try to split energy in this possible way.
We can take one last question. It's in the Zoom chat box. It says, can we study a system with more than one unpaired electron by EPR?
Here is the example. Triplet, right now, of course you can. Manganese. Manganese has 6 unpaired electrons, or 5 I think. Yeah. 5 unpaired electrons. Yeah. So transmetals are full of unpaired electrons. Some of them are easy to record, some of them are not so easy. Right now, the example right here is a triplet state. Yes, why not?
So there are some more questions. I would request the participants that they can directly email Professor Das, and I'm sure he'll be happy to answer all the questions.
May I just 10 seconds to thank all of you to ask me to give this talk. I hope it was somewhat informative you and you probably it is. I won't say useful because so much you can learn, but at least you got some names here and there. Hopefully, you'll find it interesting enough to figure out more about this. If I have been able to do that, then at least I have done something useful.
Yes, for sure. Thank you so much. It was very interesting, and yeah. So we would like to start with our felicitation program. I see that the chief guest are
How do I stop sharing the screen?
So you just have to click on yes. It has stopped.
Already stopped.
Yes. Yes. So I see our Dean Student Welfare, Professor Hardeep Singh, is already here. Priyal, I would like to hand over you. Yeah. Priyal, you are not audible.
So here we are done with the scientific talk. Hello?
Yeah, it was cracking. Now it's okay. Please go ahead.
Okay. So here we are done with the scientific talks for this conference. So putting an end to the curiosity of all the participants, I would hereby invite Yatin Batra, a final year chemistry undergraduate GNDU Amritsar and the president of the CIROC, who aims to popularize science, particularly chemistry, among students via the platform of CIROCs. He will host the felicitation program. So over to you, Yatin.
Yeah, hello. Am I audible? Can someone please confirm? Yeah, thank you, Priyal, for such a nice introduction. So till now we have seen all the sessions have been very fruitful and wonderful so far. And as Jasmine said, we would now like to proceed towards the last part of the conference, that is the award announcement. So for this, I would like to welcome and introduce our DSW sir, Professor Hardeep Singh. So he is in charge of all the clubs at GNDU, and it is all because of his support and motivation that CIROCs has been able to conduct so many successful events, including webinars, which includes also 2 national and 1 international conference. All of this during the lockdown itself, which may not be possible without his constant support throughout. So moving towards the poster awards, before I invite Professor Hardeep, I would like to announce the categories that we are having in poster presentation. So at first, we have the first category, Outstanding Poster Award, which will be 2 in number by ACS Publications. And then the second category will be called Excellent Poster Award, 3 in number. And then the third category called Best Poster Award, which will be 4 in number. In demonstration category, we will be having two different categories, that is lab-based and home-based demonstrations, and 2 awards in each case. So now with this, I would like to invite Hardeep sir to please announce the name. And when he will be announcing the name, I will, after each name, I will tell what this award is comprised of. Please, sir, over to you, sir.
Thank you very much, Yatin. And before I start spelling out the names of the various winners in the different categories that we have, I must congratulate the organizers of this online students conference on spectroscopy for the excellent efforts they have put in. I'm sure that very serious deliberations might have gone last 2 days that we have had this particular conference. I'm aware of this particular fact that spectroscopy is probably one of the very potent tools in science, especially in the physical sciences that we have. And I am a little aware, I'm not very in touch because not like the area in which I work personally, but I am aware of this particular fact that a lot of progress has been made in this particular area. And when I was studying chemistry a long time back, about 30 years back, the importance was, a lot of importance used to be given to spectroscopy, and it happened to be one of my favorite subjects as well. So those are the things, but I always find this thing very interesting, and I have gone through the titles of the persons, the posters who have been selected for the various awards. The very interesting applications have been carried out using various aspects of spectroscopy. It's very interesting. Second thing is, it is more important to note down that this is a students' conference. And if you look at the kind of titles I have, I think a lot of work has already been done by the students, and a lot of talent has been unearthed this way in this particular area. I am of this particular view. I have always been of this particular view that pure sciences should be given their due. They have not been given their due so far. And a lot of emphasis is on applied sciences and electronics and computer science. That is fine, but without pure sciences, probably will not be able to move ahead in technology and applied science as well. So this is one thing that will encourage the students to go into the pure sciences and do well in pure science as well. So good job done by all of you. I congratulate you all once again. Dr. Bindia, remotely, Dr. Venus also is sitting in Germany and probably will be contributing. I'm sure he must have contributed to this conduct of this conference as well. The student contributors, the coordinators, Yatin, Priyal, and all other persons who have contributed to this thing. It's a very massive effort, I must understand. You see, it's very easy to say it's an online thing, but a lot of effort goes into organizing the, I mean, you have to conduct a single lecture in class, a lot of effort goes into that. This is a full conference. So I understand the effort that you people have put into this. And once again, congratulations and very well done. I mean, it's a very well done job. I hope this will be repeated in the times to come. Now, not taking much time, I'd like to announce the first award, poster presentations, ACS Outstanding Poster Award 1. It goes to the ID number NSCoS-1, Dr. Prabpreet Singh.
So, telling about this award comprises a cash prize of Rs 2,500, sponsored by Society for Promotion of Science and Technology in India, and a certificate by ACS Photonics, along with 1-year complimentary ACS membership, which cost approximately 6,000. Thank you.
He belongs to Guru Nanak Dev University, Amritsar. Sorry, forgot to mention the institute. Second award, the Outstanding ACS Outstanding Poster Award number 2. It goes to ID number 07, Deepika Sardana. She is from Jawaharlal Nehru University, New Delhi.
So telling about this award, it comprises of a cash prize of rupees 2,000 sponsored by Society for Promotion of Science and Technology in India and a certificate by ACS publication, a journal Analytical Chemistry, and 1-year complimentary ACS membership.
Fine. The third award is the second category of award, that is CRSI Excellent Paper Award. It goes to the ID number 11, Navleen Kaur from Guru Nanak Dev University, Amritsar.
So telling about this award comprises a cash prize of rupees 1,000 sponsored by Chemical Research Society of India, local chapter Chandigarh, Amritsar, and also a certification by Chemical Research Society of India, local chapter Chandigarh, Amritsar.
Fine. The second award in this category is CRSI Excellent Poster Award number 2, goes to ID number 22, Poonam Sharma, again from Guru Nanak Dev University, Amritsar.
This award also comprises the same amount and the same certificate by Chemical Research Society of India, local chapter Chandigarh, Amritsar.
Fine. The third award in this category, the CRSI Excellent Poster Award, award number 3, goes to the ID number 26, Samantha Yadav from University of Delhi, New Delhi.
This award also comprises the same cash amount and a certificate by Chemical Research Society of India, local chapter Chandigarh, Amritsar.
Right. Now the next category award is ACS Best Poster Award. The Best Poster Award number 1 goes to ID number 20, Gitanjali Chopra from Guru Nanak Dev University, Amritsar.
This award comprises a certificate by Journal of American Society for Mass Spectrometry and 1-year complimentary ACS membership.
The second award in this category, the ACS Best Poster Award, goes to Manveer Kaur from GNDU, Amritsar.
This award comprises a certificate by Journal of Physical Chemistry B and 1-year complimentary ACS membership.
The third award in this category goes to ID number 2, Amita Singh from University of Lucknow.
This award comprises a certificate by Journal of Physical Chemistry A and 1-year complimentary ACS membership.
The fourth award in this category, ACS Best Poster Award number 4, goes to ID 23, Abhishek Dash from Indian Institute of Technology, Hyderabad.
This award comprises a certificate by ACS Omega and 1-year complimentary ACS membership.
Those were the poster awards. Now we come into the demonstrations. Best Demonstration Award number 1 in lab-based category goes to Jagdish Kumar Hazra from Indian Institute of Science, Education and Research, Mohali.
This award comprises a cash prize of rupees 1,000 sponsored by Society for Promotion of Science and Technology in India and a certificate.
The second award in the demonstration category, lab-based category, goes to Sahil Gaso from Guru Nanak Dev University, Amritsar.
This award comprises a cash prize of rupees 1,500 sponsored by Society for Promotion of Science and Technology in India and a certificate.
Fine. The best
I'm sorry, Yatin, I think you misread it. The first award was for 1,500 and second was for, the first award you announced was for 1,000. I think it needs correction. It was for 2,000.
Yeah, first best demonstration, first award for rupees 2,000 and second for 1,500. Yeah.
And the best demonstration award in home-based category has been shared by 2 students, Pranavi from MGN School, Kapurthala, and Abhir Mahajan from Millennium School.
This award comprises a certificate of best home-based demonstration from all the sponsors of the conference. So these were all the awards. And with this, I would like to congratulate everyone, and also a big thanks to DSW sir for taking out
I would like to add that my congratulations to all the award winners. Doesn't matter whether you have won the first award or second or third. And the more congratulations, more so for all those who have participated, because participation is more important. Keep on doing your good work. Awards will come, awards will go, not a problem. But ultimately, your good work is going to be recognized today or tomorrow, no problem. So participation is important. Keep on participating. If your work is good and you put in your efforts, you'll definitely get rewarded someday. These are very, very small steps in the right direction, and you'll cover a lot of distance if you keep on moving this direction. So all the best to all of you. Keep doing good work and keep the science work go on. Thank you very much.
Thank you, sir. Thank you so much for taking out time and being here with us.
Thank you.
So with this, I would like to hand over the mic to Jasmine to please take over the session. Yeah.
Yes. So as we are at the end of our conference, so we would like to invite Dr. Bindya Arora, convener of Cyrox Club and assistant professor at Department of Physics, GNU. She specializes in atomic physics. She was recently awarded the Young Scientist Award by the Punjab Science Congress for her outstanding work in the field of blackbody radiation shift calculations for optical clocks. She is the guiding light behind all the initiatives and a pillar of success for Cyrox. So here, I request Dr. Bindya to wind up the conference with a vote of thanks. So over to you, ma'am.
Thank you, Jasmine. Thank you for your generous words. So I think it's fair to conclude that the conference was a great success. What is special about this conference is that it was totally student driven. By that, I mean every initiative was taken by student, including hosting, registration, and everything. Obviously, the mentors, me and Venus, were there every time for timely guidance. But I've never attended or seen a conference where everything, including coordination with participants and speakers, is done by students. So very big congratulations to all the students who were part of this organizing team. So it's customary to have a vote of thanks and thank everyone who has been a part of the conference and made this conference successful. So I'll start with the contribution of number of people who have been instrumental in smooth running of these talks, very interesting talks, poster presentation and discussions and networking. So first and foremost, I would like to thank our worthy Vice Chancellor, Professor Jaspal Singh Sandhu, for his support and motivation always, and our Dean Student Welfare, Professor Hardeep Singh, who has been backbone not only for this conference, but for all activities. His trust in us gives us confidence to take any decision without any mind. Like we don't have to take any permissions because we know that he trusts us and he is always behind us. I would like to thank Dr. Venus, who is a co-convener with me for this Cyrox activities. A very big thank to the student team who has worked day and night and in a very professional manner, right from the announcement of the conference, from registration of participants, interacting with them, and not only with participants, interacting with all the speakers, preparing a schedule, organizing all the aspects of conference, including web designing, time coordination, logistics, sending emails. Mr. Yatin Batra, who is the student president of Cyrox, was the brain and heart of the conference. And without his initiative, we could not have organized this conference. He was the person who gave the idea of organizing this all-student conference. He approached all the sponsors for funding. He arranged all the support from various organizations, which is a recommendable job. So I don't think without Yatin, it would have been possible. Thank you so much. Ms. Seher Soni, she designed the setup of the contents of the website and succeeded in building a logical structure with user-friendly registration procedure. So thank you, Seher. Thank you so much. Vijit and Simranpreet Kaur, they designed the graphic styles of the certificate, posters, and website for this conference. Yatin, Priyal, Jasmine, They have coordinated the program during the last phase of the preparations, and they were instrumental in composing the entire program book and abstract book within a one day, which is, praiseworthy job. Parul is acknowledged for her overall support and for setting up the jury of posters. Harleen, Abir, and Priyal, they helped us in advertising, and we can see the number of registrations and the effort they have made in advertising our conference and sending out the emails and posters throughout. I would like to thank Dr. R. Vijay Anand and Dr. Vandana Balla, and also CRSI local chapter Chandigarh Amritsar, who have have done enormous effort and effective contribution they have given in selecting and inviting speakers, which is like one of the major important part of any conference. And they had helped us very much in preparing the schedule for it. So timely contributions from Mr. Shankar Dutt and Saurabh, they are gratefully acknowledged. I would also like to thank all the sponsors for their generosity and interest in the conference, and they have supported the conference in very direct and indirect ways. Our sponsors for certificates, as Yatin told, were the Chemical Research Society of India, Society for Promotion of Science and Technology, SPSTI Panchkula, American Chemical Society via ACF Publications, Punjab State Council for Science and Technology. Thank you so much for sponsoring this awards and the conference. There were few people who were involved in the smooth functioning of our conference. I would like to call out their names. Aparna Sharma, membership in and scientific associate American Chemical Society. Dr. Ajay Jha, development editor, ACS Publications. Alison Curis, ACS Publications. Professor K.R. Dharamveer, General Secretary, SPSTI. Dr. K.S. Bath, Joint Director, PSCST. Engineer ML Garg, Director, SPSTI. And our chief guest, who were Mr. Dharamveer from SPSTI. In fact, he has sent his well wishes that he could not join the felicitation program, but these certificates were funded by their association and as well as Chemical Research Society of India. So I would like to thank all the judges who have put enormous time and effort in helping us shortlist all these participants and giving away these prizes. So I hope I have not missed anyone, including the wonderful participants who were here, and they have given such great scientific input, and many fruitful discussions and scientific interactions were part of this conference. So thank you so much for making this conference a success. And if anybody thinks I have missed anyone, kindly correct me. All right. So with this, I think we come to an end, a successful end.